Mürsel neredesin Mürsel? Hadi başlayalım. Daha onu canlı yayın verecektim. Bu general section'ları verdim. Keynote'ları verdim ona. Keynote'lardaki adamlar yabancı ya. Dakika onlar.
Alo, günaydın. Can you hear me?
Yes, I can.
Yes, Abu Salam. Yes, Abu Salam. You will be the first speaker. I guess you are going to make this your talk. Okay. Okay. You will be the first one.
Okay.
Okay. I need to check other speakers. Okay. Because there may be some differences between two places in the list and now who will realize. I am trying to fix who will talk. Okay, thank you. You are ready for your talk. And Esra, okay. And Esra, okay. Esra, can you hear me?
Yes, I can.
Okay, Esra. Esra, you will be the first speaker. Okay, Esra, excellent. The first speaker, the first Abu Salam. Abu Salam. Okay. I will invite you later. I will invite you later. There are now two speakers on the screen. Okay, excellent. We are waiting for other speakers. I cannot operate my, camera. I cannot operate my camera. I couldn't understand why it doesn't work. But it is not working. I didn't understand why I cannot operate it. Maybe, okay. What we can do, we can none. Okay. Okay, now it is working. Excellent. Okay. I change. Okay, Esra, I can see you. And Habu Salam. Okay. Esra. Okay, there are two people now, Abu Salam. You work together with Professor Gökçen, Gülden,
Yes.
and Nurdan. I
Yeah.
recognize very well both of them.
That's perfect.
I recognize because I work together with Dr. Nurdan.
That's perfect.
Our offices are opposite to each other at Yaşar University, you know.
Yes.
Please try to follow the rules, you know, the 12 minutes for your talk.
Yes,
If there are some questions, 3 minutes. I will remind of this at the beginning of my session opening. Okay, just I am trying to tell you now.
Okay.
Anyway, we are going to officially open this session in 2 minutes.
Yes, I'm waiting for you.
Okay, 2 minutes. Just I am trying to check the speakers. As I told you, there may be some differences between two places. There is a list, you know, which was shared with people, and there also, but in the real case, the speakers can be subject to change. Therefore, I am trying to check the real names. We will talk now.
Okay.
Yeah. But other speakers are not available. Anyway, no problem. Okay, maybe we can now start, you know. Okay, because good morning, everyone. This is Arif Abbasi from Yaşar University. We are very pleased to have 6 speakers with us, but on the screen I can see 3 speakers anyway, and they will talk about various renewable energy-based topics. The first speaker is Mr. Abu Salam. The title of his talk is Geothermal Energy Production from Oil and Gas Wells, a technical review. Before starting, you know, your talk, I wish to remind of you, you know, you should complete your talk, you know, within 12 minutes. 3 minutes are for questions. When 2 minutes left, I will remind of you. Okay, please.
Okay. Can you see my presentation?
This will be done by another person working for TÜBA. Okay.
Can you see my presentation and can you hear me?
TÜBA person, can you open it? I don't have, you know. TÜBA person, can you make this? Just I am trying, I will, you know, chair this session.
Okay, can you see my presentation?
Yes, presentation can be seen. You can start.
Okay.
You can start. Okay, please go ahead.
Good morning to everyone. I am Abdulsalam Mukhtarov, and I am second-year master's student of Polytechnico di Torino in Italy in petroleum and mining engineering. I am writing my thesis currently at Izmir Institution of Technology, and today I would like to talk about geothermal energy production from abundant oil and gas wells. You can see the plan, which today I want to follow, and I would like to talk about geothermal energy, abundant oil and gas well, geothermal energy production from abundant oil and gas well, and some system and applications. Geothermal energy and sources. Geothermal energy is a renewable sources, and depending on the reservoir temperature, it can be used for electricity generation or direct use, such as industry, agriculture, and cooling and heating system. There are several types of sources, such as deposit of geothermal dry steam, deposit of wet steam, which is the mixture of hot water and steam, and which is very common, geothermal water deposits. Utilization of geothermal energy. The first geothermal plant was created in Italy in 1904, and according to statistics, more than 20 countries are using geothermal energy to generate 74 terawatt-hour per year electricity. And a remarkable increase can be seen the capacity of geothermal power production between 2015 and 2020, with the high proportion recorded in the USA, Turkey, and Indonesia. And why oil and gas wells are abundant? Regarding the productive life of hydrocarbon wells, there are three recovery steps. Primary, including the natural flow. Secondary, including the water flooding and pressure maintenance. Tertiary, including the gas injection and other thermal applications. So when the third step are not efficient, we can say that the wells can be considered into abundant. So there are other reasons for the passing the well to abandonment session, such as changing in a well design and especially occurrence of flow mixture in petroleum field means the water cut is, and it's very common and important, gas manifestation, seasonal difficulties, and other reasons. Nowadays, there are nearly 30 million abundant hydrocarbon wells in the world, and due to that pandemic situation, some part of the wells are expected to pass their abandonment stage. So also, there are many benefits of producing geothermal energy from abandoned and gas wells, such as existing drilling activity. It can make the system 50% cost effective. Available geological data, including lithological data and rock properties, existing thermal properties. I can say that knowing the thermodynamic properties, the selection of the working fluid will be done easily. Also, having casing, cement, and wellbore and no gas emission means the system is appropriate from environmental aspects and can be produced continuously. You can see the table which indicates abundant oil and gas wells in the worldwide and are appropriate to produce geothermal energy. And you can see from the table, the geothermal capacity are related to well depths and temperature, and also it can be very variable due to the mass flow rate. Generally, the geothermal system can be reconstructed closed loop and open loop system. And the majority of research are related to produce geothermal energy from abundant oil and gas wells with a closed loop design system. In the picture, you can see the U-type U-tube system, and there is a U-shaped pipe in the well, and we inject the working fluid through the one pipe, and it will get more heat from the rock formation, and it will come to surface as heated through another pipe. I can see that the outlet pipe should be partially or fully isolated to prevent the heat transfer. And also, when the U2 heat exchanger are used for retrofitting abandoned hydrocarbon wells, the well bore should be reconstructed because of having casing, cement, tubing, and so on. Another is coaxial system. There are two flow paths in here. The first one is reverse flow. Reverse flow means we inject the working fluid through the annular pipe, and it will go to surface through the inner pipe. And the forward flow is a vice versa. And during the going to bottom, it will gain more heat from the rock formation. In comparison with U-tube system, the coaxial is better than, because of having more efficiency and saving more pump power. And also I can say that the reverse flow is effective than forward flow because of having larger heat extraction. There are also other applications, such as TÜBA method. In that method, we pump the working fluid through the injection well, and it will pass through the reservoir. And will go to surface through the production well. There are some parameters which are very important here: rock permeability, rock porosity, and the distance between two wells. I can say that with increasing the distance between two wells, the residence time of working fluid in the reservoir will be high. So as well as we will have efficient heat extraction. But on the other hand, if we increase the distance between two wells, we can face the loss of the working fluid in the reservoir. Another method is combustion methods. This method is completely different from others because in that method we use productive well instead of abandoned well, and the air is pumped into reservoir through the injection well, and the burning of the oil can make a way to be more heat in the reservoir, and so we can set the geothermal power plant between two wells, and we can produce geothermal energy. There are also some benefits and drawbacks in that system. So the benefit is this system is economic, and also due to having more heat in the reservoir, we will have a short payback time, and also, of course, high outlet temperature. The drawbacks are that due to burning of the hydrocarbon, we can witness the uncontrolled flame in the reservoir, and of course, high depletion in oil productive well. And the next one is there are some parameters which are very, very crucial in the producing geothermal energy from abundant oil and gas well. The first one is insulation thickness, and you can see from the picture. And insulation thickness is important. Why? Because we have current annular pipe, and we cannot change the diameter. So with increasing the insulation thickness, we will decrease the annular area. The diameter of the inner pipe is also important. So the smaller diameter means large heat extraction, but on the other hand, requested energy in the pump will be high because of we will have more pressure drop. Mass flow rate of the working fluid is strongly dependent on annular area. The selection of working fluid, it can be water, hydrocarbon fluid, and organic fluid. Geothermal gradient also is important, and the rock properties, including rock density, rock permeability, rock specific heat, and rock conductivity. The last one is also very crucial. And lengths of borehole heat exchanger.
2 minutes left. 2 minutes left.
Okay. The conclusion is that extraction of geothermal energy from abundant oil and gas well is very beneficial, and also two-well method and the combustion method can be used to produce geothermal energy from abundant and oil and gas well. Also, the insulation should be done on the outer pipe in all applications to avoid heat transfer between two wells. And the material with low conductivity should be selected for insulation for getting better results. And as a final note, the fluid and wellbore parameter selection of working fluid diameters and working fluid rate are also very important in that type of system. Thanks a lot for your attention.
Okay, thank you very much for completing, your presentation on time. Excellent. Okay, are there any questions? I can't see any questions on the questions and answers section. Guys, I will wait for some questions, maybe.
Okay.
Otherwise, I can ask one question, one quick question. You work, in Turkey, I guess. What do you think, the geothermal energy potential of Turkey?
Actually, I'm working on the parametric study, especially related to Italy, and sometimes we are working on the geothermal potential of Turkey, especially Dodan field in Turkey. Can you hear me?
Okay. Yes, I can hear you. Yes, it is very clear. Just I am checking, the screen from time to time, especially the questions and answers. Okay, to forward some possible questions to you. Anyway, okay. Thank you so much. Now I would like to invite the second speaker, Zeynep Özcan.
Thanks.
Zeynep Özcan is here. Okay, Zeynep Özcan. She will talk on. Okay, Zeynep. Okay, she will talk on working fluid selection and performance analysis of a geothermal binary power plant.
Yes.
Okay, from İzmir Institute of Technology, please. As you know, 12 minutes for your talk.
Okay, now I'm sharing my screen.
Okay, you can start after seeing your presentation on the screen.
Okay, so can you see my screen as a full screen?
Okay, full now.
Okay, now I'm starting.
Okay, so, please.
Welcome, dear participants. I am Zeynep Özcan. Today, I will present our study called Working Fluid Selection and Performance Analysis of a Geothermal Binary Power Plant. I work on this study with Professor Dr. Gülden Gökçen Akkurt. I would like to thank her that she gave me an opportunity to work with her in this study. So before starting, I would like to introduce myself shortly. I am Zeynep Özcan. I graduated from Energy Systems Engineering last year at Yaşar University. Afterwards, I started Energy Engineering Master of Science program at İzmir Institute of Technology. Now I can begin. I hope you enjoy. For today, I will be talking these topics, which are introduction, description of the system, working fluid selection, methodology and analysis, results and discussion, and conclusion. So to give a brief information about this, geothermal energy is commonly used for generating electricity, heating and cooling buildings, and also it is used for power industrial activities. And there are three main types of geothermal power plants, which are dry steam plants, flash steam plants, and binary cycle plants. In the study, we deal with binary cycle plants. Binary cycle plants transfers heat from geothermal hot water to another liquid, which is known as binary working fluids. These binary working fluids have low boiling temperature and high vapor pressure. And in heat exchanger between geothermal hot water and binary working fluids, heat transfer processes happens, and this cause binary working fluids is converted into steam form. With this steam form, it is used for generating turbine. The selection of these binary working fluids are really important because they influence the design of binary cycle equipment, operation conditions, efficiency, and environmental effect. So for our study based on another study that was made for this plant, which is located in Reno, Nevada, USA. Normally this plant has two similar units, but in figure 1, you only see the one unit because we did our analysis only for one unit and just like the other study that we based on. Because again, when you look at the figure 1, in left section, you see little cycle. In the cycle, geothermal hot water circulates. And when you look at another cycle, which is called organic Rankine cycle, the working binary fluid circulates in this cycle. So this plant employs isobutane as working fluid, but in our processes, we analyze, we made an energy and exergy analysis for various working fluid as well. This power plant operates at 160 degrees Celsius. And as it is seen in table 1, there is given geothermal plant data. This data is fixed. And we did all calculations according to these data. So working fluid selection is really important and is based on two main criteria. First criteria is environmental criteria that contains ozone depletion potential, toxicity, flammability, and global warming potential. According to these criteria, since almost all working fluids are flammable, especially hydrocarbons, I assume them with their fire prevention equipment and continue with the second criteria. According to the critical temperature and pressure, and also the boiling temperature at various pressures, the proper fluid that delivers the maximum thermal and system efficiency must be selected. Additionally, as I mentioned earlier, the power plant operates on a liquid dominated resource at 160 degrees Celsius and 1,264 kilopascal. Therefore, these criteria, isobutane and butane are 152A, are 124, and isopentane were selected. And as you can see in the table 2, there are critical temperature and pressure values as well. So for methodology and analysis, energy and exergy analysis were conducted through EES software, which has extensive thermodynamic library due to different binary working fluids based on the data given in table 1. As I mentioned earlier, geothermal resource temperature and turbine inlet temperature values are really important for binary working fluid critical temperature, because the critical temperature of a substance is the temperature at and above which vapor of the substance cannot be liquefied, no matter how much pressure is applied. Therefore, this property is related with the turbine work as well, because we don't want any moisture in the turbine as well. So the turbine inlet temperature of the plant which is 146.8 degrees Celsius, which is about 420 Kelvin, which is higher than the critical temperature of isobutane and the temperature of other working fluids, except isopentane. So according to this, turbine inlet temperature, efficiency, and losses at constant mass flow rate of each fluid analyzed and compared. Additionally, isopentane was studied in detail. As you can see, there is some energy balance and exergy balance formulas, and exergy disruption, which is total plant loss formulas, and energy exergy efficiency formulas are listed. So for results and discussion, after calculation, these temperature versus entropy diagrams, they were plotted for each working fluid. And as you can see, all graphs were shown on their own saturation line. And you can see these points represents the turbine inlet temperature, or we can say the turbine inlet stages. So firstly, when we look at the figure 6, we see unlogical graph because when I run ES code, because of isopentane's critical temperature, I obtain negative values like negative energy and exergy efficiency values and negative exergy destruction values. Therefore, as it's seen in figure 7, I change turbine inlet temperature, meaning I increase turbine inlet temperature to observe energy and exergy efficiency. So as it's seen in figure 8, there is exergy efficiency changes due to turbine inlet temperature changes. You can see I even increase its turbine temperature above isopentene's critical temperature, but even though it looks like a reasonable result, it is not, because at higher temperature, I also obtain negative exergy destruction values as well. That's why I selected 184.8 degrees Celsius temperature as optimum temperature, because at that temperature, all the results were observed and noted as reasonable. And again, in figure 9, you can see the TS diagram of isopentane at that temperature. So for the conclusion, at the end, I compared all the results for different working fluids. At 146.8 degrees Celsius, you can see that isobutane has the highest energy and exergy efficiency, which are 4.1% and 38%. And when it is looked to turbine work, again, the winner is isobutane with about 21,000 kilowatts work. And when we look at the total exergy destruction, which is, we can say, total loss of the plant, again, isobutane has the lowest total loss among them. So when we look at the isopentane's trial at the constant temperature, which is this, we get, unfortunately, negative values, but after changing turbine's inlet temperature closest to the isopentane's critical temperature, we obtained reasonable results, such as exergy efficiency is 18% and total exergy destruction is noted as 68,000 kilowatts. So for the conclusion, isobutane has the highest energy and exergy efficiencies, which are 4% and 38% respectively. The highest total work and the lowest total exergy destruction rate were encountered for isobutane as well. And while isopentane has the lowest exergy efficiency, R124 has the lowest energy efficiency and turbine work output and the total loss value. So at the end, I think it is proper to say that isobutane is the optimum working fluid among other fluids in the study at these conditions as well. So that was the end of my presentation. Thank you for listening. I hope you enjoy. Are there any questions?
Yes. Thank you very much, Zeynep. We enjoyed very much. I especially enjoyed very much. Why? Because I am very happy to be in the same session with you. You know, you graduated from our department.
Yes, I'm so glad to see you here.
Yeah.
So, yes.
Yeah, I am also proud of you. Okay, excellent. Are there any questions? I am checking the chat to check if there are any questions. But I can't see any questions. But we can discuss, you know, the one issue which is very crucial. You know, if we can compare energy and exergy efficiencies are higher, you know, than the corresponding energy efficiencies.
Yes.
No, but we know that the general tendency is to see lower exergy efficiency compared to energy efficiencies. Have you investigated this issue? Why the corresponding exergy efficiencies are higher than the energy efficiencies?
Okay, so actually, as I said it before, this study is based on another study that was, how can I say, that was performed. And with these results, I made a validation of their result as well. And they also find their results they also find higher exergy efficiency than the energy efficiency as well. That's why I continue according to their steps, and I found these results. But I believe you are also right. And
okay, also when you talk about exergy efficiency, because there are various definitions we can use for exergy efficiency of energy-related systems, as you know. Maybe, for example, functional exergy efficiency, universal exergy efficiency, and there are various definitions we can use to solve exergy-related problems. Okay, thank you so much.
Yes, I thank you. I hope you enjoy.
Okay, thank you so much. Now it is time to invite the third speaker, who is Yunus Emre Yüksel. Yunus Emre Yüksel. I can't see Yunus Emre Yüksel. Okay. From Afyonkarahisar University. He will talk on modeling and performance evaluation of the geothermal energy-based combined plant for different products. Please.
Okay, let me share my screen. I think. It's okay now. Good morning, Chair. Good morning, all attendees. Today I will talk about the model of the geothermal energy-based combined plant for different products. This is the outline of my presentation. I will start with the introduction, in which I will talk about the geothermal energy systems and why we choose to produce hydrogen and power systems. And then I will briefly talk about the definition of the system, how we integrate the subsystems together, and then the thermodynamic and parametric analysis that we have used to evaluate the multi-generation system proposed in the study. And then I will talk about the results and the discussion of the study, and finish with the conclusion part. Why we choose to use geothermal energy? Because there are some advantages of the geothermal energy. First of all, it is renewable and sustainable energy sources. And also it is stable energy supply, and geothermal energy is not dependent on the weather. And also it is not dependence, it has no dependence on fossil fuels. We can use geothermal energy on large or small scale applications depending on the sources and the temperature of the geothermal source. And also after high initial cost, we can maintain the geothermal energy with low cost. Of course, there are some disadvantages of geothermal energy. As I mentioned before, there is a high initial cost of geothermal energy plant. And then it can emit some greenhouse gas emissions, especially sulfur oxides. It can emit sulfur oxides. And also geothermal energy is a location-dependent energy source. If you don't have any geothermal sources, you cannot use, of course. So for Turkey, especially in eastern part of Turkey, there are some high temperature geothermal sources. And so we need this high temperature because to produce electricity, power, or hydrogen or other products. This graph shows the geothermal energy usage in the world. As we can see from here, Turkey is attacking in the last 10 or 5 years, and Turkey now entered the 1 gigawatt country club of geothermal energy. As you can see from here, United States and Indonesia and Philippines are the first 3 countries that use geothermal energy, and Turkey is the first place. So in this study, we are trying to produce power and then hydrogen. Why we are trying to produce hydrogen? Because hydrogen is an excellent energy carrier for future energy projections. And also hydrogen is a non-polluting energy carrier. It's economically competitive. and it is as safe as gasoline. And hydrogen is not a new energy carrier. It's used safely for over 50 years. And the important part here is that hydrogen can be produced from a variety of sources. We can produce hydrogen from fossil sources, or we can produce it from the renewable energy sources. This is the important part. This is the green part. If you compare the properties of hydrogen with natural gas and also gasoline, we can see here hydrogen has no color and also has no toxicity. It is odorless gas, and hydrogen buoyancy relative to air 14 times lighter than the air. Natural gas double time lighter than the air. And also energy by weight. If you compare energy by weight and energy by volume, hydrogen is very advantageous and more advantageous than natural gas and also gasoline. So we can use as I mentioned before, we can produce hydrogen from fossil traditional sources and also renewable sources. I will check my time, so I will skip my presentation. I will skip my study. This is the system definition of my study, of our study, that we performed by Professor Öztürk and Dr. Yılmaz. The schematic representation of the multi-generation system can be seen from here. Here, at the left or at the top left of the screen, you can see the production well. The geothermal fluid is extracted from here and is sent to separator and then sent to the steam turbine. You can see here there are 3 turbines to produce power. First of all, flash binary geothermal system, and then organic Rankine cycle plant, and then transcritical carbon dioxide cycle. We can produce power from these parts of the multi-generation system. And then some part of the power produced from the steam turbine sent to the PEM electrolyzer to produce hydrogen. At the very middle of the screen, you can see here water enters at stream 26 to the PEM water heater and then PEM electrolyzer to produce hydrogen and oxygen. And then rest of the heat energy is utilized in heat exchanger 2 to produce heating effect to the water coming from the stream 38. And then we can produce hot water to be stored later. At the last part of the screen, at the last part of the schematic representation, we can see magnetic refrigeration plant. Magnetic refrigeration plant is a cooling technology based on the magnetocaloric effect we can use here. We can use the heat energy of the rest heat energy of the system in magnetic refrigeration system to produce cooling effect. Okay, what are these numbers in here? These numbers are used in the thermodynamic analysis. We have numbered each streams in this multi-generation system and then used them in the thermodynamic balance equations. These are the state points that we numbered in the multi-generation system. These are the first column is temperature, pressure, entropy, enthalpy, and mass flow rate, and exergy values of the state points. And we use these values in these balance equations. You know, there are 4 main balance equations used in thermodynamic analysis. First one is mass balance equation. The second one is energy balance equation. And the third one is entropy balance equation. The last one is exergy balance equation. Each states in our schematic representation are used in these balance equation, and we have used engineering equation solver software to evaluate the system. Let me talk about main results and discussions of the system. This is the main outputs of the system. These are the power production rates of subsystems. The steam turbine can produce up to 17 megawatt power, and the organic Rankine cycle 1,850 kilowatt, and the transcritical carbon dioxide cycle can produce 1,681 kilowatt power. The system, this multi-generation system, can produce heating effect about 9 megawatt, and the hydrogen production rate is about 0.0124 kilogram per second, and the cooling water production rate is 1.582 kilogram per second. These are the power production rates of subsystems. Let me talk about the parametric studies. These parametric studies can be performed to evaluate the system, how parameters affect the system. The first parameter chosen in this study is the reference.
I can't hear you. I can't hear you.
Okay, let me check. Just a minute.
Okay, you can
It's
continue.
okay now. Okay.
Can you hear me? Can you hear me?
Yeah, I can hear you.
Okay,
Is
please
it okay
continue,
now?
please.
Okay, I will continue.
You can continue. Well, by the way, 2 minutes left to finish.
Okay, I will finish with parametric studies. These are the energy efficiency and exergy efficiency variations with respect to reference temperature. As we can see from here, reference temperature has a positive effect on energy efficiency and exergy efficiency because as reference temperature increases, the irreversibilities decreases between the environment and the multi-generation system. Therefore, power production rates increases as reference temperature increases, and hence exergy destruction rates of subsystems decreases as well. And this second parameter is that geothermal water temperature effect on energy and exergy efficiency. This is the very important parameter, geothermal water temperature. As we increase the geothermal water temperature from 150 to 220 centigrade degree, we can see here energy and exergy efficiencies of all subsystems increases, and also overall system energy and exergy efficiency increases. And therefore, power production rates increases as well. As you can see from here, hydrogen production rates increases about 0.0115 to 125. And also, as power production rates increases, exergy destruction rates decreases. The last parameter of this study that we performed is the geothermal water mass flow rate. As we increases geothermal water mass flow rate from 140 to 180 kilogram per second, again, we can see from here, energy and exergy efficiencies increases as well. And also power production rates and increases. On the other end, exergy destruction rates of these subsystems decreases. Of course, Chair, we performed economic analysis for this, but we cannot make it ready for this presentation. So we are trying to adapt this full paper because it is very important economic analysis. So we are trying to increase geothermal water temperature, geothermal water mass flow rate. Of course, these are making this geothermal plant more expensive. And these are the conclusions. True thermodynamic performance investigation is done in this work of integrated plant that produces power, heating, cooling, hot water, and hydrogen generation. Based on analysis results briefly, some significant crucial findings can be demonstrated as follows. The electricity generation capacity of the steam turbine or ORC turbine and CO2 turbine is computed as 17 megawatt, 850 kilowatt, and about 1700 kilowatts respectively. In addition, the heating and cooling water production capacity is calculated as 8,726 kilowatts and 1.582 kilogram per second. At a geothermal reservoir temperature of 180 centigrade degree, the energy and exergy effectiveness of the entire model are computed as 44.81 and 46.32% respectively. The proposed model's total hydrogen generation capacity is also computed as 0.0124 kilogram per second. In conclusion, it should be noted that the overall system's performance increased by rising both mass flow rate, and water temperature of geothermal fluid. Thank you for your listening, Chair. Sorry for the interruption. My internet connection is not stable because of my places now.
Okay, no problem. Okay, no problem. Thank you very much.
If you have any questions, I can answer them.
There is one question related to the cooling part of your paper.
Yes.
One question. And what is the material used for the magnetic cooling? Which has a good magnetocaloric effect.
Yeah, of course. This magnetic refrigeration system is actually a very old technology. But if you have used strong magnets, you can take good, better cooling technologies, and here we can. And also, if you have high temperature entering the magnetic refrigeration plant, we can improve our cooling capacity. So we are using the rest of the heating, rest of the temperature of the multi-generation system in this magnetic refrigeration plant. And also here we are using strong magnets to produce cooling effects.
What about the COP value of the magnetic cooling?
For this study, we have not calculated the COP, but we can done it for the full paper. We can done later, okay. Maybe.
Okay. Another question: how we can use hydrogen produced in energy? Okay. How we can use hydrogen produced?
That the hydrogen produced we can use in. Again, proton exchange membranes, fuel cells, we can use it, directly sending to the natural gas combustion in houses. We can combine hydrogen and natural gas in houses. But actually, the better one is that hydrogen should be used in fuel cells to produce electricity, and then, for example, to drive a car, something like that.
Okay.
Mm-hmm.
Okay.
Thank you for your presence here.
Okay. Thank you so much. The time is over.
Okay. You're welcome.
Have a nice day. Okay.
Thank you so much.
Now I would like to invite the fourth speaker, Esra Gün from Istanbul Technical University, who will talk on determining compensation rate for wind-solar hybrid energy system in Istanbul based on ANFIS modeling. Please.
Hi, everyone. I'm sharing my screen. It's okay?
Okay. We can see you, but okay, we can see.
Okay. My name is Esra. I'm PhD student in Istanbul Technical University, and I will talk about hybrid renewable energy systems. And my presentation, determining compensation rates for wind and solar hybrid energy system in Istanbul based on ANFIS modeling. My presentation content is some abstract introduction, Turkey renewable energy potential, hybrid renewable energy systems, data and methods, and ANFIS modeling, the final results. In this study, wind and solar energy analyses are made separately and together as hybrid systems based on the measurement wind and solar data in Istanbul and surroundings. Analyzes wind power and solar PV hybrid generations are examined with monthly and hourly profiles, and the annual revenue value of the whole-scale price of electricity calculated. It has been examined which source compensate the monthly total electricity generation values of the hybrid system. And based on hybrid system electricity generation data, an adaptive neurophysics inference system, UNFIS modeling is applied, and a monthly relationship between these sources are estimated for all locations in this study. Wind and solar energy are important energy source today with the developing technology and variety progress. With the emergence of renewable energy systems based on wind and solar, hybrid systems have been developed and which enable the use of two systems by combining them. As for Turkey renewable energy potential, this map shows Turkey solar energy potential, and our study area in Istanbul about 6 hours sunshine daily. And this map shows Turkey wind potential, and our study areas, for our study area, mean wind speed about 6 meters per second, and wind is a dynamic parameter. It can be changed easily. Hybrid renewable energy systems, renewable energy sources are extremely attractive because they don't run and don't have any significant harm to other sources in terms of environment and human health. The aim of hybrid system is to increase the efficiency by providing the use of energy source and together and to ensure that others meet the energy needs of the system if one of the sources is not decreases. The most important feature of hybrid renewable energy power plant is that energy sources are complementary to each other. And data and methods. The data used in study were measured by ISKI for 5 different stations located in and around Istanbul. And the data period, at least for 1 year, some study areas data periods 2 or 3 years, but generally minimum 1 year data was used. The solar potential in the study, wind and solar potentials for the identified regions were examined, and the capacity factors for wind and solar hybrid system are determined and modeled. Wind potentials of the sites determined by AWS Open Wind program, and our production analyses are also performed. Solar analysis is performed with PVSys program, and our production results are obtained and calculated. The obtained productions are converted into 1 year, monthly, and hourly data sets for hybrid systems, and hybrid electricity generation analysis is evaluated. The analysis includes compensation rates, capacity factor, and etc. And these tables or heat maps show that monthly and hourly average capacity factor for these sites. And the colors show that from green to red, the capacity factor increasing. And for the example, wind turbine and PV electricity generation estimated by using OpenWind and PVSys softwares, and capacity factor for each renewable energy system for wind 30% and for solar 22%. And hybrids capacity factor, wind and solar hybrid capacity factor table is here, and average capacity factor is 24%. In this perspective of hybrid electricity generation profile, the scattering diagrams for all average values for each and all months for desired time and prepared and their correlations calculated. It's modeled then the most significant highest relationship evaluated between July and August. In this study, in addition to energy production, wind, PV, and hybrid analysis, revenue analysis included two scanners was performed for ISKI, and the Ormanlı sites is the first for capacity factor and electricity size revenue and consumption revenue. As for ANFIS modeling, the relationship between the actual data and the data that ANFIS calculates and creates as a result are shown. It is seen that the relationship established with ANFIS between wind, solar, and hybrid production values and the next month's hybrid production relationship is very strong. And ANFIS and very real data relationship table is here, and the month and the next month relationship is very high. And results. In this research, there are 5 stations that scattered all around Istanbul. According to results, wind turbines and electricity generation capacity factor and revenue of these systems are calculated. Hourly, monthly, and annual energy production of the total hybrid system are also calculated for all regions. Monthly and hourly production values were taken into consideration, and the ratio of the total production value of the hybrid system was calculated. Monthly total energy generation values of the hybrid systems are analyzed based on source and compensation ratios. It's seen that mostly wind energy and PV complemented each other as a renewable source. ANFIS modeling done with relationships between the mean values data sets, and relations are evaluated and modeled using physiologic. With ANFIS annual R production values for wind turbine, PV, and hybrids are evaluated with physiologic. The relationship between the measured data and the modeled data by ANFIS examined, and it's seen that the correlation between measurement and modeled values for the next month is very high. My Francis, and thanks for listening.
Okay, okay. Thank you very much for your presentation.
You're welcome.
Okay, I am checking the questions. I can't see any questions to you. And what we can do, we have some time. Maybe why compensation rate is so much important? Why compensation rate is so much important?
Because if one of the energy source decrease or run out, the other energy source can compensate the other, and the production continue.
The production is continuing, okay. And can we You mean that we should consider this compensation rate? If you want to design a hybrid system, it is very crucial to consider this compensation rate. Okay, in the design. Okay. Okay, thank you so much. Okay.
Thank you very much.
Have a nice day. Have a nice day. Convey my best regards to Professor Şahin. Okay. The fifth speaker. Okay, I would like to invite the fifth speaker, who is Josie Rock Segnon. Okay, are you ready? Are you ready? Okay. The title of the talk is Outdoor Performance of an Improved Thermoelectric Heat Pumping Solar Air Heater. Okay. Okay. You can start.
I'm sharing my screen now.
Okay. Can you say your name? My pronunciation may be incorrect. Can you say your name, please?
Yeah, hello.
Okay.
Yeah, I am Josué Roxegnon. I'm from Benin,
Okay.
and I'm currently a master's student at the University of Nigeria. So my research topic is about energy materials, and I work with Dr. Howard Njoku. So this morning, I am going to present some of our research in on the outdoor performance of an improved thermoelectric heat pumping solar air heater. Can you see my screen in full screen? Okay, now. Okay, so as I said, I work with Dr. Howard Njoku from the University of Johannesburg, and today I'm going to talk about doing an introduction of my work, present the different applications of thermoelectric modules in solar energy conversion systems, and also the materials and methods used in this study, the results of our project, and the conclusions and acknowledgements. So as we all know, solar thermal energy systems have been improved over the years through several means, and one of the major means is by the enhancement of the heat transfer rates through the use of fins, ribs, baffles, and also the enhancement of the working fluid on the application. Also, over the years, thermoelectric generators or thermoelectric coolers have been used in different solar energy conversion application devices to improve the performance of solar energy conversion system performances. And here we can see different applications of those thermoelectric modules. On this slide, we see three of them pertaining to the solar thermoelectric power generation, where thermoelectric generators can be used to produce electricity directly from the solar radiation on the left side of the slide, and also they have been used with
Josie Rock, can you hear me? Josie Rock, Josie Rock, can you hear me? Can you hear me? Josie Rock, can you hear me? Could you please switch off your camera so that we can hear you? Josie, could you please switch off your camera? I cannot communicate with Josie Rock. Josie, could you switch off your camera?
Yes, I can.
Switch off your camera. what we are going to do now, we don't have any internet connections. Just I'm going to wait, you know, for a few minutes. I cannot communicate with him. Maybe we can wait. No connections at this moment. What we can do? Okay, okay. Okay, that is good idea. That is good idea. We are going to move to the last speaker. Okay. The title of the talk is, you know, development of hybrid power systems for North India rural areas. Okay. Gotham, are you ready? Maybe it is better to continue with you. Okay. To save the time. Okay, please.
Can you see the full screen?
Okay, please. Okay, yes, I can see. Okay. I can see.
So shall I start?
Yeah, now you can start. Yes, we can hear you. Okay. Please go ahead.
So I'm Gautam Muthanpuran. I'm from India. Currently, I'm doing my master degree in TÜBA Berlin, Germany. So as I'm going to talk about renewables, I want to say that today is the World Biodiesel Day. So I'm going to present a topic in development of hybrid power systems for North Indian rural areas. So starting with the agenda, today I'm going to introduce what is hybrid system and why we're going to use hybrid in India and so on. Next, what is the purpose of this paper and what is the methodology I used in this paper. And I want to share about few things about currently what is the energy market in India. And next, what is hybrid systems? I want to show some few schematics and some optimization techniques which I'm used in this paper. And next is evaluation criteria before implementing a hybrid energy system and some suggestions to implement hybrid energy system in rural areas. And finally, the conclusion. So starting with the introduction, what is hybrid power system? So hybrid power system is a combination of two or more resources combined to form one system. So which are mostly renewables. So in the right-hand side, you can see a bar chart. In the x-axis, you can see a different combinations of hybrid energy system, starting with the wind diesel system, going on with PV diesel, wind PV diesel. Like this, we have variety of combinations around the world. So in this chart, you can see a wind PV is the most used combination around the world. Next to that, wind PV diesel is it's the second most used combination around the world. So coming back to the points, like hybrid system has a lot of advantages, like they can use with the grid connected, they can use in half grid, and they can also use in special purpose modes. An off-grid hybrid means it can supply power to the rural regions in all aspects such as reliability, sustainability, and with environmental protection. So why we need this hybrid system in India? As we all know, India is one of the biggest country and has a lot of population. So it is very hard to connect grid to each and every corner of the country. So this hybrid system will be the permanent solution for the rural regions where the grid cannot be connected. So what is the purpose of this paper? So India has a lot of renewable potentials, but the problem is it is not utilized properly. So this paper shows like how to utilize the renewable energy potential and to provide an uninterrupted power supply to the specific community. And through this hybrid energy system, we can attract investors and we can provide extra employment opportunities to that specific community. So by providing employment opportunity, we can increase the revenue of each household in that community. By that, they can spend for their quality education, quality food, and for quality medical care. By this, we can uplift a society in that specific rural region. And also the purpose of this paper is to how to overcome the technical, economical, and other barriers in hybrid energy systems. So coming to the methodology, starting with the literature review, next to find the research questions of this topic, and to do a case study of a specific village in India. So this case study is about like what is the population, what is the renewable potential available in that specific village, and what is their background, what is the work they are doing, how much income they are having, and what is their electricity bill, and how much they can pay their electricity bill and everything. So after finding all these things, we can configure a system. So after configuring, we can develop a hybrid system model, and we can size each component of the system. For example, if we have a PV wind battery system, we should size each component. Like what is the capacity of PV, what is the capacity of wind, and what is the capacity of battery. So after sizing, we can simulate in some softwares or using some methods, and we can find the optimal solution to implement hybrid energy system. So talking about energy market in India. So India is a country which has a lot of capacity to produce electricity. Obviously, they are producing more electricity than it needs. But the problem is it lacks in sufficient transmission and distribution facility. So for this problem, the government of India is continuously working to expand renewable energy investment. And also they're providing a lot of subsidies to the investors and also to the common citizens. So as a citizen of India, I know they're providing a lot of subsidies, because if I want to install a PV panel in my house, the state and central government giving me 50% subsidy, which means if the overall cost is around like 1,000 euros, they're giving me 500 euros a subsidy. This motivates a lot of people to install renewables in their houses. And also in India, renewable hybrids will help for decarbonization, lowering energy cost, and also provide electricity for rural areas. Talking about decarbonization, you can see the pie chart on the right side. You can see that 53.1% of energy installation is from coal. This data is updated till March 31st, 2021. So in this, you can see 53.1% is from coal and only 22% is from renewables. This causes major carbon emissions. As I want to tell you that after America and China, India is the third country which is emitting a lot of carbon emissions. So this hybrid solutions in India will reduce the carbon factors, and also it will reduce the cost of energy. And also India is keep on trying to reduce the carbon emissions. So they also signed in the Paris Agreement, and they're planning to install 175 gigawatts of renewable energy before 2022. And I want to tell you like why I choose North India, specifically North India, because North India is a cluster of region where they have forests, deserts, mountains, rivers, and everything, different kinds of region. So it is for the government, it is very hard to connect grid to every part of the region. So hybrid energy system will be the proper solution for this kind of problems. So coming to hybrid energy systems. So in the left-hand side, you can see two schematics. On the top, you can see PV wind battery hybrid system. On the bottom, you can see wind diesel battery hybrid system. So in it is a simple schematics. It is a similar solution, similar schematic solution for this study also. So you can see PV wind battery is connected to the inverter, and it all connected to the common AC bus. And this will provide to the community. So these two systems are most widely used hybrid energy systems. So the problem is, though we find the energy potential in that specific area, and we can say that I'm going to implement a wind PV battery system, and we need to know what is the size of each components, because we have a certain demand. We know what we're going to install, but we need to know what is the capacity of each parameters for PV, how much wind, how much, and battery, how much. So to optimize this, we have some optimization techniques. So starting with the graphic construction method. So graphic construction method is, in this method, we develop a sizing curve between two parameters. For example, between PV and wind. So we develop this sizing curve through collecting wind speed data, solar irradiance data. But the problem in this method is we are not considering a solar slope angle, PV slope angle, and we're not considering the installation cost of the renewables. So this method will not give you optimal solution. So coming to the probabilistic approach. So probabilistic approach is a simple method, and it is very easy to execute. So this kind of method is also not approachable. So coming to iterative technique, it is a mathematical model. It gives you a best hybrid solution. And the problem is it increases the computing effort, but sometimes it will give you a less ideal solution. And next, artificial intelligence method. So this method will also give you the best ideal solution of hybrid model. So this method is approachable. So coming to multi-objective design, so two conflict parameters can be designed in this method, and it decreases the operation time and it gives you the best optimal solution. So according to the research articles and authors, they're suggesting iterative technique, artificial intelligence method, and multi-objective designs or the optimization technique we can use while developing a hybrid energy system. So coming to evaluation criteria, we have 4 major factors to evaluate while developing a hybrid energy system. So starting with the technological factor. So first we have a loss of power supply probability. So it is the ratio of total energy deficit to the total demand hours. So next, equivalent loss factor. So it is a total effective loss load hours to the total hours. So like this, we have various parameters to calculate while developing a hybrid energy system. So talk about like total energy loss in the technological factor. So for example, to estimate the excess generation of electricity when there is no demand. So when we have a PV, wind, and battery system, and we have a certain demand. So when a battery is full, and also you fulfilling the demand of the community, but still you have excess generation of electricity in your plant. So to calculate those kind of factors, we need these kind of mathematical models. So coming to the economic factor, while building a hybrid energy system, economic factor is also a factor that needs to be considered. So levelized cost of energy. So this levelized cost of energy should be low in your while developing a system, because if the LCO is too high, definitely the people will not purchase the electricity. So the project will goes on to failure. So what is levelized cost of energy? It is the average net present cost of electricity generation for generating a plant over its lifetime. So next, we have to consider capital required cost, long-term cost. Long-term cost is some of the initial installation, maintenance, operation, and replacement cost. So coming to net present value, it is one of the important factor for the investors, because if the NPV value comes in positive range, definitely the investors are going to invest on the project because it gives you the profit. If the NPV is a negative, yeah, the investors will have to work on that, and they have to make it as a positive value. So NPV is nothing but the current total value of the future stream of payment. So finally, we have to consider the annualized cost of system. So, and also the social acceptance and political acceptance is very important. So why social acceptance is very important? Because if you are placing a wind turbine near a community, it will produce a lot of noise pollution. So you have to create an awareness between the people, and you have to tell them what is the actual scenario, what will happen, and everything, or else it will create a chaos between the community. And obviously, political acceptance is also important. And finally,
2 minutes left. 2 minutes left, please.
Yeah, okay. So finally, the environmental factor. So one of the major reason to implement hybrid energy solution is to reduce the carbon emissions. So we also need to reduce the carbon emissions as much as possible. So some suggestions to implement HES. We should produce output power with high quality. In India, like even though some rural areas have electricity, but the quality of power is very low. So they're facing this problem really high. So we need to address this problem to very much. And we have to provide this electricity at reasonable rates, because already the people in rural areas, they doesn't have a lot of income. So if you give them at a high rate, definitely people will not buy it. And also try to construct less complex system, because in hybrid energy system, the load variation is too high. So there is a chance of entire system failure. So coming to the conclusion, so this paper is to electrify the rural villages by using the renewable potentials without any grid extension. And it will find you the optimum combination of hybrid energy system based on the technical, economical, and other factors. And also with different hybrid combinations, we're going to design 3 sub-designs, which are called as a basic supply, reliable supply, and uninterrupted supply. So thank you for your time, and I'm open for any questions.
Okay. Thank you very much for your presentation. due to the time limitation, I should move to the previous, speaker.
Yeah.
Okay, thank you so much. Have a nice day. Have a nice
Thank you.
day. Okay.
Have a nice day.
Thank you. Okay, Josie. Josie Rock, now it is time your turn.
Yeah.
You can
Hello.
continue. Okay, please switch off. Okay, excellent. You have switched off your camera, and you have just 10 minutes to complete. Okay.
Okay.
Please
So
try to focus on the main topic, and
yeah.
try to summarize, because we have some problems associated with the internet connection. Okay, please go ahead.
Okay. So in this study, like I was saying, we have been focused on the application of thermoelectric cooling, thermoelectric coolers acting as heat pumps incorporated in solar air heater to improve the heat collection of the solar air heater. So here we can see the two different designs. And on the left side, we have the conventional solar air heater that causes elevated heat losses because of the high temperature of the absorber plate. And on the right side, we can see that when we incorporate
we can see your presentation. We can see your presentation.
Okay.
We can see. No presentation is available on the screen.
Can you see it now?
Yes, now it is okay now.
Okay.
We can.
Okay. So on the left side on this slide, we have the conventional solar air heater with the absorber plate that reaches high temperatures and causes a lot of heat losses. But on the right side, we have our proposed system with integrated thermoelectric coolers that are powered by a PV module to pump heat from the absorber plate, cool it, and then improve the heat collection of the solar air heater. So we have here the overview of the system, where we can see the PV module producing electricity to power the TECs at the back of the absorber plate. And on the right side, we see the absorber plate, the TECs, and some heat sinks for effective heat dissipation. So 4 TECs were attached at the back of an absorber plate of dimension 430 mm square. Okay, here we have the energy flow diagram of the proposed system, where we can see the inlet, the input energy is the solar radiation to the thermal collector and the PV cells. So the PV cells produce electricity to power the heat pumps, and those heat pumps add up to the thermal energy, which is the output of our system. And some materials have been used for the construction of the two models of the subject of this study. So we have the cover plate, the casing, the absorber plate, and some insulation, and of course the thermoelectric modules and the PV module. And we can also see the arrangement of the TE modules at the back of the absorber plate. So here we have the experimental setup of the collectors that were experimented in Nsukka in Nigeria. And we had the two collectors, both the conventional solar air heater and the TE heat pumping solar air heater, experimented at the same location. And some parameters were measured, such as temperature at different points of the collector, air velocity, irradiance, and power output of the PV and power input to the TEC. So those data were fitted into some relation to determine the thermal energy production of the system by equation 1 and 2, and also the thermal energy efficiency of the system, equation 3 and 4. So our research and discussion are classified into two major categories: thermal profiles and thermal energy production. So when we look at the test conditions, we see that the two solar air heaters were experimented on 2 different days, and the solar radiation on those 2 different days were plotted on the left side of the slide, where we see that the conventional air heater benefited of solar radiation up to 900 watts per meter square, while the TE heat pumping solar heater benefited a solar radiation up to 700 watt per meter square, while the airflow was fairly the same during the two tests. So we compare here the thermal profiles, the temperature at the inlet and the temperature at the outlet, and we see that although the solar radiation was less in the TE heat pumping solar air heater, the temperature rise as seen on the right side was higher for the TE heat pumping solar air heater, reaching a value up to 33 degrees Celsius against 27 degrees Celsius in the conventional solar air heater. And this is an increase by 5 degrees Celsius. Also, when we look at the thermal energy production, the same pattern was observed, and we see that the cumulative heat gain of the solar air heater were compared, and we see that the TE heat pumping solar heater reached higher values up to 2.6 megajoule against 2.1 megajoule in the conventional solar air heater, which is an increase by approximately 22%, which is an important increment in the thermal energy production. So also the same result was obtained in terms of thermal energy efficiency, where we see that the cumulative thermal energy efficiency of the conventional solar air heater was up to 28% against 47% for the TE heat pumping solar air heater. This is a very important increment in the energy efficiency by virtue of the application of TE heat pumping. So now we then looked at the effect of the PV output on the performance of the system, and we found that according to the arrangement of the electrical arrangement of the TECs and the PV module shown on the left side, the power input to each TEC was fourth of the power output of the PV. So these could be shown on this graph, where we can see that if we increase the power output of the PV module, we could also increase the power input to the TEC, then increase the thermal energy output of the TECs. And by increasing the thermal energy output of the TECs, we could also improve the performance of the solar air heater. So conclusions. In this study, two different solar heaters have been compared, one with a conventional design and one with a TE heat pumping incorporated to the solar air heater. And we found that both thermal energy production and energy efficiency were higher in the TE heat pumping solar air heater than in the conventional solar air heater. And the increment were by 19% for the thermal energy production and up to 67% for the energy efficiency. So TE heat pumping could be a very nice means of improving the performance of solar thermal systems. And this was the aim of this study, and which was funded by the DAD, and we thank also the Association of Commonwealth University for enabling us to attend this conference. So thank you very much for your presentation.
Okay, thank you very much. Thank you very much. I am checking now the screen. There aren't any questions to you. Okay, thank you so much. Have a nice day. And
thank
now,
you too.
I would like to say a few words to summarize this session, in which there were a total of 6 presentations. This session mainly focused on geothermal energy related studies with 3 papers. 2 were related to how to assess the performance of geothermal power plants, and the last one related to how to produce energy from oil and gas wells. And the fourth one, the fourth one the fourth and fifth one were related to hybrid energy systems, from performance assessment to considering various factors in the design. Also the last one was related to thermoelectric heat pumping solar air heaters in terms of performance assessment, aspects. Okay, now it is time to close the session. I wish you all the best. Have a nice day. Okay, I am leaving.
Hello, everyone. So there was a last-minute change in the chair. I'm Associate Professor Mertgür. I'm the Vice Dean of the Istanbul Technical University Mechanical Faculty of Mechanical Engineering. So it's nice to be here. I hope there's no problem. Everyone can hear me.
Yeah, I can hear you. Hello.
So if everyone who is presenting could indicate who is presenting in the chat on the chat, that would be awesome. So we have many beautiful talks. So the first one is environmental impact assessment of novel photoelectrochemical reactor for hydrogen production. I think Ali Erdoğan Karaca is presenting because I'm seeing him.
Yes, Professor.
So you have 12 minutes plus 3 minutes Q&A. I'm looking forward to it.
Okay, and then I hope you can see my screen now.
Yes, I see the presentation.
Okay, so thank you, Professor, and dear listeners, thank you for attending this session. My name is Ali Erdoğan Karaca. I'm a PhD candidate of mechanical engineering working under the supervision of Professor Dr. Ibrahim Dinçer at Clean Energy Research Laboratories of Ontario Tech University. In this presentation, I will talk about one of our recent study titled as Environmental Impact Assessment of a Novel Photoelectrochemical Reactor for Hydrogen Production. I will begin my presentation with the introduction section. Then I will explain the motivation, background, and objectives of this study. I will continue with the system description and analysis. After this, I will present the results of the study, and I will conclude my presentation with a couple bullet points. As the share of renewable energy in the global energy mix increases, the intermittent characteristic of renewable resources brings some challenges in terms of reliability. In this regard, energy storage in the form of hydrogen as an energy carrier and fuel is promising. First, the energy density of hydrogen is much greater than all other energy storage mediums. Second, the stored energy in the form of hydrogen can easily be transported. And third, hydrogen can be readily converted into electricity by fuel cells and back again hydrogen by electrolyzers, which can be considered as a benchmark for the future energy infrastructure. There are many drivers that is motivating us to conduct this study, but I would like to summarize them in a couple bullet points. First, hydrogen is key for a green energy transition. However, conventional fossil fuel-based hydrogen production methods are pollutant. Renewable hydrogen production methods are important to decrease the environmental impact. Photoelectrochemical hydrogen production is promising because the process produces hydrogen from water by using solar energy as primary energy source. However, photoelectrochemical systems operate with low efficiencies. Advancement of these systems is important to commercialize this nature-friendly method while decreasing the carbon footprint of hydrogen and hydrogen-based energy systems. In this study, we are developing and analyzing a new photoelectrochemical cell for hydrogen production from solar energy. First, we evaluate the system performance through thermodynamic and electrochemical analysis. The results are considered in the environmental impact assessment of the PEC cell by using a life cycle assessment technique. We also comparatively evaluate the LCA results of the PEC cell with 3 different hydrogen production methods, namely natural gas steam reforming, wind-based PEM water electrolysis, and PV solar-based PEM water electrolysis. The main contributor to the LCA results will be discussed. So how the system works? Upon exposure to solar light, the semiconductor absorbs energy which is greater than its band gap energy from the light. This process excites electrons in the valence band into the conduction band. The excited electrons leave behind electron hole pair on the valence band. The photoexcited electrons and the electron hole pairs cause reduction and oxidation reactions of water. On the right side, the delta G, which is the Gibbs free energy, represents the energy required for the conversion of one molecule of water into hydrogen and oxygen. This corresponds to this energy corresponds to a potential difference of 1.23 volt per transferred electron for reversible conditions. However, the potential difference must be greater than the reversible one to compensate the potential voltage losses in actual conditions, or in another word, in irreversible conditions. In most cases, the photovoltage occurs as less than a required one. For instance, commonly used N-type semiconductor titanium dioxide can generate only 0.7 to 0.9 of the required photovoltage. Therefore, the process needs to be assisted with an external bias voltage. Depending on the source of applied external bias, photoelectrochemical hydrogen production can be performed in a total sustainable manner. The figure shows the PEC-based hydrogen production with the CAD modeling of the developed PEC reactor concept. The table on the right side shows the geometrical dimensions of the PEC cell. In the LCI analysis of the PEC cell, the required bias voltage is considered from a PV solar panel. A conic electrode geometry is selected to increase the photoactive electrode area and obtain a passive solar light tracking characteristic throughout daytime. The PEC cell comprises two surface coated conic electrodes as anode and cathode separated by a Nafion membrane. The sunlight penetrates the PEC cell from the cathode side, in which a P-type copper oxide semiconductor is utilized as a photocathode. On the dark side of the reactor, there is a titanium dioxide coated electrode. Base material of the electrodes on both sides of the reactor is stainless steel. These equations are from the electrochemical and efficiency analysis of the PEC cell. For the wavelength of 500 nanometer, the quantum efficiency is assumed as 20%. Energy and exergy efficiencies are calculated by considering hydrogen as a useful output from the system and bias voltage from an external source, which is from a PV solar panel in this case, and solar light as an energy input to the system. These figures represents the boundary of the LCA analysis of the hydrogen production methods. Materials and energy requirements are considered in the LCA. The CML baseline, which is developed by the leading university, is considered as the impact assessment method, and 1 kilogram of hydrogen production is defined as the functional unit of the LCA study. The EcoInvent database available in the CIMAPRO software is utilized to obtain the LCA data for material and energy inputs for the corresponding hydrogen production methods. This slide shows the material and operational parameters. On the top left side, the table shows the material used in the body of the PEC cell. On the top right side, the table presents the materials to build a 20 megawatt 10 water electrolyzer. Data in this table is obtained by scaling up a 1 megawatt 10 water electrolyzer presented by Rua et al. At the bottom left corner, the table presents the results from this electrochemical and thermodynamic analysis of the PEC cell. In this regard, hydrogen production rate is evaluated as 47.1 microgram per second, while operating an energy and exergy efficiencies of 6.3 and 6.38% respectively. Natural gas steam reforming is a major and commonly used hydrogen production process. CIMAPRO software database already includes a steam methane reforming hydrogen production plant. Therefore, it was not required to build the plant in the software. Data available in the software is utilized in the LCA study of the natural gas steam reforming. This figure shows the normalized LCA results of the hydrogen production methods obtained from CIMAPRO software. Environmental impacts of the hydrogen production systems are investigated in terms of abiotic depletion potential, global warming potential, ozone depletion potential, human toxicity potential, and acidification potential. And note that the functional unit of the LCA study, 1 kilogram of hydrogen production for each production processes. Abiotic depletion potential is the measure of the use of non-renewable natural resources. In an LCA study, this impact category considers the degradation of abiotic resources such as fossil fuels, minerals, and metals. Abiotic depletion potential of the natural gas steam reforming is evaluated as the lowest due to high production rates per kilogram of used materials in the system. On the other hand, the ADP of solar-based PEM water electrolysis is the highest. In the LCA network analysis, zinc mining operation for the photovoltaic panel manufacturing appears as the major contributor to the abiotic depletion potential of this hydrogen production. Acidification potential refers to releasing chemical compounds to air that may cause acid rains. The PEC-based hydrogen production process has the lowest environmental impact in terms of acidification potential, which is followed by wind-based PEM water electrolysis. Natural gas steam reforming has the highest environmental impact in terms of acidification potential. Sour gas burning in the sweetening process of natural gas is the major contributor to the acidification potential of this hydrogen production. The global warming potential was originally developed to compare the heat trapping ability of different greenhouse gases in the atmosphere relative to another gas. In this regard, carbon dioxide was chosen as a reference gas due to its long residence time in the atmosphere. In this study, global warming potential of the hydrogen production methods are evaluated on a time horizon of 100 years. PEC-based hydrogen production process has the lowest environmental impact by means of global warming potential. Natural gas steam reforming is the most pollutant hydrogen production process in terms of this impact category. Due to using significant amount of fossil fuel in the production, this method has a high environmental impact in terms of global warming potential. Human toxicity potential defines the potential damage of a unit of toxic chemical discharged to the environment on human health. Natural gas steam reforming has the lowest environmental impact in terms of human toxicity potential, that is followed by PEC-based water splitting. Wind-based PEM water electrolysis has the highest human toxicity potential. Sulfuric tailings from copper mine operation for the construction of wind turbines appears to be the major contributor to the human toxicity potential of this hydrogen production. Ozone depletion potential relative to CFC11 is a measure of how much a chemical compound released to the environment can damage the ozone layer. Due to low production rates, the PEC-based hydrogen production process has the highest ozone depletion potential. Nafion manufacturing is the major contributor to the ozone depletion potential of the PEC reactor. Wind-based PEM water electrolysis has the lowest ozone depletion potential among the evaluated methods. In this study, we comparatively evaluated the environmental impact of a newly developed photoelectrochemical cell for hydrogen production with the LCA techniques. The hydrogen production rate of the PEC cell is evaluated as 47.1 microgram per second, while performing energy and exergy efficiencies of 6.3 and 6.38% respectively. LCA results show that photoelectrochemical hydrogen production is a clean road that can be considered within the concept of a green hydrogen sector transition. And these are the sources we utilize in this presentation. And thank you for listening.
Thank you for the great presentation. So we have around 2.5 minutes for questions. I guess we can take one or two. Any questions? There are no hands up. Actually, I will ask a question then. So I always wonder, when you generate electricity from solar energy, actually, so the efficiency is quite low in all methodologies. So this means that you release a lot of heat, right?
Yes.
So how much is that an issue for the device that you designing? I mean, how much does it affect the design?
Actually, Professor, I can explain this one. Just a second, please. First of all, in these systems, Professor, we use semiconductors, And as a base material, there is no material that is like capable enough to like absorb photon energy. So why? Because the band gap energy of the semiconductors are not narrow enough to absorb energy from the photons. So what we do, we hybridize the surface of the electrodes with coating with other semiconductors. Some of them is good for because they have a narrow band gap energy, and that absorbs energy, a lot of energy from the solar. And some of them is provides stable characteristics in the aquatic solutions. By combining these two, the copper oxide and titanium dioxide, and coating the electrode surface, that helps us to utilize from the solar energy better. But however, the PEC cells, the main setback of this technology is the low energy density. According to US Energy Department, if this system catches 10% of solar to hydrogen efficiency, it can be commercialized. So that's the benchmark. Actually, but still there are still gaps in the literature. And from that point, the energy efficiency and exergy efficiencies of these systems can be increased. And the geometry of this study, and we are also investigating from different aspects to this the PEC cell concept. And the analysis shows that the geometry is also one of important parameters that can play a key role to increase the efficiency of this technology.
Okay, thank you for the great talk. I worked in the Joint Center for Artificial Photosynthesis in the 11th Workday National Lab. So it's actually, I'm quite interested in this technology in the past. So very interesting. Good luck. And I see it's very, very nice results. So congratulations.
Thank you. Thank you.
So let's move on with the next talk, which is also looks very good. So is Professor Adnan Mindilli presenting, or?
No, Melike is presenting.
Okay, so
okay.
So let me give an introduction. The next talk is the role of machine learning, which is very interesting, on metal hydride for hydrogen storage. As someone who is working computational, I'm very interested in that one. So let's see. Good luck. You can start.
Okay. Is my recording started? Okay, I think yes. Okay, thank you so much, Professor. Hello, everyone. Here talking Melike from the University of Balıkesir, and with Professor Mindilli, we conducted a study about how machine learning can actually take part on hydrogen storage studies.
Can I interrupt just shortly? Can you make it full screen? It would be easier for those who are
it's using. Not? Okay, here then. I'm sorry.
Oh, thank you. Sorry for interrupting.
Okay, with Professor Mindilli, we conducted a study about how machine learning can take part on hydrogen studies, especially in metal hydrides. So I will start the presentation with a quote. Nearly 30 years ago, the editor of Nature, John Maddox, said that it is impossible to predict the crystal solid structure based on their chemical composition. But nowadays, we all know that it is far from true. And moreover, predicting the structure of materials is one of the most important challenges in material science. And in the context of hydrogen storage in metal hydrides, machine learning is considered as one of the most promising strategy on this challenge. So this will be the main subject of our presentation. So I have 3 big headings. And at the end of the presentation, I will conclude up with 3 strategic points regarding this subject. Okay. Storing hydrogen is often considered as the bottleneck of the hydrogen revolution. And ideally, researchers are looking for a compact, safe, and cheap and efficient hydrogen storage. And generally, metal hydrides are considered safe materials, and they can work under mild conditions and they can produce with high volumetric densities. What is metal hydride? It's basically a metal reacting with hydrogen, which is forming metal hydride. So this is a reversible reaction. Also, hydrogen uptake and release can be easily controlled by changing the temperature and pressure. And you see a general representation in this graph. Here, by the hydrogen absorption or uptake is an exothermic, and the hydrogen release from the material is an endothermic reaction. So in more specific, metal hydrides formation can be classified into 3 categories. The first one is the elemental metal hydrides, which is pretty straightforward. And the second one is the intermetallic hydrides, which is an interesting and effective option. As you see, there are two metallic components, A and B. Here, A is a rare element, and it tends to form a stable hydride. But B is a transition metal, and that forms unstable hydrides. And the most common studied materials are AB, AB2, A2B, AB5, etc. Another interesting and promising materials for hydrogen storage application is the complex hydrides. In general, they present a wide variety of composition with alanides, borohydrides, and amides. Okay, among all these options, the choice of storage material ultimately will depend on the cost, the safety, and its performance, like energy density or reversibility, or their fast kinetics, or the heat of formation. So let's take a look in this table. The materials with an orange dot are the most promising candidates in the literature. As you see, these hydrides are excellent in terms of the hydrogen specific density because they are all more than 10%. But the hydrogen release kinetics are often slow. What I mean is, for instance, borohydride, their hydrogen release can take several hours, which is a great barrier. And the other thing is, for instance, the temperature of the hydrogen release. As you see, there is 720, 600 Celsius. So these can be considered very high temperatures. And I think the comparison will be much more easier here. And I want to take your attention with the little yellow dot here, which is the ultimate target set by Department of Energy for light vehicular application for cars. When we look at the promising materials that I showed in the previous slide, these materials, in terms of energy density, they are clustered around this target. But you can see that they are in red color, which means their reversibility is pretty poor. So we say the development is of new materials is critical. And here are some of the traditional methods right now in which fundamental thermodynamics equations are explicitly solved. But the problem is here, the problem here is the computations are huge, which they require long computational time, and they need really powerful computers. So to go beyond the current materials, machine learning has enabled us rapid predictions by using existing material data. And it is changing the classical paradigm of material simulation and computation. Okay, machine learning is a subset of artificial intelligence. It provides a faster and cheaper alternative to multi-scale modeling techniques also. They learn easily from the experience, from your data, and they are able to establish a cause and effect relationship between the variables in your data set. And recently we have seen that the deployment of machine learning in hydrogen storage has been done to do the predictions of the material structure. As you see, there are 3 types of machine learning: supervised, unsupervised, and reinforcement. In the context of hydrogen storage in solid state form, the most employed models are mainly supervised ones. Here, the algorithm has an idea of how the data works and how is the relationship between the inputs and outputs. And of course, here, the type of algorithm that you choose should be based on your data. I mean, how much data you have or what type of data you have. And it can also greatly change the predictivity capabilities in machine learning. Just to make more clarify, I would like to show a flow chart of a simple example here. Okay, first we have a data set. Here I used open source hydrogen storage materials database that I got from Department of Energy from Hyde Park. And there are 2,722 data points here. So you can see the distribution of the materials with this histogram. And among them, I did first pre-processed my data. What I did is I filtered only complex hydrides, which means AB types. And I selected 4 parameters just for example, which are pressure, temperature, heat of formation, and hydrogen storage capacity. And then I split my data into 2 sets, and 80% of is for the training purposes, and the 20% is for testing purpose. Also, you could have done with the 70-30 format. This is also acceptable. And then we move on to algorithm selection for machine learning. Okay, one of them is classification and the other is regression. In this example, I choose the classification algorithm and classified 3 out of the 4 variables. Okay, and after performing the training, in which the algorithm actually establishes a relationship between the input and the output, a predictive model is set up. And then the evaluation starts. And then the evaluation starts with the test set. I mean, in other words, we are asking the algorithm, what would you be predicted of the temperature if I give you this pressure, this hydrogen weight %, and this heat of formation? So if the assessment is successful, you can accept the predictive model. If it is not satisfying, then you can keep the training continue. So a simple machine learning can be set up by this way. And actually, no study has been conducted within the scope of our object with the other 2 methods. But just for an example, I can show the flow charts. And I think it's necessary to highlight that in supervised learning, there is no training here. The main goal is to find hidden structure in the data set by using clustering algorithms or by using artificial neural network. And the reinforcement on the other end is quite different because this technique is used only when you don't have data. If you have very small amount of data, reinforcement is good for you. And learning action is based on your feedback. What I mean is, okay, a prediction comes, you say good or bad or so-so. And based on your feedback, the agent or the machine needs to figure out which actions to take based on your feedback. Okay, I'm coming to 2 more slides I have, and I will be finishing up. Databases are very important to train machine learning models. So both good and bad examples are needed for the prediction accuracy, let's say. And there are 2 well-known open source databases, and they offer structural properties of metal hydrides. One is the Open Quantum Materials database, and the other is Hyde Park from Department of Energy that I used for my example. And you can find these data and more from these databases. And just for an example, I have shown the possible inputs and possible outputs in the table. But I would like to highlight one thing here, because the desired hydrogen storage properties are highly dependent on the final application. Okay, what I mean is, for instance, for automobile application, the gravimetric density is the most important factor. On the other hand, in stationary applications, high volumetric density is preferable because the weight is not the dominant factor that will affect the efficiency in your system. So therefore, the same inputs may not be valid for all cases. I just wanted to highlight this point. And in conclusion, we came up with 3 strategic points. The first one is the discovery of new stable and fast kinetic compounds is crucial to realize the hydrogen economy transition, and machine learning can make this transition faster. The second point is before conducting really expensive real experiments, actually machine learning can offer you a very low cost and in a very safe way to explore new metal hydrides. And the last one is machine learning can test numerous combination of metals and predicting their thermodynamic properties in a very short computational time. So these are the references we used, and thank you for your attention. And I will be very pleased to answer your questions.
Thank you for the interesting and nice presentation. Unfortunately, we have around a half minute left for Q&A, so maybe questions can be written through the chat. So right now, if anyone has a question, so we need to move on with the next one.
Okay, I'm sorry.
For a great presentation. So I think I have seen Sankar Sekar's video. So I suppose he is presenting, right? So the next talk is activated carbon decorated spherical titanium oxide nanoparticles for enhanced hydrogen production.
Yeah, good morning to all. I'm Dr. Shankar Sekhar, working as the assistant professor in Dongguk, South Korea. Today I'm going to present activated carbon decorated spherical titanium nanoparticle for enhanced hydrogen production. In the cases in day-to-day life, we are using the fossil fuels for a energy purpose. In the cases we normally using the petrol, diesel, everything. But in the cases, petrol, diesel emit a large quantity of carbon dioxide and other carbon emission product. Sir, can you hear me? Hello? Sir, can you hear me?
Yes, clearly. I can hear you clearly.
Okay, sir. So nowadays we are using the different kind of energy storage material and energy conversion technologies, such as like a supercapacitor battery and fuel cells for future transportation and power utilization. So in the cases, we can reduce the carbon dioxide emission and we can control the global challenges. So next, in the cases, we are looking forward for hydrogen generation. In these cases of hydrogen generation, we use 2 kind of methods. One is electrocatalysis, another one is the photocatalysis. Compared to electrocatalysis, photocatalysis is the easiest way to, we can separate the hydrogen from wastewater and sulfide containing wastewater. For some industrial wastewater also we can utilize this, and the separated hydrogen we can utilize for future energy storage application for vehicles and home utilization also. In this cases, the basic principle of semiconductor compared to all other material, semiconductor based photocatalysts are best for photocatalytic hydrogen production. In these cases, we have 3 types of process for generating of hydrogen energy. One is for charge separation of electron and holes from the photocatalytic semiconductor materials. Another one is we can change from the electron move from conduction valence band to conduction band. And other one is that we can add with the reduction oxidation process for separating the electron hole and generate the hydrogen from the wastewater. These are the basic mechanism of the principle for the semiconductor photocatalyst for hydrogen energy production. So in these cases, my work is we designed the TaO2 nanoparticle synthesis from normal Joule cell method, and we added with the activated carbon. It is derived from the biomass leaves. So we can mix it with the TaO2 with the activated carbon in the sonochemical process, and finally we make the TaO2 activated carbon nanocomposite. And we tested with the some physical characterization and microstructural characterization. In the cases of physical characterization, the pure TaO2 showing the anatized phase of TaO2 nanoparticle. When we make the composite, there is 2 peaks observed in the XRD pattern, that 002 peak and 100 peak. It is indicating the amorphous structure of activated carbon. So it's clear confirm the prepared material is composite material. So further we confirming through FTR the prepared pure material and composite material. In these cases of composite material, there is shift occur in the FTR spectra. So it's the activated carbon shifting the peak shifting of the pure material. So it enhances the charge transportation of the prepared material. So this is the microstructural characterization FESM image of the pure material and composite material. Pure material showing the interconnected spherical nanoparticle with average size of around 20 to 30 nanometer. When in the cases of adding with the activated carbon nanoflakes, it makes the composite structure. In the integrated structure with aggregated integrated nanoparticle will occur in the composite structure. So further we tested with the hydrogen production using photocatalysis method. In these cases, we are using the trapezoidal reactor for making the hydrogen production. We use different kind of concentration of sulfide and sulfite concentration. According to the sulfide concentration, 0.15 molarity, we observe the high hydrogen production capability around 400 milliliter per hour. In the cases we change the sulfide concentration, we observe 0.2 molarity, we get the high hydrogen production capability. And also we change the dosage levelage of prepared catalysis. We change the different catalyst dosage level. We observe 0.1 gram by liter. We observe the high specific hydrogen production capability around 400 milliliter by hour. So we check with the pure and composite material. Compared to pure material, composite material showing the high hydrogen production because of the synchronistic effect between the activated carbon nanoflakes and TaO2 nanoparticle. So we observe the high hydrogen production in this composite material. So this is the photocatalyst hydrogen mechanism. In these cases, we done the experiment in the open sunlight. So we get the light energy from the solution. So we separate our solution in the hydrogen equations. So it is summary of my present work. We prepared successfully in the TaO2 composite through Sol gel method, and activated carbon we added with the sonochemical process. So in these cases, this composite showing the aggregated spherical particle-like structure. Compared to pure material, the composite showing the high performance around 400 milliliter by hour. So this material is suitable for future hydrogen conversion applications. Thank you for your kind attention.
Thank you. Actually, we have now a lot of time for Q&A. So we have around 7 minutes. Please feel free to ask any questions. If there are no questions, I actually would like to ask one. So what is the next step now? Or is that confidential information in the lab?
So we are planning to produce in large scale industry. So we try to plan to the large scale industry. So we need for more capacity. Generally, in all over world, the got the 1.1% efficiency for hydrogen production. So we try to improve. Normally we are using the wastewater from industrial, so it contains the more sulfite ions. So we can easily separate the hydrogen from the wastewater. So it is India is the largest wastewater industry, so we can resolve this problem.
Thank you. That's very nice work. Very nice work. I'm actually not surprised that questions are not asked, because okay, it's all hydrogen and all look similar, but all the methodologies and what's presented is actually much different. It's very interesting, very interesting. I'm very excited actually that they made me the chair today.
Thank you, sir.
Are there any other questions? None? I think everyone is excited about their own presentation. It happens. So thank you again for the great contribution. So let's continue with the next one then. Actually, your presentation brought us back on schedule. That's actually great. So the next one. Okay, so it's the influence of biohydrogen production on ratio of generated acids and regulation of delta pH in E. coli during fermentation of mixed carbon sources at pH 7.5. Who is, okay.
I am Rankine Gevorkian. Do you hear me?
Welcome. I have a hard time pronunciation your name. Can you say it again?
Can you hear me?
Yes. Very clearly. So, okay, please, you can start with your presentation.
Thank you. I am Rankine Gevorkian from Armenia, Yerevan State University, Faculty of Biology. The topic of this research is influence of biohydrogen production on the ratio of generated acids and regulation of delta pH in Escherichia coli during fermentation of mixed carbon sources at pH 7.5. Nowadays, fossil fuel reserves are gradually decreasing, and renewable energy is going to be an essential source for power generation in the near future. Furthermore, its safety and ecology are also emphasized. And molecular hydrogen is suggested as an alternative source of energy, which is effective, renewable, ecologically clean, cheap, and can easily transported and distributed. There are many ways to produce molecular hydrogen, such as methane reforming, electrolysis, but they require high temperature and pressure, and consequently, they cannot be cheap. So the biological way and hydrogen generation from biomass is more effective way to produce hydrogen. Hydrogen is used in the refining and chemical industry, and it is used in fuel cell portable energy generators. One of the hydrogen producing bacteria is Escherichia coli, which is able to utilize the mixture of carbon sources such as glucose, glycerol, and formate. Different organic acids such as formate, lactate, acetate, and succinate, and ethanol as alcohol are generated during the fermentation as either products or byproducts. Escherichia coli produce hydrogen from formate via reversible membrane-bound for hydrogenases. Hydrogenases can operate in reverse mode depending on the fermentation substrate and its extracellular pH. Hydrogenase 3 with the formate dehydrogenase H and proteins encoding by Higg operon forms FHL1, a formate hydrogen lyase 1 complex, and a hydrogenase 4 with formate dehydrogenase H forms FHL2 complex. Hydrogenases form hydrogen cycle through the cell membrane. When one of the hydrogenases operates in the direction of the hydrogen generation and the other one in the direction of hydrogen uptake. Nowadays, the study of the utilization of mixed carbon sources is highlighted. It is up to date to find a substrate for different bacteria to make hydrogen production more affordable by a biological way. Especially, many researchers are focused on the conditions in which bacteria can produce hydrogen more and longer. It is important to investigate mixed carbon fermentation because there are many industrial and agricultural wastes which contain several substrates such as sugars, acids, and alcohols for utilization by bacteria. It is significant to reveal the fermentation processes in the case of the lack of enzymes involved in hydrogen production to understand the role of hydrogen in the formation of metabolic cycle. So the main purposes of this research is to investigate the role of hydrogen generation in Escherichia coli in the ratio of generated acids in delta pH regulation during the fermentation of mixed carbon sources at pH 7.5. Bacteria were grown under anaerobic conditions in highly buffered peptide medium with addition of glucose, glycerol, and formate as carbon sources. Escherichia coli wild type and mutant strain with defect of formate dehydrogenase H were used during this research. It was investigated generation of acids and oxidation reduction potential kinetics in Escherichia coli wild type and FDHF mutant cells at pH 7.5 during fermentation of glucose, glycerol, and formate. It was shown that externally added formate was utilized by wild type in the amount of 2 and 6 millimole during the lag phase of the bacterial group, but hydrogen generation was not determined. Formate can have impact on the appropriate enzymes, operants transcription, and FHL pathway synthesis. Hydrogen generation started from a 3 hour when bacterial cells started to utilize glucose. And one part of the synthesized formate was converted to hydrogen and carbon dioxide by the FHL complexes. And the second part was passed out by FOC-A or FOC-B formate channels and maintains relatively constant external formate concentration from 9 to 11 millimole till the moment when no glucose was not detected anymore. During the fermentation, NADH is required during the synthesis of ethanol and succinate. In the process of fermentation, the NADH from glycolysis is recycled back to NAD+, so that glycolysis is continuing. And this occurs through ethanol and succinate generation. That the amount of succinate produced is lower than ethanol. This is due to one ATP loss during the succinate production, which is not energetically efficient for fermenting cells. Ethanol generation from glycerol is higher than that from glucose. Glycerol generates more NADH during utilization reactions, which led to ethanol generation to balance cytoplasmic redox state. So the generation of acids and oxidation reduction potential kinetics were studied in a mutant strain also. And external formate was not absorbed by the mutant cells absent of formate dehydrogenase H during the lag phase of the group. The lack of hydrogen generation and formate absorption was described by the absence of FHL complexes, so the absence of formate neutralizing complexes. External formate concentration remained elevated up to 50 millimole during the fermentation, and high concentration of formate in the external medium is compensated by the low generation of acetate and lactate, but not succinate, which is aimed to regulate delta pH. This process by coupled to low generation of ethanol. In the case of the lack of the hydrogen generation, formate generation rate was higher, as the formate neutralizing complex was absent. The generation rate of a formate in a high value is compensated by a low generation rate of lactate, which is aimed to regulate delta pH. So during the next stage of our research, we investigated the variation of intracellular and extracellular pHs in E. coli wild type and FDHF mutant cells at pH 7.5 during fermentation of glucose, glycerol, and formate. The study of both biochemical and bioenergetical parameters is important to understand regulation mechanisms of fermentation and control biohydrogen production. Externally added formate when utilized by wild type cells decreased the value of intracellular pH by 0.1 units at 3 hours of the group compared to mutant strain. Meanwhile, delta pH maintained similar in both wild type and mutant strain. Due to hydrogen generation produced from a 3-hour internal formate was neutralized in wild type, whereas in FDHF, formate excreted out, which led to acidification of extracellular and intracellular pHs at 6 hours. This resulted in the vital perturbation of delta pH in FDHF mutant strain compared to wild type. True of the acid concentration variations, such as concentration of formate, lactate, and acetate, changes in the delta pH perturbation were decreased at 24 and 72 hours. So, taken together, it can be concluded that hydrogen generation has vital impact on the metabolic flux formation during fermentation of mixed carbon sources. Hydrogen production has a significant role in delta pH regulation. And the bacteria delta pH through variation of concentrations of the generated acids, such as formate, acetate, and lactate at pH 7.5. Thank you for your attention. If you have questions, I'm ready to answer.
Thank you for the presentation.
Thank you too.
Are there any questions? No questions? Not a single question has been asked so far. So, okay, then let's go on with the next speaker. Thank you very much for the nice presentation. So this shows again the variety, although everything is hydrogen related. Now we had, I guess you are from the biology department, right? So it's a biologist's contribution to the field. So this shows how extensive this field is. So thank you for this valuable contribution. And the next talk is, okay, design of future hydrogen supply chain, a multiple objective model for Turkey. So now it's supply chain, industrial engineering. I know. So who's presenting?
Mehmet.
Güler, right?
Yes, Mehmet Güler.
Yes.
Can you hear me?
Yes, I can hear you clearly.
Okay, Mert Hocam, thank you for the nice introduction. So as you said, well, now I'm from a very different discipline from industrial engineering. So that's really a different, let's say, session. So today I will talk about design of a future hydrogen supply chain, a multi-objective model for Turkey. This is a joint work with my colleagues, with Ebru Geçici and Ahmet Erdoğan. So my master and PhD students. Well, in fact, Ahmet was the one who would talk about this presentation today, but his brother is getting married, so he's a bit busy. And Ebru will defend her master thesis in half an hour, so she's a bit busy. So it's now my duty to talk, to make the talk today. Well, sorry. Okay. The thing is that, well, we all know that, well, the energy that we need is increasing day by day, okay? And the current sources like oil is being depleted. So moreover, even if it is not being depleted, okay, we have the problem of global warming, okay? So in fact, we see the current consequences as the wildfires in Turkey and in the Greece and in US. Sorry, I'm very sorry. Okay,
I completely understand. I have 2 small kids at home.
Okay, so my wife is a doctor. She's at the hospital. My babysitter has just quitted. I have 2 kids at home, so I'm sorry for this.
Same problem here. Believe me, same problem here.
Okay.
I completely understand. So I actually had to change. So I actually was going to take care of the kids today too. So I took a 1 hour. I asked my wife if she can give me 1 hour. So.
Oğlum şey al, ben şimdi konuşayım. Az sonra bitecek. Az sonra. Okay.
So I don't mind. If no one, I don't think that everyone else is minding, so we can just go on.
Okay, thank you. So we see the problem of global warming, where we see the current consequences, right, in the wildfires of in Turkey, Greece, and US, and so on and so forth. So the thing is, well, the researchers seek for alternative energy sources. Okay. Well, today I will talk about the supply chain model of hydrogen. So what do I mean by supply chain? Well, it's a very famous term that is used in industrial engineering and operations research. But I'm not sure whether you are familiar with this. So it means, well, in fact, the flow of the good and the information from the very beginning, from the raw material parts to the end, where it is delivered to the end users. Okay, so from the very beginning of the start of the production till it's delivered to the end users. So in fact, it just covers the obtaining of the raw material, its production, its transportation, then its storage, and also it's used by the end users. So what we are trying to do is to optimize this supply chain model. Okay, again, sorry for this. So what I'm trying to do is just to optimize the supply chain model. So what do I mean by optimizing? Okay. So the thing is, well, so we will take a snapshot of Turkey, okay, in 2050 in terms of the transportation sector. So in fact, this is a bit standard in the literatures. So people think that, well, the amount of cars will be just saturated during 2050, 30 years from now. At that saturated point, people are trying to optimize the supply chain. So what I mean by optimizing, well, it's finding the location and the type of the production facilities. It's finding the location and type of the storages, and then finding the flow between and within the regions or the grids, and I will speak it in a minute. And the methodology that we use is what we call a mixed integer programming. Again, this is a very famous tool that we use in operations research. So in mixed integer programming, what we have is we have some constraints, like, for example, the capacity of this production facility is this much, so you cannot exceed this. Or you say that, for example, in this place, you cannot open this kind of production facility, and so on and so forth. So these are the constraints. And you have an objective function. And the objective function is the thing that you're trying to optimize. Okay, so you have an objective function and you have some constraints, and you're trying to optimize that function with respect to that constraint. So what is the objective function? Well, there can be several objectives. The first one is the cost. So you may try to minimize the cost of the total supply chain, or the total locations, the flows in between, so that you minimize the cost. Another thing is, of course, you can minimize the carbon dioxide emission. Okay? And the third part is minimizing the risk. So the risk is, just think about just building a large facility into a location. So there is a risk associated with this. Or you just produce some hydrogen and you just transport it from that facility to other locations. And this trucks going from the factory to other cities and grids, well, that's a risk. Okay, so you may try to minimize this risk. Well, the thing is that, so in this research, what we're trying to do is just to unify these three objectives, because the general thing is, if you have several objectives like this, they are generally conflicting each other. Okay, and the thing is, you should just somehow unify them. So there are several ways that I will talk about, two of them, one of which we just use in this research. One of them is, for example, you say, well, 1 unit of emitting carbon dioxide is equal to, for example, $2. So you just define the carbon dioxide emission in terms of dollars, and you just add it to the original cost part. Okay, just this part, right? And again, you can define the risk. So 1 unit of risk is equal to, I don't know, for example, $15, and add this to this cost. So what you have is all units are same. this was dollar. You just convert these two into dollars. So what you try to do is just minimize these dollars. But as you might guess, well, this is very hard. Just finding the dollar equivalent of carbon dioxide emission or risk. In fact, risk is a bit tricky because there are very different ways of defining risk. In fact, that's the tricky part. That's one part that we are still working on it, because just building a factory, a smaller factory, well, does it have a smaller risk? Or if you increase the amount of production in a factory, does it increase the risk or not? These are some questions which are not very well answered in the literature. So in fact, we are searching on this as well. Okay, so this is the setting. We have Turkey. So people from Turkey, you know that this is the map of Turkey. So we have several grids. Okay, so by grids, I mean, for example, Istanbul is a grid. Okay, this part is a grid. This part is a grid. Antalya is a grid. But for example, here, as you see, this yellow part, this is a grid as well. So what we do is, since we are working on the transportation sector, we just merge the cities that are next to each other until the threshold. I'm not sure whether what was the threshold, but it's something like 1 million cars, or I'm not sure, 500 cars, 500,000 cars. I have 33 grids and 4 optimization scenarios. So one scenario is just minimize the cost. The second one is minimize the carbon emission, and the third one is minimize the risk, and the fourth one is the multi-objective part, where we use the absolute constraint method. So this method is a little bit different than the one where you define the carbon dioxide emission and the risk in terms of dollars. What you do is, so you minimize the cost. Okay, you said that, well, minimize cost, subject to, you say that, well, okay, sorry. And you say that, well, I want the carbon dioxide, the maximum level of carbon dioxide to be, I'm just making it up, 1 million meter cube, okay, something like this. So you put upper bounds to the other objectives. You put an upper bound to the risk, you put an upper bound to the carbon dioxide, and then minimize the other objective, which is the cost. That's how we do in this research. So as I said, well, risk is a bit tricky. We just define it in a way that we see from the literature, but it turns out that, well, its behavior is very similar to the part where we minimize the carbon dioxide emission. So it turns out that, well, when you try to minimize the cost only, don't look at the carbon or risk or any other thing, okay, you have 10 large facilities, the steam methane reforming, and 6 small, let's say, facilities. And you open that in only 9 grids, and the remaining 24 grids, they don't have any production plans. So how you deliver them? You just deliver them using transportation, right? And the degree of localization here turns out to be 27%. And we just measured it by calculating how many of the required hydrogen is supplied by the facilities that are in that grid. That's the amount of localization. And for carbon and risk, it turns out that, well, if you try to minimize carbon and risk, you should open as much as facilities that you can in each grid. That is because the model tries to minimize the transportation within and between the grids, okay? Because transportation has a great risk and carbon dioxide emission within its structure. So the model tries to minimize it. So we see that, well, there is 2 different ends. The first end is, well, this is a central solution where you open very large facilities and distribute from these facilities. And the other one is a local one, okay, where you open facilities, small facilities at each part of the grids, at each grid and each different part of the grids. And in the multi-objective case, where you put a limit on the carbon dioxide and the risk, carbon dioxide emission and the risk levels, it turns out that, well, this is something in between, okay? So you open 5 large plants and 83 small plants, where the degree of localization is now 52%, okay? So this is a balance in between, where you have, where you minimize the cost and minimize the carbon and risk as well. So I will click. So this shows, well, the amount of cost in scenario 1, in scenario 2 and scenario 3. As you see, this one minimizes the cost, but in carbon emission and risk, it doesn't take care of the cost. So you have a large amount of cost in these models. Similarly here, this one minimizes the carbon emission. As I said, it has a similar structure with the risk. Hence, it also minimizes the risk as well. But this model doesn't take care of the risk and the carbon emissions. So the carbon emission is large here, which is 30% when you compare it with this one. And here the risk is 10% higher than the, this part, okay? And this is the multi-objective case where we try to minimize all of them, okay? So the cost is $14 million per day. So it is 60% greater than the first scenario, okay? When you look at the carbon emission, it's 50% larger than the, okay, so this is my, okay. 50% larger than the risk scenario where you minimize the risk. And this one just increases 3% from the scenario where you minimize the risk. So as you see, again, this scenario just is a balance between the cost and the carbon emission and the risk. Now I'm finalizing, well, this is my conclusion. So as I said, we just work for the supply chain, the hydrogen supply chain structure for Turkey, where we try to minimize the cost, carbon emission, and the risk. And it turns out that, well, if you minimize the risk, well, it has a pretty much centralized solution. When you minimize the emission, carbon dioxide emission and risk, well, it has a decentralized solution. It turns out that, well, you try to minimize all of them. We have a semi-decentralized structure. Okay, thank you for listening and sorry for 2 small kids. I hope you enjoy my talk.
Thank you, Mehmet Hocam, for the nice presentation. So as we see now, it was from an industrial engineering perspective. Actually, I just frequently came across how actually important this kind of design is for the Turkish strategy, or I guess any country's strategy regarding energy efficiency and strategies. Are there any questions so far? We maybe have 1 minute. A quick question? No questions? Okay, Mehmet Hocam, thank you again for the presentation.
Thank you, Mehmet Hocam.
And this brings us to the final presentation, which is which is electrospinning is a powerful tool for the design of carbon nanofiber towards hydrogen energy systems by Aysel Kantürk Figen. Welcome.
Okay, thank you very much, Professor Gür. I am from Yıldız Teknik University Chemical Engineering Department, and today I want to talk about, I want to introduce the facility techniques as electrospinning for designing carbon nanofibers towards hydrogen energy system. Now you can see my outline. First of all, I want to introduce the electrospinning techniques. Then I will talk about its fundamentals and theoretical background. I want to share some examples of carbon nanofibers using hydrogen energy reported in literature. Then I want going to present my preliminary results, which is about carbon nanofibers production performed in my laboratory. Finally, I will finish my presentation with our going on studies. With increasing interest in nanotechnology application in energy, electrospinning has become a useful technique for designing nano-sized fibers for energy storage, conversion, and also production. It has been used in technological areas such as tissue repairing, wood dressing, biosensors, membrane applications, drug delivery system, and enzyme immobilization for a long time. And nowadays, these techniques applied for fabrication of face masks for personal protective against COVID-19 also. Generally, in this technique, electrospinning has been using an electric charge jet of polymer solution to produce nanofibers, and these fibers can be fabricated with various morphologies and structures which can be easily controlled by altering the electrospinning processes. So that electrospinning technology prefer to fabrication also functional polymeric nanofiber composites which can be utilized and used in hydrogen energy application. Now let's take a closer look at the fibers. Fibers in the form of continuous filaments and alien objects are found in nature also. As you can see, spider webs and silk filaments can be given remarkable examples of natural fibers. Researchers prefer the electrospinning for design the aligned, randomly oriented nanofibers or core shell structure nanofibers with diameters down to nanometer scale. Also, synthesized electrospin fibers shows the unique properties which was very important for using in hydrogen storage or production. Electrospin fibers have unique properties such as high surface area, low density, smaller and tunable pore size distribution, and also porosity. Now you can see the basic setup of electrospinning procedure. This apparatus consists of four parts: injection pump, spinneret, nozzle, high voltage power supply, and the collector. After the preparation of polymer solution at optimum conditions such as concentration or viscosity, injection pump used to pump the polymer solution, the spinneret and nozzle part. Then when we apply the high voltage, fibers start to form, and we can collect them from the collector easily. The main issue here is that if you wanted to obtain a uniform, smooth, or beadless fibers with desired unique properties, and functionality and quality, you have to adjust and optimize the parameters such as solution parameter, processing parameters, and environmental conditions. For obtaining a spinnable solution, the molecular weight of the polymer is the most important parameter. It also affects the flammability and the conductivity of the polymer solution. Researchers showed that and reported that at low molecular weight of polymer, when you obtained beads instead of fibers. And especially, more importantly, if you want to get qualified fibers, concentration of the polymer solution should be arranged at the optimum level. And also electrospinning process, including apply voltage, distance, and the solution fit rate, also affect the quality of the fibers. Besides these parameters, humidity, temperature, and also aerial setup medium have effect on fibers characteristics. So special cabinets are designed to minimize these effects. Carbon nanofibers and their hybrids are promising nanostructure carbonous materials, nanoscale components with different dimensions or morphologies, such as nanoparticles, nanoroots, nanowires, nanotubes, and nanosheets can be easily introduced into polymer solution, and after the spinning procedure, you can obtain the fiber nanocomposites which contains the carbon nanofibers or the other integrates. Today, most of carbon nanofibers are made from polyalkylnitrile polymer, and after the electrospinning, you have to proceed thermal treatment to convert the polymer structure to carbon nanofiber network. We prefer to use PAN in electrospinning solution because of it contains large carbon, and after the thermal treatment, it maintained its ladder-like structure after the thermal treatment. Because of their excellent electrical conductivities, large surface area, and also chemical stability, which is important for the processes, they can play multifunctional roles in energy-related technologies or applications such as fuel cells, ion batteries, solar cells, hybrid solar cells, supercapacitors. Related my project, carbon nanofibers can be designed, used as a catalyst in hydrogen production or a storage medium for hydrogen. I want to share some examples of carbon nanofibers reported in literature. As you can see, they found a very a large area, useful area in energy application. Electrospoon carbon nanofibers can be designed as a membrane for direct methanol fuel cell application, or can be fabricated as a catalyst for enhance the hydrogen storage capability of, for example, metal hydrides. Or can be used as a hydrogen absorption medium, and also can be fabricated as a network for efficient hydrogen evolution. And in this process, you can load different type of active metal to be transferred them to active and reusable catalyst. Now I want to give you information of my preliminary results. As you say, Department of Energy underlined that boron materials, boron-based materials or boron fuels such as sodium borhydride or ammonium borane are promising hydrogen storage material for fuel cell applications or onboard applications. Due to their high storage content in this project, it is aimed to develop efficient and reusable carbon fiber-based catalysts to realize the efficient and repeat hydrogen released through to hydrolysis reaction from boron fuels. Therefore, in my laboratory, we produced carbon nanofibers using electrospinning method following the thermal treatment. In this study, we preferred, within the scope of experimental studies, first two different solutions were preferred, PAN containing and graphene dope PAN containing. After the preparation of the polymer solution, we focus on the optimization of the spinning parameter. As I mentioned before, this is the main issue in this process. If you want to produce the randomly, homogeneously bitless nanofibers, you have to optimize this process. And finally, we performed some analysis to check the morphology of the fibers, and we can see the optimization results of fiber production. In our study, our optimized spinning conditions were determined as 17 kilowatt applied voltage, 2.2 centimeter per hour flow rate, and also 17 centimeter distance between collector and nozzle. And now you can see the digital image of nanofiber and carbon nanofiber, which produced after spinning and also thermal treatment. When PAN solution is spun, white PAN fibers is obtained. When we doped with graphene, there is no any change in this color. We can easily say that we can homogeneously disperse to graphene into a polymer solution. After the thermal treatment, it has a black colored fibers, which is unique for the carbon fibers. And we can say that after the thermal treatment, it retains their structure so that our parameters is very useful, right or useful parameters to obtain nanofibers. Now I only I can only share the same images of carbon nanofiber and graphene doped nanofiber. And as you can see, randomly non-woven carbon nanofibers were successfully fabricated under our optimized electrospinning conditions. After the thermal treatment, they preserve their fiber structure. We also measured the diameter of the fibers. After the spinning procedure, PAN fibers obtained under 400 nanometers. After the thermal treatment, we obtained the nanofibers diameters at 100 below. When we add graphene into polymer solutions, the graphene additives increase the viscosity of electrospinning solution, so we obtained the higher diameter of carbon nanofibers, about 150 nanometer. As you can see by this study, we provide randomly non-woven morphology carbon fibers, which be very benefit future application in hydrogen energy system, also in hydrogen storage and hydrogen production. Now this is a going on project when we are trying to loading the active metal in this carbon structure to be used as a catalyst in hydrolysis reaction of boron based fuels to produce hydrogen in a repeat and efficiency way. Also, we have to, of course, we perform the catalytic activity test, and also this is a catalytic reusability is the main parameter for using the catalyst also in industrial application. As a last step of our study, we aim to test the catalytic reusability. Here's our reference used in this presentation. Thank you very much for your attention. Also, I want to thank the Turkish Academy of Science to support this project. Thank you. Thank you very much.
Aysel Hocam, thank you for the nice presentation and congratulations for the award.
Thank you very much.
For your recent award. So we have time for questions. If there are any questions.
I will be happy to answer them.
I guess not. So we finish the complete section without any questions. So interestingly, actually, I'm right now in the chemical engineering department because my wife is a faculty member here.
Okay.
So as one chemical engineer, I guess the chemical engineering department right now. So I think there was one speaker for which we didn't give time for for Q&A. Let me also ask that one. It was the second talk. Are there any questions regarding any talk? We have around 5 minutes left. The attendees, any questions? None? For example, they presented the role of machine learning on metal hydrate for hydrogen storage. Didn't have time for a Q&A on that one. I guess not. Okay, that concludes then the session. So I thank all speakers for their great presentations. I hope to meet all of you in person one day soon. It's hard with all this pandemic going on. So I wish all of you a nice day.
I wish to. Thank you, Mert Hocam. Have a nice day. Thank you.
Dear participants, welcome to the invited session 4. My name is Can Özgür Çolpan. I'm from Mechanical Engineering Department of 9 Eylül University, and it's my privilege to chair this session. In this session, we have 3 distinguished speakers. Firstly, I would like to start with Dr. Demirci. Dr. Demirci received his Bachelor of Science degree in chemistry in 1997 from the University of Strasbourg in France. He received his Master of Science in Physics and Chemistry of Molecular and Macromolecular Materials in 1999, and his PhD in Physical Chemistry with a specialization in heterogeneous catalysis in 2002 from the same department. In 2007, Dr. Demirci obtained a permanent position of Associate Professor in Materials Chemistry at the University of Lyon in France. In 2011, he transferred to the University of Montpellier too as Associate Professor in Materials Chemistry. Now, he is a professor at the University of Montpellier since September 2015, and he works on inorganic chemistry, materials for energy. His research interests are boron chemistry, hydrogen storage through boron-containing materials, metal catalysis, and boron-based materials for other applications. Dr. Demirci has co-authored and published more than 150 articles in peer-reviewed international journals, and he has written several book chapters, books, and edited many issues of international scientific journals. And it's my privilege to give the floor to Dr. Demirci now. Your microphone is off at the moment.
Thank you. Thank you for this kind of introduction. So I'm gonna try to share my screen. Could you see my screen?
Yes, we can.
Okay, that's good. So before starting, I would like also to thank the organizer and especially Professor Dinçer for giving me this opportunity to give an overview of our activity on boron materials and especially boron materials for carrying and storing hydrogen. And before starting about science, I would like to give you a few words about the hydrogen energy context in France. Maybe you know that less than 1 year ago, in September 2020, the Ministry of Ecological Transition, as well as the Ministry of the Economy, have announced 7 billion euros to be invested in the hydrogen economy by 2030 in France, with 3 priorities. First, developing electrolysis in industry. This means more than 50% of this amount of money. Priority 2, it is developing the hydrogen mobility for professionals. In fact, high-duty vehicles like trucks, and this is 27% of the investment. And there is a priority 3 that is of interest to us. There is a support to research and development, as well as innovation and training. And it represents about 20%. It means 650 million euros by 2023, and there will be an additional amount for the last years between 2024 and 2030. I am involved in one of the work group, and especially we are preparing a proposal entitled Solid about solid state hydrogen storage. The idea is to gather the manpower between CNRS and CEA, which are 2 research institutions in France. The second one being more dedicated to atomic energy, but within the last years, we have started to work on renewable energies. And our objectives is to get a part of the 24 million euros dedicated to hydrogen storage. And this means that we have prepared a proposal. We have good feedback, and now we are working on the proposal, and we are quite optimistic to start the project in fall 2021, with recruitment starting in September 2022, especially for the PhD students. Now I would like to talk about boron-based materials, and as an introduction, I would like to state that we work on compounds that are in fact old. Here you have some pictures about famous scientists having who worked on boron-based materials within the 19th century, preparatory distillation that helped to progress fastly, known for sodium borohydride, but some other compounds also, like ammonia borane, even though his attempt failed at that time. And Professor Sheldon Shore, who invented or discovered ammonia borane, but also the dihydrogen bonds that drive the solid state of this kind of amine borane compounds. I have also to mention Professor Brown, Professor Perry, and so on. There are so many scientists who contributed in these boron-based materials and involving boron chemistry in the 19th century. So nowadays, I mean, over the past 20 years, we have, I would say, just rediscovered these old compounds, starting from sodium borohydride. You well know the Millennium Sail prototypes, which is a hydrogen on-demand system for producing hydrogen to provide half of the hydrogen. There were some prototypes here, 2 vehicles you can see, but nowadays you know that Millennium Sail has bankrupt and this project is now over. I have also to mention the borohydrides, the metal borohydrides here, just as do you hear me? Because I think that
yes, your connection went off.
Okay, sorry. I will share my screen. Sorry. I think I was on this slide when it stopped. Do you confirm? Sorry.
Yes.
So there are many borohydrides that have been discovered over the past 2 decades. I can cite Professor. That's okay.
Yes,
okay.
There's no problem.
I can cite Professor Jensen. I can cite from Denmark. I can cite Professor Filinchuk from Belgium. And you can see many borohydrides that can dehydrogenate at different temperatures. For example, we can cite lithium borohydride at 660 Kelvin, or the strontium one at 650 Kelvin. So which are temperatures that are high for the application. But there are metal borohydride like the iron one that dehydrogenate at 273 Kelvin or 0 degrees Celsius. And there are also many other bimetallic ones. Other examples of old compounds that have been discovered, I mentioned ammonia borane, but there are also the amidoborane derivatives. The sodium and the lithium amidoboranes were discovered before, but now we have a series of monometallic, bimetallic amidoboranes. Here you have some examples, the calcium one, the strontium one, the rubidium one, and so on. But all of them have been investigated for the hydrogen storage capacities, but mainly for material chemistry, for crystallography, because the most promising amidoboranes are the lithium and the sodium one. I can mention also hydrazine borane, where the hydrazine group substitute the ammonia group of ammonia borane and some derivatives. This was, in fact, the idea was to mimic what was done with ammonia borane and producing metal amidoboranes for ammonia borane and metal hydrazine-doboranes for hydrazine borane. And a few other examples. Here you have ethylenediamine borane. As a first example, it has been rediscovered recently by Professor Zhang et al. In Angevin 2021, where we show that it's possible to recover at room condition to 6 hydrogen. You have also a BN-based methyl pentane, which is able to dehydrogenate at 50-80 degrees C with a catalyst 6 equivalent of hydrogen. So there are many examples that have been discovered over the past 2 decades. All of them are hydrogen carriers, and we can discuss about them in 3 categories: the adsorbents, especially for the boron nitride one, the complex hydrides. The metal borohydrides are examples of complex hydrides, and chemical hydrogen. I mean ammonia borane and sodium borohydride, because in that case, hydrogen storage is not reversible. And it is important to stress on that point. With adsorbent, it is expected that the hydrogen storage is reversible, so you can put hydrogen to store and recover hydrogen by decreasing, for example, the pressure. Boron nitride-based porous materials are examples of adsorbents. I'm going to talk about that. For the complex hydride, we are the monobimetallic borohydrides. We have not spent too much time on this compound, so I'm not going to speak about these compounds, but I have shown in the introduction several examples. And the BNH material storage materials. And in that case, as you can see, this, as I am going to show you, the storage is not reversible, just recyclable. So let's start with boron nitride. So about boron nitride in the literature, it is interesting to make some comments about what have been published so far. Here, this is a table that summarizes the hydrogen uptake capacities of this compound. So you can see that the values, the storage capacities, gravimetric hydrogen storage capacities vary from about 2 up to 5.6 weight per cent at 20-25 degrees C under pressure of 30 to 100 bars of hydrogen. This is quite high. This is very interesting. This is the main problem with this kind of materials. Chemisorbing means that the hydrogen absorption is too strong, and the release of this hydrogen, of most of this hydrogen, it occurs at around 300 degrees C. However, despite these very interesting results, attractive results, there are very few reports when we compare to the literature dedicated to, for example, MOFs, with very good performance nowadays, and this is quite surprising. Regarding boron nitride in the literature, there are, on the other hand, many papers dealing with computational studies. These computational studies stress on 4 improvement ways. The first one is to improve the textural properties of BN. The idea is to make BN porous to get more defects, and these defects may help in storing hydrogen. A second aspect to improve the storage capacity will be to substitute boron and or nitrogen by oxygen, carbon, and oxygen. Here on the bottom of the slide on the left, you can see that the binding energy of hydrogen changes while adding some other elements than boron and nitrogen, oxygen and carbon. And we may be able to tune the storage capacity of hydrogen of this boron nitride based material. A third improvement will be the functionalization by lithium, titanium, and so forth. And this may help to dissociate hydrogen and store hydrogen on BN. And a last improvement could be to focus on 2D boron nitride, 2-dimensional boron nitride. And the chart at the right, show that if we are able to increase the interlayer spacing of this 2D boron nitride, it will be possible to store more hydrogen, even at 25 degrees, up to 2.8 weight per cent of hydrogen. So what we have done is we have started a work focusing on carbon-doped boron nitride. This is a project called Reversible and funded by the French ANR. The idea was to develop amine boron adducts to be used as surfactant to nanosize ammonia borane, so to get nanoparticles of ammonia borane, as you can see here by the SEM image. And then we pyrolyze these nanoparticles to get porous carbon-doped boron nitride. I have given you a summary of one of our last achievements. So we are able to get porous boron nitride with a specific surface area of 500 square meter per gram with 2 weight per cent of carbon. And our analysis by XPS, for example, shows that we have a carbon that substitutes boron and nitrogen and not 2 phases, like we can see sometimes, boron nitride on the one hand and graphitic carbon on the other hand. So in our case, it is a carbon-doped BN. The surface of the micropores is quite high with 270 square meter per gram. The pore volume is given, but unfortunately, our BN-based material do not store hydrogen at 30 degrees C and under 100 bars of hydrogen. I would like also to mention another recent result from another group, from Wen and Goldberg, as you can see here, because their result is more striking than ours. They worked on BN microsponge, in fact, doped with oxygen and carbon with both of these elements. Here we have some SEM images that I recovered from their paper. We are able to get specific surface areas up to 1,200 square meter per gram, which is quite high. And you can see that the storage capacities, depending on the specific surface area, are quite high, close to 2.5 weight%. But the problem is that this minus 196 degrees C and not at room conditions. So we are quite puzzled. So we are wondering if BN is still, so it is really promising for hydrogen at room conditions. Well, anyway, our works help us to prepare a series of nanostructures of ammonia brine. You can see some SEM images here. We are not able, we can heat treat them to get boron nitride. None of our boron nitride is able to store hydrogen at room conditions. It is, on the other hand, able to store carbon dioxide at interesting capacities. But the problem is that, in our opinion, we are more and more pessimistic with boron nitride for hydrogen in room condition, and we are wondering if the results published in the 2000s were so rigorous in terms of the storage capacity that have been published. Now I would like to talk about sodium borohydride quite rapidly, in fact. So sodium borohydride is well known because there are a lot of works on this compound since the late 1990s. So the black arrow shows the dehydrogenation process, which is the hydrolysis process of sodium borohydride in the presence of catalyst. And then in colors, you can see that because this is the main challenge with this reaction is to recycle the product in sodium tetrahydroxyborate into back sodium borohydride. So the red arrows shows the Braun-Schlesinger process, which is currently used for producing sodium borohydride that could be adapted to recycle the product. And the other paths shows alternative recycling paths using magnesium hydride, carbon and hydrogen, methane, and so on, and also in blue, an electrochemical process. All of these processes have been developed. They are, however, costly. There are some issues that have to be solved. But the problem is that when we focus on that reaction, which is able to works well at 20 degrees C and giving high storage capacities, most of the works have focused on the accelerator. The storage capacity, while optimizing the amount of sodium borohydride in water, is not well optimized yet. The generated hydrogen is not pure, and this is not well mentioned in the literature. And the broad product, there are some ways to recycle it as shown previously, but the processes are not cost effective and there are still works to be done on that way. In fact, we have missed the target for scale up. It's not too late in my opinion. And since 2-3 years, we are working on scaling up. We have already constructed one demonstrator that works well. We are able to produce 100 liters of hydrogen in a short time to feed a fuel cell, a 200-watt fuel cell. And now we are working on a second prototype with an industrial collaborator. In fact, we have finished the project. The first project with this industrial collaborator has stopped because of issues I'm going to mention right now. It was issues we were not expecting when we started this work, because we were more focused on lab scale devices and not in prototypes. And now we are discussing with them for another application we missed over the past 10 years. So I would like I'm not going to give you some results. I will list you our key learnings about these collaborations and this prototyping. The thing is that you have to forget all of the data you have collected at the lab scale. The hydrogen generation rates, the conversion, the temperature, and so on. You cannot use this data when you scale up the system. While scaling up, everything changes, the rates, the conversion, the temperature, and so on. The borax precipitation that you cannot see when you work at 100 milligram scale occurs when you work at 10, 40, 100 gram scale. This is a big problem because borates will precipitate, and also you can find it in the piping because of the exothermicity of the reaction. I will talk about that once more later. And this hydrogen is thus not pure because of humidity, and this humidity, this moisture, carries borates and also sodium cations. In fact, it is quite difficult to work with a powdery catalyst. Working with 100 milligram of sodium borohydride, 5 milligram of a catalyst is quite easy. But working with 100 gram of sodium borohydride and, for example, 5 gram of catalyst is quite tough to recover and to separate after that. So I cannot imagine how we can ensure using a powdery catalyst when this technology will be deployed. And the last point is the exothermicity. So with about 40 gram of sodium borohydride, this means 250 kilojoule that will be released. And this is a big issue. I will show you later. I would like to mention 2 key articles. I think that it is important to read and reread and to assimilate to better understand the problems. One is from Boring Europe. We worked on a device. It was the Aeropack hydrogen generator from Horizon Fuel Cell, and they used it for unmanned aerial vehicle. We observed 2 things. The borate precipitate, as I told you, and they accumulate. From a technological point of view, washing after each use is not possible. And the second problem is the decrease of the activity of the catalyst, which require maintenance after 8 to 10 hours of operation, which is not feasible from a customer point of view. So what I would like to say is that these issues have not been solved since 2007, the year when this paper was published, and we observed these issues while working on our 2 prototypes. I will also to mention a recent paper from Ariel University, Israel. The device is really interesting. I like the design. I like the idea. You can see that the idea is to use the water and catalyst mixture to pump into the sodium borohydride compartment and then recover hydrogen. And the fuel channel is mixed to water catalyst mixture, and this can be reused. This is very interesting because we are able to get a flow rate of hydrogen between 200 and 600 using some electronic devices to control the flow. But the main issue is the temperature. As you can see with the orange curve, the temperature reaches 6 degrees C, from about 25 to 60 degrees C, for 40 to 400 to 500 milliliter hydrogen per minute. And reaching this temperature is quite high. And in our case, so I cannot show you the results because this is quite confidential because of the collaboration with the industrial partner. We reached almost 85 degrees C while producing the hydrogen. And given that our technology is dedicated to be used by worker, and he will have to take in his hands the device. It is not, we cannot imagine that reaching this so high temperatures could be managed by this kind of workers. So this is a big issue, and managing the heat while hydrogen is produced is really important in that case. So my conclusion about this works is that the only solution today, I think it's the only priority we should have, is to scale up sodium borohydride, because there are some opportunities for technological deployment, but we have to scale up and solve all of the issues I have mentioned. Now to finish, I would like to briefly mention ammonia borane. So ammonia borane is a technology that is quite interesting because in the same molecule, you have the protic and hydridic hydrogen. And I would like to mention the Thermoenergy company, now bankrupt also, from United Kingdom. They developed a system, a composite from using a polymer and ammonia borane. And they also had an agreement, a partnership with the company Safran for developing for hydrogen storage dedicated to plane applications. but it was in 2014. But since then, the same company has bankrupt, and Safran does not consider ammonia burning as a potential way to store hydrogen. And yesterday, I read a paper about one expert in this kind of application. And for planes, it is considered that cryogenic hydrogen, liquid hydrogen, will be the solution for storing hydrogen on board. But anyway, another demonstrator is from the Korea Institute of Science and Technology. You can see here that they were able to flight an unmanned aerial vehicle, and they used also ammonia borane in the form of beads, and they were dehydrogenated in a thermolytic conditions. So they added ammonia borane in a solvent, in a heavy solvent, and they heated it to get hydrogen. In fact, the dehydrogenation of ammonia borane is a really complex process. So depending on the state of ammonia borane in a solvent or in solid state, in red here, or in solid state and in the solvent state, it's a mixture of solution of ammonia borane and precipitating ammonia borane for the blue arrows. The reaction is quite complex. So it is really difficult to progress if we are not able to be selective in the dehydrogenation of ammonia borane. And to make, I have a problem with my screen. Okay, so to be clear and to make the discussion simple, the idea is to dehydrogenate ammonia borane by heating it to recover 2 equivalent of hydrogen, pure of course, below 100 degrees C, and with the formation of one product only, for example, polybenzylene, because it is possible to rehydrogenate it by reduction in hydrazine. So the challenge is to make this dehydrogenation reaction as simple as shown by this slide. And for this, 5 strategies have been developed so far. The first strategy is to solubilize ammonia borane in a solvent. The second one is to dope ammonia borane with a solid state dopant, for example, copper chloride. The third one is nano-confinement, so putting ammonia borane in the porosity of porous material. The fourth one is nanosizing, it is what we are doing. And the fifth one is to elaborate derivatives like the amidoboranes I mentioned in the introduction. But the problem is that none of these approaches is mature enough to go further in applications. The most attractive ones will be nano-confinement and the derivative nowadays, but it is surprising that we have not seen in the literature any scale-up system right now. For, in my opinion, there are some room for improvement for 2 of these strategies, nanosizing and the derivatives. But recently, while discussing with an industrial partner, one question arose: is it technologically relevant to focus temperatures lower than 80 degrees C for dehydrogenation? In fact, since over the past 15 years, we systematically focused on destabilizing ammonia borane to recover hydrogen below 80 degrees C. And now the industrial partner is wondering about this strategy and thinks that is not relevant at all. Anyway, I'm going to conclude. So in fact, it's not really a conclusion. It's just my feeling and my vision. And to cite one actor in a famous French movie, the thing is that we have to admit that we are going around in circles with boron-based materials for hydrogen storage. I think that for sodium borohydride, the only way to progress is to scale up. Otherwise, we will spend too much time and spend too much money to produce some new results, some new catalysts, some new knowledge, but without being able to scale up the system and to deploy the technology. With the other boron-based material, I think that none is mature enough and efficient enough, for example, to supplant the metal hydrides that have already shown that they are able to be scaled up, like the Toshiba's H21 system, where neutral metallic hydride is able to store hydrogen produced by electrolysis. And finally, I would like to thank you for your kind attention and mentioning once more that boron-based materials are not mature enough for storing hydrogen.
Thank you very much, Dr. Demirci, for this very informative and nice presentation. And if there are any questions from the participants, please type in the chat screen or in the Q&A screen. And maybe in the meantime, I have one question out of curiosity. So you showed some applications of boron-based materials in aerial vehicles.
Yeah.
And, I was wondering your opinion of the chance of commercialization of these storage technology in land vehicles or automotive applications. Can it compete with compressed hydrogen or metal hydrides?
I don't think so. I think that for automotive applications, compressed hydrogen is mature enough, and it is the best way to propose a feasible and easy solution for customers. For boron-based material, I don't think we have any future in this kind of applications.
Okay, thank you very much. I'm checking if there are other questions.
Sure.
Well, I don't think there is other questions. So thank you again for the presentation.
I thank you.
I would like to continue with Mr. Zafer Üre. Mr. Üre started his career in J&E Hall in the refrigeration field and later worked as a consultant for a number of UK-based building services consultancy firms. He also served with York International in overseas markets as a sales manager. Currently, Mr. Üre is the founder and managing director of PCM Products Limited, specialized in PCM-based thermal energy storage products and associated low energy cooling technologies. Mr. Üre takes a special interest in promoting alternative energy efficient and environmental friendly technologies and overall load shifting site demand management practices for practical refrigeration and air conditioning applications. So Mr. Üre, the floor is yours. You can share your screen and please start your presentation.
Okay, can you hear me?
Yes, we can hear you.
For some reason, it's not sharing. So you cannot start the screen share. Okay. It's not allowing me to say share my screen.
Dr. Demirci, I think you need to stop sharing screen first.
Try again. No, I think it's.
Okay, I think Dr. Demirci, you are sharing your screen. That's why Mr. Üre cannot, if the TÜBİTAK staff is also here, they can also do it. Okay, it's done.
Okay, now it's working. Thank you for the introduction. Can you see my screen?
Yes, we can.
Okay, great. Thanks for everyone. Good afternoon. And I'll be talking about the thermal energy storage, storing the energy in the form of thermal. And really, our main focus is the built environment whereby people lives, either whether it's a house, domestic, or commercial, office buildings, industrial, whatever happens, wherever the human occupies a space. With the modern living standards, we need light, power to drive everything what we have in the house, utility, as well as we have to heat them and cool them, as well as provide hot water. So these are the essential services, M&E, mechanical and electrical services, we have to provide for human beings living in modern, if you like, the housing or the office working environment. In order to provide these services, we use main primary engines, machines, whether it's a boiler or heat pumps or chillers or coolings, and somewhere off the line, we provide these services using some sort of machinery, and those machineries requires primary fuel, generally either gas, oil, or some sort of electricity, and of course the water to go and satisfy this demand. And those are the primary energy sources. And lately, within the last maybe 10, 15 years, we start introducing some sort of passive cooling techniques, as well as solar and wind energy as alternative to that primary fossil fuel-based energy demand. So this is basically the ladder, the steps we provide the services. And within that services, majority of these requirements in human occupation requires some sort of energy, and usually either heating or cooling type of energy. And if you can store that energy and spread the load, that will be a significant advantage for the grid, as well as basically the production of that energy and use of it. And when we say storing high is above 0 degrees C, freezing temperature of the water, low, below. And in order to bridge the gap, and if you can store the energy, which like the previous speaker talked about storing energy in hydrogen and using, or batteries, some form, some shape, really when the energy is available, especially if it's free, like solar or cold energy overnight, if you bridge the gap between the energy availability and energy use, and that will give us a significant advantage rather than wasting available energy. And there are two types of technologies available, sensible and latent heat storage, energy storage. We can store that heat or cold in sensible or latent. The difference between them, those who are not familiar with this technology, sensible and latent heat aspect, I could describe as a simple format, like take a water, cold water out of the fridge, refrigerator, put in a glass. It comes as cold, but very quickly reach to room temperature. But if you put a couple of ice cubes into the same glass, and that will stay longer cold because of that hidden ice energy coming back around 0 degrees C, keep that water cold far longer against the time scale. So of course, in order to make ice, you have to put awful lot of energy, turn water, liquid to solid, and in return, whatever you stored, it comes back in terms of thermal. And therefore, that is the principle of latent versus sensible. And most of the sensible storage, I think we all have some sort of domestic hot water storage tanks or very huge thick brick buildings. They don't get hot and cold that quickly because of that mass of the brick stones is giving you the thermal mass, or big, huge buckets, if you like the chilled water you can store. But the difference here, the volume of the water with the specific heat capacity of the water will dictate what the size should be. On the ice technologies, the most common is universally available water. And we use water in different shape of ice formats. And the advantage of why we basically go to the latent heat and ice, we reduce the volume significantly, almost tenfold, and having that latent heat. And therefore, the volume is basically reduced significantly for the same amount of energy we store. The only two problems we have with the ice is one is fixed temperature around 0 degrees C that limit what the application would be. And secondly, in order to make 0 degrees C ice, you have to go sub-zero temperatures, -8, -10. That's a significant energy penalties. And in order to overcome that 0 degrees C ice and make it more flexible, widespread applications, we have to deal with chemicals. As the previous speaker talked about the materials, if you want ice different than 0, 32F, you need to deal with chemicals. The chemicals, the most common chemicals available to use, organic compounds and the hydrated salt-based products. Some salts, like we know, for example, seawater does not freeze 0, depending on the salt concentration. It freezes around -2 or -3. And if you put a little bit, 20% table salt, or you put into your meal, the water freezes around -22. But some salts, ironically, instead of the freezing temperature going down, like calcium chloride or global salt, instead of going down, the freezing temperature of the water goes up, 8, 10, 10, all the way up to 117 degrees C. That's a very difficult concept to visualize, a hot ice using the water. But it's basically what is the hydrated salt is all about. Organic compounds, there is no water, hydrogen and carbon chains, but organic compounds could be as simple as the candle wax you burn on your dinner, or butter, sugar, anything else, which is commonly what we use. Organic compounds behave with a different temperature, give us the ice different than 0. Of course, over the last 25 years playing with these chemicals, we managed to come up with all the way from -100 to 1,200 degrees C, various different chemicals available to us to produce ice different than 0. And here is the metals, melting the aluminium or the iron even, it's a PCM, phase change material, is a wonderful thermal storage material, high temperature. We have a lot of molten salts. These salts basically is the melt and store a lot of energy. Hydrated salts, organic components, and polyglycol base, solid PCMs, all in the positive temperature, about 0 degrees C range. We have water salt solution eutectics down to -65, now is extended -74. And we have alcohol base -100 down to -100. So therefore, there is an extensive temperature range we could apply. And of course, once you are dealing with chemicals, you have to some sort of encapsulate, seal, handle. The advantage of the organics, not having water, we could make them like powders, granules, rubbers, thermoform, exposed to air is not a problem. Disadvantage is what you put into your car and you burn on your cooker is a hydrocarbon. And the fire, you need to be careful how you expose and handle these materials against the fire. Salt hydrate is wonderful, cheap, and widely available. But the problem is the water that tends to evaporate if you expose to the air, and you end up with the dust. In order to overcome that, we basically have to use some sort of plastic or metal encapsulation to handle the PCM. But as it said here, there is a will, there is a way, and you can apply these things in various forms or shapes. And therefore, the next I will be giving you, now we have a new toy, different than 0 degrees CIs. And what can we do with this toy? And also the reason, why do we need to play with this toy to make the thermal energy storage? Why do we need a TES? The reason we need TES, here is the typical cooling profile of a building or process. You have like office complex, if you think about 7, 8 o'clock, it starts, by 6 o'clock, everybody's gone. But you have here during the daytime, have a mountain to climb because the peak 100% you reach around lunchtime, but nothing in the middle of the night. So the idea is if we shade this mountain and shift it into the off-peak periods, we can level it up. First of all, we can use half the size machinery to do the same job. And also we can utilize free energy as well as maybe cheap energy, help to basically grid supply. And here is the heating profile is exactly the same. Overnight, you get the excessive cool heating demand. And during the basically is the, when the sun goes down, you have another peak here coming. So if we can level this one up and store that hot, when the free energy available or any other means, we can spread that load, that will help the grid. And here's on the right-hand side, a typical UK electricity generation in January 2020. You can see basically what the electricity has been produced. Initially, the cheapest one is the nuclear, and it has to run all the time. And here in the UK, we have gas turbines, which is the lowest CO2 emission plants, and they take the burden and the bulk of it. But as you can see, as soon as you come to the lunchtime, we start firing up the coal fires. And solar and wind is unreliable. It goes up and down, unpredictable. If there is no sun, if there is no wind, you have a massive coal plant producing a lot of CO2. And also advantage of shifting this mountain here to off-peak, we also save a lot of CO2 because midday, our CO2 emission is around really 0.3, 0.4 kilogram per kilowatt hour electricity, but at night it's just about half. The reason is nuclear and very efficient gas turbines, natural gas-fired turbines. So therefore, you're not only basically helping the grid to level and build a less power plant, but also you are pumping less CO2 for the same energy. And as you can see here is the annual pattern is more or less the same, jig-jag like a saw, but also is for the last 10 years is more or less the same pattern is showing how many gigawatts we produce. And as you can see here, like the 30 gigawatt is average basically is the load, but we need at least 45, 50 during the peak hours. Now we understand why we need the thermal storage and how do we do it. And there are basically try to minimize the environmental impact on these built environment services, achieving the zero energy function. And this is the basically holy triangle is the cardinal rule. And the top of that is the free energy. Anything is free is available, that's great. And secondly, basically, not everything is free in life. We have to use and pay for it. And if you are going to run any machinery, let's waste nothing and try to use every ounce of energy out of that fuel, what we use. Secondly, the reason we explain, we need to shift this load and level the basically the operation. Let's have a look at first of all, the free energy. What's free? What's free really is there's the day warm energy. sun, and the night cold energy. And this is the typical ambient profile between night and day. So therefore, we have a cooler nights, warmer days. If we can bridge, here is the PCM, our wonderful bridge. If we can bring the day heat into night, we don't need heating. We reduce the heating significantly. If you bring the cold night to day, we reduce our air conditioning cooling demand. So that's a natural 24-hour daily cycle. Is wonderful. If you can achieve everything free, not running any machinery, consuming electricity, that's the ideal. Here is the typical office building. And during daytime, people basically generating heat, solar, internal gains, machines, and everything is getting hot. And heat tend to rise. But of course, in the night, nobody there. The building is cold, is around 20, 21 degrees C, even in the middle of the summer, maybe 24 degrees C. Therefore, it's cool enough. So if you have an ice, think about the ice plus 27, and that will freeze naturally within the building without running any refrigeration, any cooling. And therefore, once you build that ice, remember our glass with no ice in the glass, water gets very quickly warm. But if there's a glass, it keeps cool. Exactly the same. If we have this ice in our office confined space, the heat will go up by naturally, and it will hit the cold surface and start melting the ice. Hence, your glass will be cooler, and the people basically will be cooler. If you have big enough ice, think about like a sponge soaking up the heat. If you have big enough sponge, you will end up soaking the whole heat. And if you can handle and absorb the heat without coming back to the space and where people sit, you don't need any air conditioning, any machinery. We can achieve this basically with natural cycle of the ambient, and therefore it will be an energy-free environment cooling system. And that could be seen in the tiles format. As the temperature of those ceiling is relatively higher than the room. So that basically will give us, and also we can improve that significantly in terms of on-demand cooling using these fans and the mechanical ventilation. But the concept is we make ice overnight free of charge using the natural cold night energy and bring that cold back to daytime when these are like IT centers, when the computer rooms is a backup as well as cooling the IT centers. So we can achieve a lot of free cooling. And especially, of course, is like these are a typical mobile transmitting boxes, and you see this big little box with a big antenna sticking out on the pole. And even in the Middle East, you should be able to achieve, which we do, using like 34 degrees C ice, even in the desert, the night time temperature, 3 in the morning, less than 28 or 30 degrees C. So we can make ice naturally during the daytime, soak up all the day sun energy as well as internal heat gains. And these are all gas line controls, electronics, and all the other basically mobile transmitting boxes in the Middle East. And they have no mechanical cooling, no electrical cooling, purely passively storing night energy and handle all the sun, ambient, as well as internal gains during daytime. Here is the typical example of the museum in Oman, in Muscat. And that's really 2 megawatt of energy per day by purely using the cold energy, which is around maybe 25, 30 degrees C overnight. So that's good enough to make ice for us. But of course, daytime in Oman, the ambient could be as high as 55. So if you can cool 55 ambient going into the museum, 15, 20 degrees C, that almost reduces your air conditioning load as much as by half using just purely the ambient. Another option we can improve this further, when the weather man or the weather lady tells you on telly what the ambient will be tomorrow, and that what she's talking about, what we call a dry bulb. Dry bulb when it's 34, and the wet bulb, what is the actual, basically, is the wet ambient conditions would be 22 degrees C. So that's the difference between the dry bulb and the wet bulb. Hence, majority of the large industrial units, what you see, one of those big, ugly cooling towers. And the reason the cooling towers prefer for large-scale installation, because they work using this as ambient, not that. The lower the ambient onto heat rejection of any mechanical cooling, the lower the power consumption. So therefore, we can improve our passive cooling further rather than using dry bulb. And therefore, here is a building, council building, 8-story high in Melbourne, Australia, which they kept getting heat waves. But this building has no chillers. This is an office building with no mechanical cooling. Purely they have a cooling tower on the roof and 15 degrees C PCM, phase change materials, tanks in the basement. All they do overnight, circulate the water, freeze these 15 degrees C PCM, and in return, they supply 16 degrees C chilled water to the ceilings, and it's like a sponge soaking up the heat mechanically. And it's been working there almost more than 10 years and perfectly fine. And in Melbourne, no mechanical cooling. The energy consumption is next to nothing. And of course, we talk about all this cooling, but also, of course, you can store the heat. Here is the typical example of solar collector, Commonwealth Games in Australia again. This is Dubai. You can also utilize that energy to drive your heat pump system as well as hot. We could do underfloor heating using the solar collectors or PV. PVs generate only 20% electricity, but 80% heat. That also can be recovered and used. Here's a typical house in Ireland and no boiler. And that saves a lot of CO2 reduction as well as environmental benefit. And all day produce electricity, run that fan, and the heat picked up from the PV, melted 22 degrees C PCM. Nighttime, that stored energy, pumped it back into the space to keep it warm. And same could be done, solar collectors hardly, especially in the UK, produce hot water, 65, 70 degrees C, but they produce at least 30, 35, 40 degrees C water, even in the middle of winter. That's good enough to freeze the PCM on the floor. And that basically will give you the storage all day. All that sun energy goes to the floor. And overnight, when you need the heating, it radiates and keeps the place warm, free of charge. And so you can heat the domestic buildings. Here's a large-scale installation again, the solar. This is Qatar FIFA 2022 World Cup stadiums. The theory was, of course, the initial game was supposed to be in summer. So they declared they could do the whole stadium cooling, as you can see, covered in Qatar using sun. So this is a solar-driven air conditioning system. And as you can see, this is the demo stadium they built. And there's no power supply, everything from sun and collecting the hot oil. Hot oil drives absorption chillers. That puts that cold energy into this big tank, and that's roughly 5 megawatt hours. And as you can see, during the test, when the outside 37, inside the stadium is 19. And that cooling, that's almost 30, I can't remember, about 15 or 20,000 people, actual stadium. That's an awful lot of cooling can be done from the sun. And again, this is a domestic environment. Here is the 27 degrees C PCM tiles in the floor, and solar collectors put the heat into this floor thermal storage tank. So the whole heating of this house in a UK environment can be basically provided free of charge, as well as free of any boilers, gas, or any other electrical demand. And greenhouses, there's another typical example, because by nature, the name of the greenhouse is scary and annoying, but in greenhouse, growing vegetables and the fruits and all the rest is wonderful, because during the daytime, they get excessively hot, but overnight it gets very cold. So putting this thermal mass into that greenhouse, it's stabilized. It keeps it warm overnight and cool during the daytime without consuming of energy. Of course, we said not everything is free. We need to use some machinery. We cannot satisfy the natural and the modern living demands. So if we are going to use, we should not waste anything. The biggest waste at the moment is the heat pumps. They are wonderful, they are great, but in order to basically cool something, you don't put cold in. You extract heat from the space and dump it somewhere. That somewhere could be ground or air. But of course, what you are dumping is the waste. So if you can find a way to use that waste, that's great. Here's a typical example. Schools have, generally in the UK especially, is mainly heating, because summer times there's no school. Everybody, all the students in holiday, mainly they need heating. And the heat pump wise is very efficient, and therefore you can heat. But of course you have a massive cooling, and you need to reject that cold or extract heat from somewhere, either air or water. But equally, the same buildings like university campuses with some pieces, massive IT centers. IT centers requires a lot of cooling. And therefore, if you can combine heat the building and cool the IT centers, we can basically utilize the whole energy around basically COP 5, 6 from the cooling, another 6, 7 from the heating side of it. So therefore, when we put 1 kilowatt of electric, we can get almost 13 kilowatt of combined energy. Here is another one in Italy, the microchip factory. All year round, they need humidity and temperature control. Hence, they need heating and cooling simultaneously throughout the year in different degree. And therefore, if we put 13 degrees C on the chilled and 46 degrees C on the hot side, we can run these basically the heat pumps flat out, store the surplus energy, because sometimes you need more cooling, less heating, or vice versa. So we do not waste any energy at all and combine. Here's a typical example in Norway, whereby that is a university campus, the University of Bergen, and whereby they have ammonia heat pumps, and they have to extract heat from somewhere, either lake or sea or ground or air. But instead of that, they basically extract heat from the phase change materials. There are 4 large, huge tanks as around 12 megawatt hours. So all night, these ammonia heat pumps, chillers, freezing the PCM is 10 degrees C plus 10, and therefore is very efficient. And that basically heat goes to the student accommodation, which they need that heat. Otherwise, they have to use some boiler or some other means to heat this student accommodations. And of course, during the daytime, this university has a large, huge campus with massive cooling demand. And so therefore, that whole cooling is provided free of charge as a byproduct from these heat pumps. And therefore, the efficiency of these heat pumps is around maybe 14, which is a significant. You put 1 kilowatt electric and get 14 kilowatt combined. Again, is another typical example in London, in near Thames, opposite the House of Parliament, a National Theatre. And that basically housing all the office complex as well as the show, which the big theater, and only 2-3 hours evening shows. So therefore, they have this combined heat and power CHP plant. And they, while they are producing electricity for during the daytime office, they have a massive waste heat coming from this engine. So that engine drives the absorption chillers. They put all that waste energy into the useful PCM 8 degrees C tanks. And of course, during the 3-hour show, the theater gets very hot. They need air conditioning. Instead of installing mechanical cooling, they just use what is stored free of charge during all day process, this waste energy from the engine. And therefore, they save significant in terms of the running of 2 megawatt hours of cooling and free of charge. And that's, so again, as I said, once you put the fuel, you have to squeeze that machine every ounce energy to get it out, not to waste. So therefore, thermal storage gives us this facility. Finally, we said we use the machine and we got as much as free, but now we still have a load to deal with because it peaks. Here's the conventional system, especially cooling, but heating is the same. Instead of chiller, you have a boiler. When the building load goes up, chiller has to go up to match. Think about the old-fashioned scale. One side of the scale goes up. You need to put something on the opposite side to balance and level. And unfortunately, that basically does not help us, the leveling this, shaving this mountain. Basically, you have to end up climbing on that mountain, which is consuming a lot of energy. But if we make a plateau flat, that's the way we can do that, because this building, if it's not functioning after 6, 7, like office buildings, we can run the machinery. We need half the size and put all that energy into the tank and use during the tape up, combine these two together. When the load goes up, we satisfy the demand is basically sharing between machine and the thermal storage. Here is the typical examples like is airports in Bergen Airport, or train station, high-speed train stations in Saudi, or office buildings. This one is in Singapore, again is Norway. But the principle is by running like airports, for example, 3 in the morning, nobody flies. Airport is almost shut, but you have a massive infrastructure chillers. If you can use them and put into the thermal storage, we can reduce during the daytime peak loads. Train stations is the same in Saudi. Also Saudi disadvantage. In daytime, you have a 55 degrees C ambient, but nighttime is 30. So that also saves a lot of energy for a given cooling load. Same basics apply for certain areas, certain times, helping the grid as well as economics. Like, for example, this is in China, in the factories, 2 hours in southern China, the utility companies cannot provide enough power to satisfy domestic as well as industrial. So 2 hours during lunchtime, I think is between 12 and 2 o'clock, the energy price almost 40 or 50 times higher. So the tendency is shut down the whole air conditioning 2 hours, but when the ambient 38, 90, humidity is almost 60, 70%. The minute you shut down this air conditioning in the factory, the people working there sweating like a sauna. And you need to do something. So what they do all day, running 20 hours, the chillers, to put some sort of thermal storage into the tank. And those 2 hours, they shut down the whole air conditioning machinery, extract the heat, cooling energy from the tank, and satisfy and handle. You can also use a backup, like this Australian Parliament in Canberra, when IT centers there were UPS, uninterruptible power supply, to run the computers, but not the air conditioning. Again, Canberra is hot, so all they need 2 hours voting start to finish, because they cannot terminate halfway through. And that basically sits permanently 8 degrees CPCM on the supply line. And if the chiller fails, PCM takes over, give them 2 hours cooling, and that basically handled as a standby. Same can be applied to refrigeration, cold stores, distribution centers.
Mr. Ray, I would appreciate if you could wrap up in 1 or 2 minutes.
Done. Here's the conclusion. Basically, is this the thermal storage gives us the free energy availability to use, and if you use, we should hopefully not waste anything, and shift and level the loads. Always consider mixing technology rather than one technology, and also never ever forget the return on investment. Someone has to pay for this, and therefore you have to make sure economically it's viable, and also the most important thing is to use the right technology for the right application. And that's my conclusion, and I hope I gave you the flavor and what thermal storage can offer. And I'm happy to answer any questions or clarification needs to be. Thank you.
Thank you very much for this presentation. We have learned a lot about different examples of thermal energy storage technologies and also PCM examples. And if there are any questions, please type in the Q&A and chat screen, and I will wait for a few seconds. Okay, I think there are no questions. The email of Mr. Ure is also on the screen. So if you have any questions, please. There's one question, I think. Let me see. Yes, there's one question from Nadir Javani. His question is there any policy to build a local PCM for Turkey?
Not at the moment. Depending on the market and what's the volume of requirement. But yes, there's always opportunities.
Okay, thank you very much again. So now I would like to continue with our final presenter, Professor Erkan Öterkuş. Dr. Erkan Öterkuş is a professor at University of Strathclyde. He is also the director of Peridynamics Research Center. He received his PhD from University of Arizona, USA, and was a researcher at NASA Langley Research Center, USA, before joining University of Strathclyde. His research is mainly focused on computational mechanics of materials and structures by using some of the state-of-the-art techniques, including peridynamics and inverse finite element method. He is the co-author of numerous publications, including the first book on peridynamics, journal and conference paper. Dr. Öterkuş is an associate editor of Journal of Peridynamics and Non-Local Modeling and ASME Journal of Springer Materials and Technology. So it's my privilege to give the floor to Dr. Öterkuş.
Thank you very much, Dr. Çolpan, for a very nice introduction. So let me just share my screen. Okay, so I hope you can see my screen.
Yes, we can.
Okay, great. So today I just want to talk about fraction modeling based on peridynamic theory. Before I start, let me give a brief introduction. So for those of you who are not familiar with this terminology peridynamics, so I will just give a brief introduction. So since this conference is mainly on energy, so I try to actually show you some relevant examples, including energy transition process, energy storage, and hydraulic fracturing. And I will conclude my talk with final remarks. So what is peridynamics? So peridynamics is actually a new computational technique, but from a scientific perspective, we call it a new continuum mechanics formulation. So why do we say or claim it's new? Because we are using a new set of equations with respect to the traditional equations. So instead of using partial differential equations, we are using integral equations in peridynamic framework. So using such equations actually will give us some advantages, especially dealing with discontinuities. So when I say discontinuities, basically from structural perspective, these are cracks. So basically, you know, if you want to predict how cracks they initiate and propagate, basically it's an important question for structural analysis, and peridynamics has an advantage to deal such cases. So by using peridynamics, basically we can consider any number of cracks in the system, and also to decide when these cracks they emerge and how they are going to evolve, we are using pretty simple criterion to define those. And compared to some other techniques, especially implemented within finite element methodology, which is a very popular technique in structural analysis, I think peridynamics has certain advantages, especially dealing with a large number of cracks. So that's one of the main advantages. So, you know, I was talking about continuum mechanics. Since I don't have too much time, you know, I don't want to really go into details, but in simple terms, when we talk about continuum mechanics, you know, this is a kind of a simplified technique to analyze structures. And when we do this, what we are considering is any structure that we are analyzing, they are continuous and they are made of small, small regions that we call material points. And how these material points are interacting with each other, it is probably the most important aspect of continuum mechanics. And this actually giving us how the structures are deforming under external loading conditions. So from a classical point of view, that Cauchy actually formulated 200 years ago, he assumed that these material points are interacting in a way that they need to touch with each other. In other words, he came up with this partial differential equation to describe how these material points are basically moving. This equation is basically nothing but Newton's second law, which is written in some other parameters that we are using in structural mechanics, for example, stress parameter. So this equation is really useful. You know, people have been using this for almost now 200 years, and they analyze many different problems, but it also has a deficiency of having derivatives in them. So why do we have this problem? Because when we are dealing with discontinuities, such as cracks, as I mentioned earlier, we have a field which is discontinuous. And when we have basically such a discontinuous field, we cannot calculate derivatives. So because of that reason, you know, whenever we encounter discontinuities, then we cannot use this equation anymore. And then we need to use some other strategies to get around this problem. So instead of, you know, having these extra techniques to overcome this problem, here in peridynamics, we are saying that let's not use derivatives, instead use integrals, so that we can use our equation all the time. And as you see, you know, at the top, this is our equation of motion that we are trying to solve in this particular methodology. And basically, this technique is working in a way that we are calculating the interaction force between material points, which is kind of a similar idea that we have how the atoms are interacting with each other. But in this particular case, rather than looking at atomistic scale, we can apply this technique at larger scales. So basically in structural analysis, what we do is we are dividing our domain into smaller regions. And that's also what we do in peridynamics, as you can see in here. And what we do is basically once we divide our domain into small regions, we assign a point to each region to represent that particular small domain. And then once we have these points, we define springs between them, just to define the interactions between material parts. And when we do this, we are defining a domain of influence that we call horizon. And basically inside of this horizon, basically we have points interacting with each other. And once we apply the load on the system, these springs, they will start to deform since points, they are going to move to another location. And once these basically springs, they are stretching or they are compressing, and we are deciding if these springs, they are going to fail or not. So in simple terms, what we are saying is, if these springs, they are stretching too much, we start breaking them. And once you start breaking them, your structure is going to start to do damage. And as a result of this, cracks will emerge, and then you will have catastrophic failure of the structure. So since this is a new methodology, people will keep asking us if we compared our technique against experimental data. Yes, we did. So this is just a simple example. In this particular case, we considered a material which is similar to glass, that's PMMA material. And as you can see, we have diagonal shape, and there's a central crack at the center of this specimen. And depending on the orientation of this crack, basically how this crack propagates changes. In other words, mode mixity changes. So we have some experimental data, as you can see, with these gray colors for different crack orientations. And we have the numerical simulations coming from our peridynamic analysis. And if you look actually carefully, you can see that regardless of the crack orientation, actually peridynamics can capture correct crack behavior. So just to give you an idea about, what type of outcome that we can get from our analysis, this is just a simple example. And in this particular case, as you can see, we have a tin plate, and we have an impactor, and we also have two cracks. And once this impactor hits the plate, we are expecting that these cracks, they are going to propagate. But the question is, how are they going to propagate? Okay, so it may not be always obvious. Okay, so you can ask yourself now how it's going to propagate, but outcomes can be totally different. So let's see. So this is a peridynamic simulation that we are going to now see how these cracks actually are going to evolve. I'm not sure if my video is working. Unfortunately, this is not. I don't know what, maybe there isn't. Just a second. Let's see if it's going to work. Okay, there's a problem. So basically, the way that this crack is propagating in this particular case, we have some certain angle. And maybe, we compared against the experimental data, and it matched really well. So, but I apologize that somehow this video didn't work yet. Okay, now, let's try to see how we can apply this logic for the different energy applications, starting from energy transition process, which is a really popular topic of today. So when we talk about basic energy transition, we are talking about actually moving from fossil fuel to greener energy solutions by using offshore wind, hydrogen energy, and so on. So especially like countries like in the UK, we are trying to increase offshore wind energy production. And then once we generate this electricity, people are also considering to generate hydrogen based on that energy. And once we generate hydrogen, now how are we going to actually transport hydrogen? And basically, especially in the UK, in the north side of UK, there are lots of oil and gas infrastructure, and people are now considering to use existing oil and gas, or basically infrastructure, to transport hydrogen. But the question is, can we do this? Okay, so there are certain challenges actually of doing this. One of them is, especially if you are dealing with hydrogen, it can cause some a situation that we call hydrogen embrittlement. So basically, hydrogen can make your material much more brittle so that it can actually break much easily. And also, I was talking about offshore wind and so on. And this is a really challenging environment, which can cause corrosion damage and also fatigue damage. So how do we analyze this? So as engineers, we need to use techniques, and we believe that peridynamics can be a really suitable solution to analyze such problems. Okay, the first issue is that I would like to show you is the hydrogen embrittlement or stress corrosion cracking. So how does stress corrosion cracking occur? So for this situation to occur, three things need to come together. First of all, your material should be corroded or can be corroded. Another thing is you should have a corrosive environment. Then you also need to have a mechanical load. So once these three things come together, this unexpected situation that we don't want, stress corrosion cracking or hydrogen embrittlement, can occur. And we try to kind of simulate this process, and we just basically consider a simple case to see if we can simulate this problem. And to achieve this, we just consider this simple rectangular specimen where we have an initial crack at the center. And to represent basically mechanical load, we apply some tension loading at the top and bottom surface. And we also put a corrosive fluid inside of the crack, but also at the same time, we painted the crack surface except the crack tip. So that is the only location which corrosive fluid can interact with our steel material. And to investigate this process in a better way, we also consider the material behavior in a much more detailed fashion. So what we did is, rather than looking at the material from outside, we just look inside. So we actually specifically model each grain happening or occurring within the material. And this, to simulate this process, we have the structure analysis, but that's not sufficient because we need to somehow incorporate the effect of influence of hydrogen. And to achieve this, we need to also simulate the hydrogen diffusion. So hydrogen is diffusing since it is interacting with the material, and we need to solve a diffusion equation. And once we solve the diffusion equation, we need to somehow find the influence of that hydrogen onto our structure analysis. And to achieve this, basically, we calculate the amount of hydrogen at any time, and then we degrade the material properties, especially the fracture properties, based on it. And one thing that I just want to mention is, although I emphasized earlier that we are using peridynamics for mainly structure analysis, now we also have peridynamic formulations for other physical fields. For example, in this particular case, now we have a peridynamic form of equations for diffusion equations so that we can solve different physical fields based on peridynamic equations without using derivatives. So if we come back to our problem, now what we did is, we investigated this problem by considering 5 different loading conditions. And what's happening is once you apply the load, the crack doesn't propagate. So you just keep the load the same. It stays at the same level. But once at the same time, hydrogen is starting to diffuse inside the material. And after some time, the material will start to become brittle and the crack starts to propagate. And for 5 different basic loading conditions, we were able to see how the crack propagates. And depending on how much load that we are applying, we observe that the crack propagation is different. There is also an experimental data. Sorry for the noise. So basically, we also have an experimental data that to compare. So we compare the crack propagation speed against our loading condition, and we saw that basically our results can capture what is observed in experiments. I also mentioned about basically other corrosion mechanisms, and one of the important one is the pitting corrosion, which is observed in especially pipelines and so on. Now, by using peridynamic methodology, actually we can capture realistic corrosion damage, basically mechanisms which is observed in different structures. And another important actually problem about pitting damage is, once we have pitting damage, it kind of creates a stress razor so that actually cracks can start from there. And we call this process as pit to crack transition situation. And by using our methodology, once we actually capture or represent how the pitting damage actually starts, and then basically by using again peridynamics, we can find out where the cracks can start from these pitting damages and also how they are going to evolve. And another problem that I emphasize is fatigue, which is a problem for many different industries, including energy transition process as well. And fatigue is happening by applying cyclic load. So basically, if you apply load again and again, or basically repeat by just repeating the loading, what happens is the structure, it will start to damage as a result of this cyclic load. And in this particular case, we just consider a very simple case that we have an initial crack, and we are just applying our load and want to see how this crack propagates as a result of fatigue load. And as you can see, we compared our numerical simulations against experimental data about how this crack propagates under fatigue influence, and we were able to actually capture the correct behavior. Now, the next thing that I just want to show is energy storage. When I say energy storage, the first thing that I want to show is lithium-ion batteries. These are the batteries that we use a lot in our cell phones and so on, basically. And people are actually making lots of investigation about how to improve the capacity of lithium-ion batteries. And one important kind of technology that they are considering is to use silicon as the electrode material. So although silicon has a pretty large capacity, what's happening is, once you charge your battery, silicon deforms a lot. So its volume expands up to 3 to 4 times of its original volume. So basically it's expanding and then shrinking, expanding, shrinking, keep deforming once you charge your battery, and this is causing cracking. So when cracking occurs inside your electrode, what's happening is basically you will start losing your battery. And by using paradigm methodology, we again couple structure analysis and the lithium-ion diffusion at the same time, so that we can see the influence of these two different physical fields on each other. And in this particular case, we just considered different amounts of cracking inside the electrode material, and we were able to see that once we basically charge our batteries, these cracks can evolve. And also fuel cells is another basic promising kind of technology of today. And there are different fuel cell basic types. And we mainly looked at solid oxide fuel cells, which are operating at very high temperatures, around 800 to 1000 degrees Celsius. And we just investigated, if such temperatures, they can cause damage inside of our battery. And in this particular case, at the bottom side, you can see that with these red colors, regions especially, they cause actually damage, or these are the damaged regions which can occur as a result of high temperatures. Okay, my final actually example is hydraulic fracturing. I mainly show some green technology, but we should not also forget about traditional technologies as well, or traditional fuels, because we will keep actually using them. The green fuels are not going to be used right away. So the technology that actually people are using a lot these days is hydraulic fracturing. And this is basically a technique that people use to extract oil and gas from a rock that we call shale. And to extract this basically oil and gas from that, we need to actually create cracks inside this rock. And also we need to pump a fluid at the same time. So to simulate this process, what we need to do is basically we need to couple two physical fields. One of them is structure analysis. The other one is porous flow. So once we couple them with each other so we can simulate this process, I just want to basically show you a simple example where we have kind of this shale type of rock material, and at the center we have a crack, but this crack should be pressurized with our fluid so that this crack can grow. And basically these results are just showing that by using paradigm methodology, once we start actually pressurizing our crack, it can start propagating. So this is kind of showing us that we can use paradigms to simulate the hydraulic fracturing process. So for those of you who are interested in paradynamics, this methodology, actually there are many books available now in the literature, so you can find them. If not, please send me an email. And also we have a website which is called paradigms.org. Again, we try to actually provide some information about this new technology or methodology. And as a final remark, we believe that paradynamics is a suitable method for failure analysis of problems relevant to energy transition process and also energy storage applications. And also it's also a suitable tool to simulate hydraulic fracturing process. So with that one, thank you very much for your attention.
Thank you very much, Professor Öterkuş, for this presentation. Actually, I didn't know about peridynamics before, so for myself, I have learned that I can use it for very different applications for related to energy, such as fuel cells, lithium batteries. Thank you again. If there is any question for Professor Öterkuş, please type in the screen, in the chat screen or Q&A screen. Okay, it seems there is no question. And I would like to thank you again for this very informative presentation and for your attendance and contribution to TÜBA conference.
Thank you very much for inviting me.
And with this presentation, we conclude this invited session, and there will be a 20 minutes break now, and at 3 p.m. the new sessions will continue. And I would like to thank all the participants for their attention and participation. Have a great day.
Thank you. Bye-bye.
Bye.
Good afternoon for those who are in Turkey, and good day for those who are attending from other parts of the world. And welcome to this afternoon session where we have two distinguished speakers. The first speaker is Professor Mang Ni of the Hong Kong Polytechnic University. Professor Ni received a bachelor and master's in aero engine engineering and a PhD in mechanical engineering from University of Hong Kong. And he has been a professor at Hong Kong Polytechnic University, and he was recently appointed as Associate Dean of Faculty of Construction and Environment in the same university. He has conducted collaborative research in Germany as a Humboldt Fellow. Professor Ni will be making his presentation under the title New Developments in Zinc Air Batteries for Energy Storage. Professor Ni, the floor is yours.
Okay, thank you, Chairman, for your introduction. So I'd like to share my screen. So can you see my screen?
Yes, your screen is visible. Okay. If you can put it in the presentation mode, it will be more visible.
Yeah.
Yes, this is perfect.
Okay, so thank you for your introduction. So good afternoon, ladies and gentlemen. This is Meng Ni from the Hong Kong Polytechnic University. So it's my great honor and pleasure to be here and share with you our research on zinc air batteries for energy storage. So I'd like to first talk about the background of our research. Why do we choose to work on zinc air battery? Then I will share with you our research development in zinc air battery, including the hybrid zinc metal air batteries and the engineering design of air electrode of zinc air battery. We will also introduce the zinc air flow battery for large-scale energy storage. Then I will also briefly talk about the other research activities, including fuel cells and low-grade heat recovery and so on. Then in the end, I will draw some conclusion, and I will also try to seek possible collaborations with researchers. So why do we choose to work on zinc air battery? Well, batteries are very important electric energy storage technologies. So they are very important for a number of applications, right? For example, for the renewable power application, because renewable power like solar and wind are fluctuating and intermittent. So we need effective energy storage, and the electric and the rechargeable batteries can play a very important role for renewable power application. And for electric vehicles, batteries are also very important to achieve long-range electric vehicles. And nowadays, we have a lot of different type of portable electronics, such as mobile phones, notebook, and so on. So we need batteries to provide power. And recently, there are more and more flexible electronic devices, such as flexible watch, flexible mobile phone, flexible sensors. So these flexible electronics also need rechargeable batteries, especially flexible rechargeable batteries. So we choose to work on batteries because of these potential applications. So you may realize that electrical energy storage, especially batteries, are very important for renewable power wide application, for electric vehicle development, and for personal electronic devices, especially for flexible electronics. And there are different types of batteries, and we find the metal air batteries are very promising because of their high capacity. Among different types of metal air batteries, we find the zinc air battery and the lithium air batteries are very promising. Of course, the lithium air batteries have the highest theoretical capacity, so they received the most attention in the past few years. However, we believe the zinc air batteries are also very, very promising because although the capacity of zinc air battery is not as high as the lithium air battery, well, it's still much higher than the commonly used lithium-ion battery. So the theoretical capacity of zinc air battery is about 820 milliampere hour per gram zinc. So it's much higher than the lithium-ion battery. And compared with the lithium air battery, the zinc air batteries are also cheaper and also they are safe in operation. So we believe they will have a very good future. However, there are also some challenges facing, well, zinc air battery. So we need to actually look at their performance and durability. And from the previous research, it's found after long-term operation, the performance of the zinc air battery will be decreased. And over extended period operation, the zinc air battery may even fail, mainly due to the zinc dendrite and the passivation layer formation on the zinc electrode. And on the other hand, the performance of the zinc air battery is also not very satisfactory at the moment. This is because in the discharge process, the discharge voltage is normally below 1.2 volt, and the charge voltage is over 2 volt. So you can see through one charge and a discharge, the efficiency will be lower than 60%. And this is because the charge reaction and the discharge reaction are relatively slow, so they will involve high energy loss. So in the discharge, we will have the ORR, the so-called OR reaction, oxygen reduction reaction. And in the charge process, we will have the OER reaction, oxygen evolution reaction. So you can see in discharge, actually, well, we will have the ORR, and on the zinc electrode, the zinc will be oxidized, and in the charge process, the reaction will be reversed. And due to the sluggish ORR or OER reaction, the performance is not very good. So if we find for zinc air battery, actually the durability is related to the zinc electrode, and the performance is related to the air electrode. So in the past few years, we focused our research on zinc air battery, and we mainly look at how to improve the zinc air battery performance by modifying the air electrodes. So we did some research to develop bifunctional catalyst, and we also try to optimize the electrode structure. So bifunctional catalyst means the catalyst is effective in catalyzing the ORR reaction as well as the OER reaction. So for both reactions, they are effective. So it's called a bifunctional catalyst. And in recent years, we also try to employ some engineering design principle to improve the battery performance. Because we know the OER will involve large energy loss. So we try to incorporate some metal redox reaction into the battery operation so that we may enjoy a higher discharge voltage and a lower charge voltage. Actually, well, if you look at the zinc-based battery, well, you will find that the zinc-based battery can be classified to two groups. One is the closed system, such as the zinc nickel battery, zinc copper battery, and a zinc sulfur battery, and some of them are commercially available. They can deliver a relatively high voltage, about 1.8 volt, but their capacity is low. We also have the half-open system, like the zinc air battery, and they can deliver a high capacity, but the voltage is relatively low, normally below 1.2 volt. So we try to integrate these two types of battery and the cell level by incorporating the redox reaction of the metal into the air electrode so that we can possibly enjoy a high voltage and high capacity at the same time. So this is our target. So we first developed the zinc copper oxide and zinc air hybrid battery. So we try to combine the two battery and the cell level in order to achieve both high discharge voltage and high capacity. So these figures show you the structure of the hybrid battery. So we have the zinc electrode, the liquid electrolyte, and the air electrode. So the air electrode, we incorporate the cobalt oxide into the air electrode with the aim to introduce the cobalt oxide redox reaction into the air electrode reaction processes. So we want that the cobalt oxide can be oxidized in the charge process to produce cobalt CO2. And in the discharge process, we want the cobalt oxide to be reduced first, followed by ORR reaction. So we actually fabricate the air electrode using the electrode deposition methods, and we obtained the nanostructured air electrodes, the cobalt oxide. Then we conducted material characterization. So we're looking at the microstructure, we're looking at the material phase structure, and so on. So what we obtain is porous nanosheets cobalt oxide material, and we can also find the loading of the catalyst to be around 2.72 milligram per centimeter squared. And based on the characterization, we also find the specific surface area is pretty good, about 100 meters squared per gram catalyst. Then we conducted measurements of the performance of the battery. So you can see, well, in the charge process, the cobalt oxide is actually oxidized to produce CO2, right? So this is oxidation reaction. Once the cobalt oxide is fully oxidized, we will have the conventional OER. Because the cobalt oxide oxidation reaction will involve a relatively low charge voltage, then for the battery, we can actually enjoy a low charge voltage. And in the discharge process, the cobalt oxide will be first reduced. So CO2 will be reduced to CO3O4. And this reduction process can give you a relatively high discharge voltage. Once all the cobalt oxide is fully reduced, we will have the ordinary OR reaction. So you can see in such a battery, we actually involve the cobalt oxide redox reaction, or oxidation and reduction reaction into the battery operation, so that we can enjoy a higher voltage, right, discharge voltage. And we can use the battery to light up a red LED lamp, and it's successful. Then we also measure the specific capacity of the hybrid battery, and we find we can achieve a specific capacity of about 792 milliampere hour per gram zinc, which is very close to the theoretical capacity of the zinc air battery. So you can see here, we achieved both high voltage, 1.85 volt. Conventional zinc air battery can only achieve 1.2 volt, but we can achieve higher voltage, and we can still maintain high capacity, about 800 milliampere hour per gram zinc, very close to the theoretic capacity. Of course, we also need to test the durability of the battery, and we run the battery for 200 cycles, and we find, well, it's stable. Then we calculate the energy efficiency of the battery, and we find, well, conventional zinc air battery can achieve an efficiency of about 60% or below 60%. But for our battery, we can achieve an efficiency of over 70%. So you can see, well, the efficiency is above 70% over 200 cycles. So it means the hybrid battery concept is feasible. And indeed, we can achieve high voltage and high capacity at the same time. And already mentioned earlier, nowadays, well, a lot of flexible electronic devices need flexible battery. So we also try to develop flexible battery to provide power for the flexible electronics. So here we need to use the gel electrolyte. For the previous battery, we use the liquid electrolyte, but here, in order to make the battery flexible, we need to use the gel electrolyte. Then we fabricate the battery and we test the battery under different bending conditions. So we twist the battery is still working. So here I think I can share with you video. Let me see. Oh, can I show you? Oh, I cannot show you the video. Anyway, it's okay. So based on the research, you can see actually you can twist, you can bend the battery, and the battery is still working safely, and it's still working. So apart from the zinc Cuba air hybrid battery, we also developed another hybrid battery, the zinc silver air battery. Again, the idea is very similar. We want to incorporate the redox reaction of silver into the air electrode, so that in the charge and the discharge process, we will have the silver oxidation reaction in charge. Once all the silver is fully oxidized, we will have the OER reaction. And in the discharge process, we will have the silver oxide reduction reaction. And once all the silver oxide is fully reduced to silver, then we will have the conventional OR reaction. So you can see, well, again, we incorporate the silver redox reaction into the air electrode, and we can actually regulate the discharge and the charge voltage. Because silver is a very good OR catalyst, but it's not very good for OER. So we still need to use another catalyst, which is ruthenium oxide. This is a very good OER catalyst. So basically, the air electrode is a composite containing both silver and ruthenium oxide. So silver is used for OER, and ruthenium oxide is used for OER. So again, we characterize the material property, and then we test the battery performance. Again, you can see we can achieve pretty good performance. We can achieve a power density of over 90 milliwatt per centimeter squared. And again, we achieved a pretty high capacity of the hybrid battery, about 800 milliampere hour per gram zinc. So again, this is very similar, very close to the theoretic capacity of zinc air battery. And we also do the charge discharge process, and we find in the charge process, silver indeed is oxidized to produce silver oxide. So the silver oxidation process will give you a lower charge voltage compared with OER. So you can enjoy a lower charge voltage. And in the discharge process, we will first have the silver oxide reduction reaction. And this process will give you a higher discharge voltage compared with ORR. So only after the silver oxide is fully reduced to silver, we will have the conventional ORR. So you can see by incorporating the silver redox reaction, we can enjoy a reduced charging voltage, and we can increase the discharge voltage. We can achieve a discharge voltage of about 1.7 volt. So again, compared with the conventional zinc air battery, which can achieve a discharge voltage of about 1.2 volt and the capacity of about 800 milliampere hour per gram zinc, we can achieve the same capacity, but we can increase the voltage. And in this charge and discharge process, we also use XRD to characterize the material. And we find the silver oxide material is changing in the charge and the discharge process. So we can verify that the redox reaction of silver indeed is involved in the zinc air battery operation. Then we also did some electrochemical testing. We discharge the battery and a different current density, for example, and the low current density 2 milliampere per centimeter squared, up to 20 milliampere per centimeter squared. So if we do charge and discharge and this current density 20 milliampere per centimeter squared, well, you can consider this is a fast charge and a discharge. So again, even under fast charge and a discharge, the battery is still very stable. It means our battery can be used for fast charge. And again, we also test the battery over 100 cycles. So again, you can see, well, the battery performance is quite stable. We also compare the performance of our hybrid battery with similar batteries in the literature, and we find the performance of our battery is better than the similar batteries in the literature. For example, and a current density of 4 milliampere per centimeter squared, we can achieve energy efficiency of 70%. So this is higher than similar zinc air batteries. And a current density of 2 milliampere per centimeter squared, the energy efficiency is even 72.5%. And you should know that for conventional zinc air battery, the efficiency is normally below 60%. That means the hybrid battery concept is feasible, and we can improve not only the voltage, but also the efficiency. And actually, well, we can also achieve quite a stable operation for 100 cycle. Again, because we want to develop batteries for not only conventional portable electronics, we also want to develop batteries for flexible electronics. So we also developed flexible batteries using the zinc, sulfur, air hybrid battery concept. Again, we need to use the gel electrolyte, right? The gel electrolyte. So again, we test the battery performance under different current density. You can see from 2 milliampere per centimeter squared to 10 milliampere per centimeter squared, and we can still achieve good efficiency. So, and a current density of 2 milliampere per centimeter squared, the energy efficiency is still higher than 70%. So you can see even for the flexible battery, we can still achieve high efficiency and high performance, and the durability is still good. So we test the battery under different bending conditions. So we bend the battery, and then we test the battery under over 30 cycles. The battery is performing very stably. So it means the flexible battery is technically feasible, and the performance is also very good. And apart from the hybrid battery concept, recently we also look at the engineering design of air electrode, because for the air electrode of zinc air battery, we have the liquid electrolyte, we have the solid catalyst, and we also need a gas to transport through the air electrode. In the discharge process, oxygen need to transport from the ambient air into the air electrode, and the oxygen needs to be reduced. And in the charge process, the oxygen will be produced in the air electrode, and the oxygen needs to be taken out efficiently. So you can see, it's a very complicated multi-phase processes, right? We have liquid, we have gas, we have solid. So you will find the hydrophobic level of the air electrode should be very important. So in recent years, we try to control the hydrophobic level in order to improve the battery performance. So we try to treat the electrode, the air electrode, with PTFE, which is a hydrophobic material, right? So we treat the electrode with PTFE by different times, for example, by 1 time, 2 times, and 4 times. Then we test the battery performance, and it's found when we treat the air electrode with PTFE by 2 times, we can achieve the best performance. That means now we can achieve a good balance between hydrophobicity and hydrophilicity, right? Because now the PTFE loading should be optimal. If the PTFE loading is too high, the gas transport should be good. However, some reaction sites could be covered by the PTFE loading, but by the PTFE material. If the PTFE material is too little, then you will find the gas transport may be difficult. Although the reaction sites you may have a lot of reaction sites, right? So there is an optimal loading. And recently, we also did some in situ observation study on the oxygen evolution reaction in zinc air battery in the charge process. Of course, the testing is done and quite high current density, 70 milliampere per centimeter squared. This is a very high current density for charging. But you can see, for example, you can see here, you may find some bubbles are living, some bubbles are escaping from the battery. This is because, the gas bubbles can be transported through the air electrode and leave the zinc air battery, right? So based on a lot of in situ observation, we can understand the competition between the gas transport and the electrochemical reaction. Because the flow batteries are very promising for large-scale energy storage, we also developed zinc air flow battery, aiming at grid-scale energy storage. So we try to use a pump to circulate the electrolyte to flow through the zinc air battery. And we also did both experimental testing and mathematical modeling. And we find with flowing electrolyte, we can improve the battery performance. And you can see with increasing electrolyte flow rate, the battery performance can be even further improved, as shown in these 3 curves. Then we try to understand why. So we did mathematical modeling, and we first try to understand the hydroxide ion distribution in the battery. So this is the zinc electrode, and the 4 circle show you the hydroxide ion concentration on the zinc electrode. You can see for figure A, well, it's conventional zinc air battery with static electrolyte. And you can see the hydroxide ion concentration is very low, very close to 0. Because in the discharge process, this ion is a reactant. So it means, well, if the reactant concentration is very close to 0, then the performance of the battery will be bad, right? But with flowing electrolyte, if you look in the figures B, C, and D, with flowing electrolyte, the concentration of hydroxide ion can be significantly improved. So we can improve the battery performance due to the enhanced hydroxide ion concentration. So this explains why the zinc air flow battery can achieve better performance. Then we also look at the distribution of zinc ion on the zinc electrode. So again, this is the zinc electrode. The 2 circles represent the surface of the zinc electrode. And you can see, well, with static electrolyte, the zinc ion concentration is very high. You should know the zinc ion concentration should not be too high, because if it's too high, well, the zinc ions can produce zinc oxide, which is a passivation layer on the zinc electrode, which will decrease the durability of the zinc electrode. So you will find with the static electrolyte, well, the passivation risk is very high because, well, the zinc ion concentration is very high. But with the flowing electrolyte, then you will find the zinc ion concentration on the zinc electrode is reduced significantly. This will significantly reduce the chance of passivation. So this means, well, with flowing electrolyte, we can also achieve better durability. So based on the research, we find with the flowing electrolyte, we can achieve both high performance and better durability. Of course, you need to use a pump and you need to consume some power to drive the electrolyte flow. But with larger scale battery, well, we believe the pumping power will be much smaller than the power you can generate from the battery. So for large scale zinc air flow battery, we believe they will be very suitable for the grid scale energy storage. Apart from the zinc air battery, well, we are also working on some other electrochemical systems like fuel cells and low-grade heat utilization. So we are working on high temperature solid oxide fuel cells. We developed a multi-physics model and we try to understand the coupled transport and reaction processes in fuel cells. And we also developed new materials such as the electrode material and electrolyte material to improve the fuel cell performance. And recently, we also developed the electrochemical system, and we can successfully convert the thermal energy, low-grade thermal energy to electrical power. So this is a very brief summary of research activity conducted in Hong Kong. In summary, I'd like to make conclusions. So you can see the hybrid zinc metal air battery can achieve both high discharge voltage and high capacity at the same time. And there is an optimal PDFE loading to achieve enhanced battery performance. And the flowing electrolyte can improve both the performance and the durability of zinc air battery. And of course, I'd like to seek possible collaboration with researchers from other countries to work on these electrochemical systems on fuel cells, batteries, and low-grade heat utilization. So we are working on materials, and we also need DFT calculation, and we are using conventional technique for material characterization. So if you have advanced technique, advanced facility for material characterization, I think we can work together on this very exciting research area. So this is my end of my presentation. This is the end of my presentation. I'd like to thank my group members and the funding support from Hong Kong PolyU and also the Hong Kong Research Grant Council. Thank you so much for your attention. So if you have any questions, please feel free to let me know. Oh, I find one question from Professor Dinser. Thank you for your question. What is your opinion on large-scale commercialization of zinc air batteries? Would it be possible in the near future? I think it's possible because actually the zinc air battery have been commercialized, but they are primary zinc carrier battery, not rechargeable zinc carrier battery. I think one benefit of zinc carrier battery is the low cost. Their cost is much lower than the commonly used lithium ion battery, but in the past, there are only some primary batteries not rechargeable. Now we are working on the rechargeable zinc carrier battery, and we believe, well, we can commercialize. However, we still need to work on the zinc electrode, because as mentioned earlier, the performance of the zinc carrier battery highly depends on the air electrode, and we have worked on that for a few years. But now we need to work on the zinc electrode, because the zinc electrode is responsible for the durability. In our research, we tested the battery for about 200 cycles. I think the battery demonstrates very good durability. However, for commercialization, I think we need to achieve thousands cycles, maybe a few thousand cycles. So we still need to work on the zinc electrode to improve the durability for over 1,000 cycle testing. But I believe in the near future, maybe in a couple of years, it's possible that the zinc carrier batteries can be commercialized. Thank you, Professor Dinser, for your question.
Thank you very much, Professor Magny. If you can please unshare your screen.
Okay.
Thank you. And we will look forward to the progress of your research, and look forward to hearing your further achievements. And I also appreciate your call to the participants and beyond for collaboration. Thank you very much.
Okay, thank you. Yeah, thank you.
We have a minute or two for a quick question. If from the audience, if there is a question, please put that in the chat, the Q&A box. I see none currently. In the name of saving time, I would encourage you to put your questions anyway, but I would like to move to our next speaker, and Professor Meng can potentially respond in writing during the next presentation. Now we will move from a technical and technology-based presentation to a policy one, and welcome the speaker, Ms. Bahare Sayadi, from the United Nations Department of Economic and Social Affairs, UNDESA, in New York. Ms. Sayadi is serving as a Senior Sustainable Development Officer at UNDESA, and in her capacity with the United Nations, she has advised governments, UN agencies, private and civil sector organizations on topics ranging from sustainable energy to climate in policy, programming, and implementation issues around the world, from Africa to Central America to Arab states and Asia Pacific. Ms. Sayadi holds a graduate degree in electrical engineering from McGill University in Canada, and postgraduate degree in climate change science and sustainable development from the Montfort University in the UK. Ms. Sayedi, the floor is yours.
Thank you very much. Thank you so much for the invitation. I'm very happy to be here with you all. I have put together a few slides, so let me see if I can share them with you. Okay, can you see my slides?
Yes, we can. It's perfect.
Excellent, excellent. So again, thank you for the opportunity. As mentioned, my name is Bahare Sayedi, and I'm a Senior Sustainable Development Officer at the UN. The title of my talk today is Achieving Universal Energy and Net Zero Emissions from a Policy Perspective. As Oakley mentioned, this is a little bit of a different talk from my previous colleague who spoke about energy storage and his research. The objective of my talk is to kind of give you an overview of this conversation around energy science and technology, and where does this fit in the global policy discourse when it comes to sustainable development, mainly around the issues that the United Nations works on and the commitments that the 195 members have made. So a quick outline here. The achieving universal energy access and net zero emissions are top priorities at the moment globally that are agreed to by the 195 member states of the UN. So I will give you a brief overview of where in the development agenda this topic specifically fits. Then we will go into a little bit more detail on where we are in terms of progress. And then what is the outlook for the future? What are some of the agreed to key policy recommendations moving forward? And then some opportunities for you to engage in as you proceed with your research and your work in the various institutions that you represent today related to these topics. So let me broadly say that energy access and achieving net zero emissions are two sides of the same coin that are really critical to for us to address some of the most daunting and challenging issues that the world is facing. And this is now widely recognized and integrated in some of the most prominent multilateral agreements that countries have agreed to. So one of those agreements is called the Sustainable Development Agenda, the 2030 Agenda for Sustainable Development. This was agreed to in 2015, and it really charts the path forward for achieving sustainable development by 2030. It has 17 goals, and each of these goals has a specific number of targets. Overall, there are 169 targets for this agenda. The goals are universal, which means unlike or compared to the previous agenda of sustainable development, which was focused mainly on developing countries, this one is universal. It applies to all countries everywhere. So every country can strive to achieve these 17 goals. And for the first time, the set of goals includes not only social goals that are related to people, poverty, hunger, education, gender, and so on, but it also has goals related to prosperity, reducing economic inequalities, decent jobs and economic growth, but as well as environmental goals and issues related to climate change, issues related to biodiversity, issues related to the oceans and water. So it is the most comprehensive development agenda that the world has seen so far. And it recognizes that these issues are all interrelated. So these goals are not meant to be implemented in isolation. But if you look at the energy goal, for example, it is recognized that the energy touches on all other socioeconomic issues. So it needs to take that into consideration, and it needs to be implemented in an integrated manner. So now digging a little bit deeper on the energy goal, that is goal number 7. Its title is Ensuring Access to Affordable, Reliable, Sustainable, and Modern Energy for All. In the UN world, there's quite a bit of negotiation happening when these goals are agreed to. So this is the first time that a goal was agreed to on energy specifically as part of the development agenda. This goal has 3 main targets. One of them is about universal access, which is essentially about the people in the world who don't have access to electricity and who are still relying on using solid fuels and insufficient cooking and heating methods to cook their food and heat their homes. And I'll go a little bit into more detail in terms of the numbers and data. The second one is about renewable energy. As you know, the conversation about renewable energy is quite advanced, and when it comes to addressing climate change. And so this target is specifically about expanding the share of renewable energy in the global energy mix. And then the third one is on energy efficiency. Again, you know that renewables and efficiency come hand in hand, supply and demand equally important. And so energy efficiency is one of the key targets. Now, the 7A and 7B that you see are what we call means of implementation. These are enabling goals. So the first one focuses on facilitating clean energy research and technology, which is very relevant to the topic of this conference. And that includes cleaner fossil fuel technologies and cleaner, basically, infrastructure technology and so on. And the next one is about infrastructure needs, in particular in the setting where for most the least developed countries, the small islands, and those countries who are lagging behind on this topic. Of course, the net zero goal is closely related to the conversation that is currently taking place around climate change. Again, there's a dedicated goal in this agenda on climate change. That is a goal number 13, taking urgent action to combat climate change and its impact. It has 3 targets as well. The first one focuses on the conversation around resilience and adaptive capacities. So that whole area of adaptation. The second one is about integrating climate change into national policies, strategies, and planning. And the third one is about education, awareness raising, institutional capacities, and so on. The enabling goals for this, or targets for this goal, are about finance is one of them. If you follow the negotiations on climate change, you will know that the 100 billion goal that is ingrained in the Paris Agreement is quite critical, especially this year. And so that is one of the enabling targets that is mentioned. And then the next one is about capacity needs of the least developed countries, the small island states, and those nations that are the most vulnerable to climate impacts. Obviously, there is a link between this agenda and the Paris Agreement. This agenda recognizes that anything that is going to be discussed in terms of what needs to be done around climate change is formally negotiated under the United Nations Framework Convention on Climate Change. And I am sure you are all familiar with the Paris Agreement, which was adopted in December 2015. It is the most important multilateral agreement on climate change. It really sets the goal of stabilizing the global increase in average temperature below 2 degrees, aiming for 1.5. And of course, to achieve that, achieving net zero emissions by 2050 is paramount. So this is where the conversation about energy, climate change, science, technology fits within the broader space of sustainable development and the global agendas that countries have come to and are pushing forward to galvanize action around these issues. Now, how do we know where we are with these goals? There are a number of reporting mechanisms that look specifically at the progress made. For example, every year, the Secretary General of the UN puts together a report on all the SDGs, all the Sustainable Development Goals, and where you can see where we have reached with the goal and what is lacking and where we need to be going. On the goal related to energy, and specifically energy SDG 7, there's a body of international organizations who focus on issues related to energy who have come together, and they have formed a group that specifically looks, tracks, and monitors data related to the goal on energy. And there is, on yearly basis, they put out this report, which is called the Tracking SDG 7 report, and that takes you through each of the targets and what is happening in terms of progress. And of course, on climate change, there's different institutions and organizations who are working on tracking science and data related to climate. Of course, one of the most credible one is the IPCC, and they are the main body of the United Nations that does the assessment of climate science. And you may have already seen the latest report, which came out yesterday with some sobering numbers on where we stand on climate science currently. So just to give you a sense of progress, where we're at. And this is based on the reports that I have mentioned. So what has happened right now is that there's been great progress on some of these goals so far. So around the development agenda, overall issues related to reducing poverty, improving maternal health, child care, access to electricity. These are some of the goals that we have seen progress. And that progress, you know, took place before the pandemic. Of course, now we are 2 years in the pandemic, and there has been some effect regarding the pandemic on these goals. But what is important to highlight here is that even though there was progress in early 2020, we saw that we were still not on track to achieving many of these goals by 2030. And so now the pandemic has happened and some of these goals have actually been pushed back. So in terms of, you know, the poverty reduction goal, we are now seeing 119 to 124 million people who are pushed back into extreme poverty. On the goal related to inequality, 255 million full-time jobs have been lost since 2020. And the gender goal, for example, 10 million additional girls are at risk of child marriage. And of course, on climate change, despite the slow economic slowdown, we have witnessed an increase in the global GHG emissions still throughout 2020 and this year as well. And by early 2020, the temperature increase was, we were already at 1.2 degrees above pre-industrial levels in terms of the global average temperature. And according to the IPCC's report from yesterday, at the moment, we're actually at 1.1. So that is quite close to the 1.5 goal that we have set ourselves in the Paris Agreement. Of course, climate change continues to affect every region, and it is expected that the impact will increase with additional warming. And that includes changes to wetness, dryness, wind, snow, coastal areas, and oceans. Now, if we zoom in on the goal related to energy in particular, I mentioned the first target on access to electricity. If you look at the progress, this is where there's been some really good progress in the last decade. So in the last decade, between 2010 to 2018, 1 billion more people gained access to electricity. Now, especially with COVID, you can see the importance of having electricity in communities, in schools, in health centers as a key enabler to address many of the challenges that people face in their day-to-day lives. So this issue of access to electricity is quite important, and it's great that there has been significant progress over the last decade. However, there is still 760 million people worldwide who don't have electricity. And if you look at where in the world they are, the majority of them are within the sub-Saharan region. That's 70% of those people, and 85% of that population lives in rural areas. So this is where electrification via the power grids is hard to reach to. These are communities that are in rural areas. They are remote and they are not accessible by the main grid. And if you look at, again, another breakdown is that half of those people are in low-income countries, and 1/3 of them are in what we call fragile and conflict-affected settings. So countries that are facing conflict and shocks internally and externally. So this is the statistics about where we are on energy access to electricity in particular. Now there's the universal energy access has another component that sometimes gets under-recognized, and that's the issue of access to clean fuels and technologies. When we talk about energy in the context of the needs of the developing countries, the conversation tends to sort of focus on electricity only, but another critical issue is clean fuels for cooking and heating. So again, there has been some progress, not as good as electrification in the last decade, but we have gone from 56% of people having access to clean cooking fuels and technologies to 63% in 2018. However, 2.6 billion people still cook and cook with solid fuels and heat their homes with inefficient cooking practices. And that is the main cause of 4 million premature deaths per year, according to the World Health Organization, because of the indoor air pollution that this issue causes. So you can see it is an energy issue, but it has health impacts. It has, and majority of the people who are working in indoor settings with these kind of fuels and stoves are women and the children around them. So it has that social implication on gender. It has economic impacts. It has health impacts. And this is the interlinkage between energy and other issues. Now, on the renewable energy goal, of course, we know that the energy sector needs to be decarbonized if we really want to achieve the Paris Agreement and hit that 1.5 or 2 degrees stabilized global average temperature. And there is no denying of the fact that we are experiencing a renewable energy revolution. The cost of some technologies like solar and wind have drastically decreased over the last decade, and that is great news. There's some breakthroughs in energy research and innovation. Energy storage, for example, is one that we heard about, and that is critical to this conversation around the role of transitioning energy towards low carbon systems. However, if you look at the global share, we are still around 20% of renewables in the global energy mix. And so that means we still have a much longer path to go if we really want to do the decarbonization of the energy systems globally. Finance comes to play when we talk about energy transition. Again, when it comes to renewables, there's been great progress in terms of increased investment in renewable energy technologies over the last years. So for example, between 2010 and 2017, we've reached $21 billion of investment. But if you look at where that investment has gone, only 12% of it has reached the least developed countries. So there's definitely a kind of inequality in terms of how finance is flowing in the energy sector towards issues that are critical to the transformation of our energy systems globally. And that issue of no one should be left behind is quite visible on the financing conversation. Now, energy efficiency, I mentioned this, is of course quite important as the supply side is looking at the demand side and reducing inefficiencies. And so if we look at the global energy intensity improvements over the last years, there has been an improvement of 2.6% per annum, but what the global community of scientists and organizations who are focused on this issue are recommending is 3% per annum by 2030. So again, we're not on track with that goal. What's the outlook here? The outlook is that if we continue with the current trajectory, we will continue to have 620 million people in the world by 2030 who will still lack access to electricity. We will continue to have 2.3 billion people whose health is going to be jeopardized because they will continue to rely on solid fuels for cooking and heating. And of course, the world will predominantly continue to rely on fossil fuels and technologies. If the rate of renewable energy penetration continues the way it has, and again, we are at risk of reaching the 1.5 or exceeding the 1.5 average global temperature in the next 20 years, again, according to the IPCC report from yesterday. Again, on energy intensity, I mentioned that we will be able to hit 2.3% by 2030, but what we need is 3%, and we're not where we are. So this slide shows kind of what needs to be done. Obviously, it is recognized this data is clear, we're not where we need to be. We need to scale up action, we need to raise ambition. But some of the critical issues that different countries and institutions are now huddling around are these. First of all, closing the energy gap. So in many countries where that gap still exists, governments and other stakeholders need to make it a top political priority. And that means that in the planning of their energy policies, energy projects, energy financing, and innovation related to energy, this issue of achieving universal access to electricity and clean cooking by 2030 has to be prioritized so that those that are currently without access can be given access. The second one is really about energy transition. So the transition from the current situation to Paris-compatible, low-carbon, and decarbonized pathways. And that means rapidly scaling up renewable energy technologies, a better focus on energy efficiency improvements. And of course, there's also, there needs to be a conversation and a focus about coal. So now coal and fossil fuel-based technologies. So the recommendation that is given now is that we need to move as fast as possible away from coal power plants, not opening new ones and closing ones that exist, and reach a 50% capacity of coal by 2030. The third one is about leaving no one behind, and that is looking at the interlinkages between energy and other socioeconomic and environmental issues, and making sure, for example, that in the transition, those who will lose their jobs are taken into account. So there's issues related to creating green jobs for those who will transition from fossil fuel industry to the green sector, and issues related to those who are most impacted by the lack of energy access, including women and children and the most vulnerable countries, and designing policies, financial instruments, and packages of support dedicated to those particular communities of people who are impacted to ensure that there is no one left behind. The fourth one is about finance, which is critical. And here, the recommendation that is emerging is to triple the clean energy investment globally, and particularly pay attention to the financing that goes to the least developed countries, as their ability to really tackle these challenges will rely on finance. It also includes phasing out inefficient fossil fuel subsidies and support for more innovative market-based approaches, such as putting a price on carbon and carbon pricing and so on. And the last one, of course, which is also really important and touches on all the other previous recommendations, is about harnessing innovation, technology, and data. So looking at energy innovation that addresses the key gaps that we talked about from the demand side, from the supply side, and also focusing as well on the digital divide. Many countries currently don't have reliable data, for example, and that's critical to focus on. I'm conscious that my time is running, so I'm going to go very quickly through the next set of slides. Basically, there's a number of opportunities designed for countries and other stakeholders to come together and look at the progress and state what needs to be done and then do more. So one of the most important ones this year is happening next month. It's called the High-Level Dialogue on Energy. And of course, the COP in Glasgow would be very important as well. So the dialogue is in 40 years, it's the first time that in 40 years, countries are coming together at the heads of state to discuss energy in particular. The purpose of it is really to close this gap between the net zero and universal access and to ramp up admission. It has two goals. One is to generate a roadmap towards achieving universal access by 2030 and net zero emission by 2050. And the next one is to generate action and commitment around it. So that's what we call energy compacts. The dialogue is structured around 5 themes: energy access, transition, enabling SDGs, innovation, data, and lastly, finance. There are a number of countries and global institutions who are leading the way. We call them global champions. And the leading institutions are all those recognized international institutions who are involved in the domain of energy. 5 reports have been already produced with key details on what needs to be done on these key issues that you can access online. And just very briefly on energy compacts, it is an opportunity for you as an academic, for you as someone who's working in the business industry, or an NGO or anywhere to contribute to this process. Is a voluntary commitment to make sure what you're doing in your area of work is counted towards this global movement on achieving universal energy by 2030 and net zero emissions. And so I encourage you to have a look at the resources that we have on energy compacts. There's a 6-step process. There are workshops you can take, and you basically develop an energy compact based on your work, which has concrete goals to achieve. And we will be able to showcase that in September. And it will be tracked and monitored over time, and there will be opportunities for updating them and raising ambition over time. The website for the Energy Compact is listed here. Please have a look. And if you have more information on the dialogue itself, there's another site. So I will end it here. Thank you again for the opportunity, and happy to answer any questions there may be.
Thank you very much, Ms. Sayedi, for this comprehensive presentation. If you can unshare your screen, we can go to the regular conference modality. And now looking at the Q&A box, I'm not seeing any questions, but here is your opportunity to put your questions in. But making use of my chair position, let me ask a question. The cutoff date for submitting nationally determined contributions was almost a week ago, 10 days ago. And we have seen some increase in the number of submissions. The end of the year was a little discouraging. And of course, it's too early to make an assessment, but can you give us your insight as to how NDCs are moving, what direction, and if we should be concerned or happy or cautious?
Thank you so much. This is a great question, and I should have mentioned the NDCs a bit more prominently in my conversation, because energy is quite a big piece of the NDCs that countries are submitting. In fact, most NDCs have energy as a key sector. So just to be clear, on the cutoff date, there is no cutoff date as of such. Countries are still welcome to submit, but for the submissions to be considered in the synthesis report that is going to be produced, UNFCCC sets this deadline so that they could do the assessment. That doesn't mean that now nobody can submit the NDC. As we have seen, NDCs continue to come, and I expect them to continue to come until Glasgow and beyond. And as you know, actually, all countries are encouraged to submit the NDCs by this COP. But those who are obliged under the agreement are those who have a target of 2025. And the majority of countries actually have a target of 2030 in their previous NDCs. So the fact that we see so many NDCs, over 100 NDCs already submitted, is a really encouraging sign, because these countries are not the ones, or only a small portion of countries had the obligation to come forward with NDCs. But what we see is momentum around every country in the world who is really focusing on this topic to raise ambition and come with an updated NDC. So I see it as a quite encouraging sign that we have so many countries already submitting NDCs, and we will see more by the time of the COP. And so that's one. Secondly, I think, you know, the net zero emission goal by 2030 has also created quite a bit of quite a bit of traction around the NDCs. So there's the NDCs, and then there's the long-term strategies that are focused on the 2050 and net zero emissions. I think with the IPCC report, it's pretty clear that we really need to do backward planning from, you know, 2050 to the current NDC, and then have this ramping up of ambition over time. So I see the NDCs as the mechanism to do that. As long as globally every country agrees that by 2050 we need to reach net zero emissions, then there's some flexibilities for countries to kind of use the next several years as a way for aligning their NDC with that trajectory. So the one that we see in December, or the synthesis report, may not put us on that trajectory at the moment, but the mechanism of the NDC is such that it is going to be ramped up over time. So we are doing better and better and better over time, so that by the time we reach 2050, we have gone on that trajectory. And so I personally am hopeful. I think there's a lot more global importance put on the issue of climate change, the NDCs, and this net zero emission is becoming mainstream around the world.
Thank you very much. Thank you for these insights. And of course, we appreciate your insight and look forward to NDCs being implemented, and more NDCs and more ambitious NDCs to be put in line. Let me see if we have not received any questions. So I would like to thank you, Ms. Sayedi and Professor Meng, for your respective presentations. And with this, I close this session of the conference. Thank you.
Thank you. Thank you.
Hello Salih Hocam.
Şamil Hoca merhaba. Sesim geliyor mu?
Ben
Sesim geliyor mu Şamil?
Merhabalar.
Merhaba Birol.
Merhabalar Salih Bey. Şamil Bey.
Birol benim sesim geliyor mu?
Evet duyuyorum sizi çok net.
Şamil'inki gelmedi. Şamil mikrofonu aç. Şamil, microphone is closed. Click on it.
Yeah, okay.
Okay, now it's okay.
I have opened. Okay.
Yeah, okay.
Good afternoon. Salih Hocam, I have located in Gümüşlük, Bodrum, and helicopters have transport water to the very near fire. I am very sorry. There is a many helicopter voice after my house.
That's okay.
First of all, thank you very much for attend to Turkish Academy of Sciences Energy Technology Conference. If you're ready, I can start. And first speaker is Professor Salih Saner from Cyprus. I give some information about Professor Saner. Please, a few minutes. I don't find information, but I can talk with my memory. Professor Saner is a petroleum professional, have worked with Turkish Petroleum Company, Kral Fahd University of Petroleum and Minerals in Saudi Arabia, Schlumberger in Saudi Arabia as a professor. Now he have worked for nearest university, and Salih Saner give a presentation about geopolitics and geology of the Eastern Mediterranean. Please, Professor Saner.
Okay, I am uploading the slides. Are you receiving my slides now?
Yes, it is look good.
My slides are on, okay. Okay, as you see, my topic, I have two topics. From the title, you are going to see that geological and geopolitical controls on the hydrocarbon source in the Eastern Mediterranean. Too many people talking, writing about Eastern Mediterranean. It is becoming a big, great issue. So, my two concerns are geological evolution of the area, because geology is important in occurrence of hydrocarbons. The formation properties are formed as a result of geological processes. And the second one, geological evolution controls the occurrence of oil, and geopolitical issues are important in controlling the operations, exploration, production, transportation. So there are many importances that we can talk about the Mediterranean, Eastern Mediterranean, but our concern here is energy issues. And when we talk about energy issues of Eastern Mediterranean, one is transportation and the other is the reserves and resources. I put stars there, reserves, resources, 2 stars, but transportation issue is 5 star. More important, what we are going to see now is a map, what I got from my friend. As you know, 48% of oil reserves are in the Middle East. And this oil is transported to the market in Europe. You can see how the transportation pathways coming from Middle East, from Red Sea, coming from pipelines and going to Europe. So importance here, Suez Canal is very important, and the Eastern Mediterranean, everything is passing from. So if you interrupt this transportation here, you are going to paralyze Europe. Another thing is, of course, some pathways are going to Far East, some hydrocarbons are transported to Far East, but transportation to Europe, and today even LNG from United States, if you want to transport it to Far East, it has to come from Gibraltar, Mediterranean area, Suez Canal, and go to Far East. Let's come to the issue now, reserves issue. When you look at the oil hydrocarbon occurrences in the region, we have 2 zones, 2 belts. One is from Turkmenistan to Romania, Azerbaijan, Turkmenistan, in this belt, and the other one is starting from Oman, going to Qatar, Iraq, and coming to North Africa. So Eastern Mediterranean is on this belt. Why shouldn't have hydrocarbon? What is the reason of these 2 belts? We have to look at the world map millions of years ago. First, we are starting. Millions of years ago. Now it's going to be a historical presentation. 225 million years ago, there was a single continent called Pangaea and Ocean Pantalassa. And shallow areas of this sea here in this area, Tethys Sea, there is a bay, big bay, ocean. The shelf area are these zones I show you as hydrocarbon bearing zones. So shelf of Tethys Sea is prolific. What happened? Years ago, as we saw, there were Eurasia, Africa here, Gondwana here, 2 continents, and the ocean, Tethys Sea in between. In geological time, we have some plate movements, what we call in geology, and Gondwana part started breaking off. So this breaking off from the Gondwana started forming new seaways between those lands, those continents. And while these things are pushed to the north, this one was opening. This is the new Tethys Sea, new Tethys. Where is Cyprus Island today? Cyprus Island is not an island. This is 190 million years ago, what we call in geology Varrovian time, there was no Cyprus. It was somewhere in this oceanic area. And gradually, while these small continents are pushed to north gradually, closing the Tethys Sea and opening the Neo-Tethys, still Cyprus Island is not an island. So this area, gradually, after this one, this area, this oceans here, this seaway pathways are closing. This is Turkey now. This is Turkey, and this is Greece and Italy. So while these are compressed northward, and this one is opening, later on, this one started also getting compressed between Gondwana and Eurasia. Between two continents, this area, when this one started getting compressed, that time some slices from the bottom of the sea started coming up and forming the island of Cyprus. The first, Troodos mountain rise up. These are very new compared to the 200 million we started. Now this one is 15, 20 million years ago in Miocene, early Miocene. Troodos mountains appeared as an island in the area. We are seeing some riphoidal rocks, riphoidal islands in the area surrounding Troodos. Later on, and later on, 8 million years ago, Mediterranean Sea dried up, all Mediterranean, and the lower basinal areas remained as salt lakes, but everywhere is salt. There was no ocean between Africa and Taurus, from Eurasia to Gondwana. So it was land. We call this one Messinian crisis. Then the connection, again, we got connection with the Atlantic Ocean, and water came back and it formed a sea, Mediterranean of today. And this time, with the uplift of the Beşparmak Mountains, we are having two islands. This was salt basin before, so sea is covering everywhere. We have Beşparmak Island, we have Troodos Island, and now small changes in the sea level, going back, coming again. We are having Beşparmak Island, Troodos Island, and the basins between them, young basins. All today basins, in order to look for hydrocarbon, you need to have basin, first of all, sedimentary basins. As we said, from one side, Africa is pushing from south, and on the north we have Eurasia, and we are having Mediterranean today. The basins that we can talk about, the basins, that areas where we can explore, look for hydrocarbons are, one is Levant platform, what they are calling. Other one is Nile Delta and Herodotus Basin. This is the Herodotus Basin. Herodotus Basin. They are on the extension of Africa plate. Africa plate. So they are on the passive margin of the Africa plate on the continent, but they are partially oceanic. They are far from the land, oceanic. These basins, three basins, were studied by USGS, United States Geological Survey, and they said, you may find 122 trillion cubic feet of gas in this area. In Nile Delta, 223 trillion cubic feet of gas. And in Herodotus Basin, you may find 123 trillion cubic feet of gas. Israel was, of course, Egypt found in 1960s gas here in Nile Delta, and Israel was trying to find drilling. 460 wells they drilled in the shallow waters because technology was not allowing to go to deep seas that time, and they couldn't find oil. After this USGS study, they went to deep sea areas here, and first they found Tamar oil in 2009. So, and this one encouraged everybody in the area, USGS reports plus finding of Israel. After this one, Israel continued exploring, and they found bigger than Tamar, another 2 fields, and Cyprus also found 3 fields in the area. Then Egypt went to deep sea also here in this area, and they found bigger than Israel and Cyprus, Zohr field. So in the area, it is proven that there is hydrocarbon. And this is the cross-section from Africa to Taurus block to Turkey. There are basins in between. So this is the basin, Nile Delta, and Levant Basin is on the extension of Africa. And in the Taurus Mountains, between Cyprus and Taurus Mountains, we have a basin sitting on accretionary prism. This is the difference. This is very important difference, actually, making this one more important in terms of oil occurrence. We have Paleozoic and Mesozoic, but here everything is broken. And after Paleozoic and Mesozoic, Tertiary is normal sediments on this accretionary prism. Anyway, but if you are looking for gas from tertiary here, tertiary there, so it means it is possible to find gas also in this basin, why not? But USGS didn't make a study, and our studies, Turkish studies, came very late. Now, as a result of this geological process, we said we have Paleozoic system, Mesozoic system, and we have tertiary. We have a salt deposition which dried up, and after salt we have very young sediments. This is the sequence that we are drilling, and mostly our findings in Mediterranean are from 4,000 meters, and they are reported as biogenic gas. I was surprised first when I heard biogenic gas, but unfortunately, it is true. It is biogenic gas. All the results are showing biogenic gas because the geothermal gradient is very low in the area. Now this one is showing occurrences where we are having oil fields in the area, Tamar, Leviathan, Karish, or Israel, and Cyprus Aphrodite first finding, and Cyprus found Calypso. Egypt found Zohr, and Egypt has lots of small gas fields in Nile Delta. Here, Palestine also having 2 fields, but I think Israel grabbed them. They are not allowing Palestine to exploit it, because if you sell oil, you may buy a weapon. That's why Israel seized the fields here there. if you look at the results, these are the numbers that I don't want to give you details, but these are the resources that the USGS gave, and these are the numbers. So it means 122, 38 is found so far. And no exploration on the Cyprus, to the north of Cyprus. Antalya, Mersin, and Laskia fields are not explored yet. So the amount of oil that found, this is the found oil, this is the estimated reserves. And the amount of oil they found is not so huge compared to world reserves. They are making too much sound, but it is good. It is $50 to $60 billion maybe, but compared to the world reserves, it is not so big. Up to that point, Greek, Israel, they were doing exploration. Greek, Cyprus, and Greece, they were trying to declare for exclusive economic zone and give concessions, license to companies. Turkey was not able to do anything because no drilling rig, and when they try to rent a drilling rig for deep seas, they are not giving to Turkey. Oh, if you take and drill in Cyprus, so it's making a political issue, you know, no seismic. So Turkey decided to do something. And gradually, Greeks started in 1974, and Turkey started actually intervening the game at 2018 with Subya crisis. Subya crisis is the one that Turkish Navy stopped Italian Saipan drilling rig accessing to the drill location. And after then, right after that, in 2019, Turkey bought modern seismic ship. Two of them are available, and one was available before. 3 seismic ships, and Turkey bought 3 drilling rigs for deep sea drilling. And Turkey in 2020 came up with a blue homeland map of Turkey. Then Turkey signed an agreement with Libya for exclusive economic zone. And in 2021, recently, there is a declaration of sovereignty target for Turkish Republic of Cyprus. So area completely changed. So game changed now. So many years Turkey was not able to intervene. Now Turkey is intervening, is scrambling everything for them. Of course, the reason behind this is European Union, which is supporting a Greek side. This one is showing gas reserves in the area. This is Russian gas, and here is Qatar and Iran, Turkmenistan, and the Cyprus Eastern Mediterranean gas is going to be this much. That's why they are saying Cyprus gas is needed to replace, you know, they don't want to be depending on Russia. So no, it cannot. Yeah, so this much gas. Yeah, it is a good income, but it is not equivalent of Russian gas. Today in the area, Greek side came up with this, you know, blockage blocks, exploration blocks. They drilled, they start finding gas, and later on Turkey, after procurement of deep sea drilling rigs, Turkey started opening wells in the area. I think Western countries stopped drilling on both sides at the moment, but I don't know what will be happening in the future. So because Greek side came up with their own exclusive economic zone, which is not acceptable for other countries. It is clashing with Turkish exclusive economic zone, and also it is also from Egypt, from Israel, from Lebanon there. If you put the midline, they are getting extra lands. In order to come up with exclusive zones, you have to go with UNCLOS, United Nations Convention of Laws, International Court of Justice, International Court of Arbitration decisions. You have to consider all of them. And one important issue is not middle point, it is also equity. European Union, why European map is not considered, is not considering equity principle of UNCLOS, creates disputes in the European. So this is European Union supporting this one, which proposed by Greece. So European Union is responsible also of the conflict in the area, giving this area, exclusive economic zone area, to Greece and Cyprus, because European Union is not a court to decide. Turkey now came up with a blue homeland map. No, the map should be like this. We have agreement in Black Sea. Aegean should be, this is, by the way, this is not the ownership of the sea. This is exclusive economic map, exclusive economic zone map. It is not, it doesn't mean this area is belonging to Turkey. It is international sea, but the exploration rights are going to be Turkish in these areas. This is the Turkish map. There is a great difference between the European and Turkish. They are not giving any sea for Turkey, huge continent. Turkey says, this is my area. And Greece and Cyprus says, no, this is yours. That's why the source of conflict. So let's come as conclusions, what will happen. Our conclusions now with these observations. Economic gas reserves have been proven in the Eastern Mediterranean. We have hydrocarbon in the area. Finding more gas and crude oil in the future is possible. Gas reserves cannot be enormous to be an alternative for Russian gas in Europe. Discovery of gas deteriorated the political tensions in the area. So the discovery of gas created more problems. And continuing with the conclusion, European Union has a responsibility in exclusive economic zone disputes by issuing Sevilla map. The Sevilla map is they got this map done by a Spanish university, and by coming up with map. We have insecure environment in the Eastern Mediterranean. It is obstructing operations, narcotics, gunboat policy, wars, terrorism, everything. And the limitation of exclusive economic zone and solving legal ownership problems are necessary in the area. Without doing this one, exploration is not going to bring prosperity in the area. Turkish Republic of North Cyprus, hydrocarbon rights are upcoming from 1960 Republic of Cyprus Foundation law. Now we are going with independent Turkish Republic of Northern Cyprus, and this Northern Cyprus state is going to have hydrocarbon rights. It has to be considered in all the agreements in the future if we can make peace and agreements. And what we are saying, the last word is no peace, no beneficial hydrocarbons. The hydrocarbons that found They are not going to bring any prosperity. Israel is not selling. Cyprus is not exploring and selling, doing nothing. And the companies, exploration companies, are getting big share in such a conflict areas. When they are making agreement, they are getting a big percentage. No, nothing is left for people, probably. Okay, this is all what I wanted to say. Thank you very much for those listening.
Thank you very much, Professor Saner. Your interesting and comprehensive talk. Please, are there any questions? Use chat or NIQ section. During this time, I want to ask you one question. You know, Professor Saner, Turkish Petroleum Company have drilled many wells on Cyprus and offshore area, but they were abandoned as a dry. What is your comment?
Actually, we do not have any information about the completions. You know, they are saying dry, maybe dry, but that is normal. You know, in exploration, you can, as I told you, Israel drilled 460 wells before drilling Tamar well. You know, so you know, you may need to go with more drilling in the area, and the results are not so sharp to us, so not clear to us. They didn't tell about completion.
Okay, thank you again.
Okay.
There is any question, and we can continue with the next speaker.
Thank you, Shamil.
Next speaker is Ibrahim Çemen from University of Alabama.
Well, can you make me a co-host so I can share my screen?
Yes, please. Share your screen, please.
All right. So am I co-host now? I guess. Let's see, participants. You need to make me a co-host before I can share my screen.
Okay.
Or maybe I am. I'll see if I can share my screen.
Okay. TÜBA technicians will help you. Please wait.
All right. Okay, I'll go all the way to the...
Okay, we can see your presentation.
Okay.
First of all, I would like to give you information about Professor Çemen. Professor Ibrahim Çemen is a petroleum structural geologist conducting research at and teaching at the University of Alabama, Department of Geological Sciences. Professor Çemen is an Istanbul University alumni who joined Oklahoma State University School of Geology in 1984. After earning his PhD in geology from Pennsylvania State University, he was awarded early tenure and promoted to associate professor in 1986 and became full professor in 1994. He have served as the department head of 5 years at Oklahoma State University and 4 years at the University of Alabama. Ibrahim Çemel gave a presentation about shell fracture analysis and modeling. Please, Professor.
Thank you. Can you hear me?
Yes, yes.
Oh, thank you, Professor Chen. And thank you, Salih Abi, for all that nice presentation. I'll start with a little bit of a personal touch before I start my talk. I was one of Salih Abi's assistant back in what, 1972, 73. And he was doing his doctorate thesis under Professor Altanlı, and we went to Bilecik, and we helped Salih Abi and Okay Abi, Okay Gürpınar. We learned a lot. That was really excellent educational opportunity for us. And we actually appreciated later more than in that summer. That usually happens. Students do not appreciate what they are learning as they are learning, but later they appreciate it. So thank you, Sadia. All right, now I'm going to be changing the gear completely. This is not going to be a big picture oil and gas systems of talk, but more in a small scale quantitative natural fraction analysis, basically using this terrestrial LiDAR machine, which is really interesting machine that we've been using for quantitative natural fraction analysis for the last 10 years or so. We do a lot of detailed work, and there's a lot of applications for this machine. So although I'll be the presenter of this talk, but this is by no means by my work only. I thank to my graduate students who work on this project. Again, we can't do anything without graduate students. I had 3 graduate students doing master thesis in this project, Robert Venchel, Benjamin Ginter, and Jeff Clark. They are basically the contributors of this project, and they did great work as their master's project, and they are all working as geologists now. Before that, when I was in Oklahoma State, we started this project, and Onur Ataman and then also Josh Hensel, they did work. But basically, this would be a summary of work by Robert Venchel, Benjamin Ginter, and Jeff Clark, and we actually just submitted a paper to AAPG based on Robert Venchel's work. Okay, after this introduction, then what is so important about natural fraction analysis? I mean, every time we do a work, we need to ask ourselves, why are we doing this? And that's one of the things that I actually learned from God bless his soul, Enver Altanlı. He always say, why are you doing this? Why are you doing this? It is basically when we do this, horizontal drilling and hydraulic fracturing have revolutionized gas exploration in the United States. It was a big game changer in the late 90s. When I was at Oklahoma State University, and I was the chair back then, and we were working with all those oil and gas industry people in Oklahoma and Texas. It was really a time of revolution. And these 2 methods, though, rely on basically robust productive reservoir models. But then those models has to have a good input in terms of the fractures. If we don't have a good understanding of natural fractures in their geometry, all this, the reservoir models that engineers do is really down to drain. In other words, garbage in, garbage out, but you gotta put a good data into the model. And that's how we started this. I'm gonna be telling you a little memory as we go along, how we started this project back in 2006 at Oklahoma State University. Actually, maybe it's 2004. Okay, just briefly, I'm sure all of you know about this natural fractures. But when we talk about natural fractures, they are basically systematic fractures. And there is three modes, the extensional, also called opening mode. There is two shear mode fractures, one basically sliding and tearing. But then there are those other systematic fractures, what is called, they are shear fractures, and they are conjugate shear fractures that form basically 30 degrees to sigma 1 direction. And so fracture systems then can be systematic and non-systematic. In reservoir fraction analysis, or basically outcrop scale fracture analysis, we always think about systematic fractures. We want to get rid of the non-systematic fractures. And then, but sometimes it is hard to identify all the non-systematic fractures, because the reason we don't want to consider them, they are new, they are formed very recently, and they do not affect the quality of the reservoir. But then not all systematic fractures parallel to one of the principal stress directions. As I talked about, we have conjugate shear fractures forming 30 degrees to sigma 1 direction. Anyway, so much from my structure class. Now, what does terrestrial LiDAR do is basically it uses point cloud data to create 3D models and high resolution images of the outcomes. How does it do it? In terms of understanding of the physics, it is simple, but of course, building these machines is very sophisticated. And there is a machine, this is the LiDAR machine. We use Regal VZ400, and there's a Nikon camera attached to it. There are tie points. These tie points are important because basically with the laser LiDAR laser beams here, and then it measures the distance, and with respect to these tie points, and then we get this 360 degree image acquisition here. But the first image is so bad, we can't do anything with it. But then with the Nikon or any other good quality camera, second color acquisition scan is done by the camera mounted on top of the LiDAR machine. Then it adds color to it. And with this color, basically, we can really see a lot of fractures, nice bedding planes, and we can do a lot of measurements, unbiased measurements. That's the one important thing about LiDAR machine, that since it is done by the software, it is unbiased. It measures everything. Then yeah, we will talk about this pitfall. Sometimes it measures those non-systematic fractures too, and it is hard to basically get rid of them. Now, there is a software that comes with this machine, RiseScan Pro software. It has this window, a simple window that we are becoming to accustomed to see in most of those softwares. And again, scan position is very important. We need to get 2 or 3 scan positions to put all that together. Now, resolution is very important. Here, when we look at this in an outcrop scale LiDAR images, this is 0.08 resolution, which is standard. And if you're working with a large area, maybe it is good enough. But in an outcrop scale, it is really not enough at all. So we need to adjust on the resolution. This is 0.08. And then when we do 0.01, things start to get a little focused. And then when we do 0.08, it is better. This is the highest resolution we've been able to get, mostly because of the machine's capacity and our computers' memories and all that. But this has been, with our experience, this is enough for us to do a lot of measurements and see everything in very clear. So resolution, when you work with LiDAR, resolution is very important. And so what we do, then these high resolution images, basically, they reveal fracture spacing and fracture density, and they allow us to quantitatively assess how these fractures vary in different sections of a shale unit, where bedding thickness, mineralogy, and degree of deformation differ significantly. So we have two major objectives with all that work. One, bedding thickness and the mineralogy. Basically, we determine whether a statistical relationship exists between A, bedding thickness and the mineralogy, for example, silica content versus organic content, and B, bedding thickness, fracture spacing, and fracture density. This is all relating to gas shale reservoirs, because based on this data, statistical data, the models can be built for better production of the gas shales and gas shale reservoirs, especially in Woodford, which is perhaps the most important gas shale unit in North America. Now, we can do all this nice, fancy animations from the outcrops. You can see a very detailed view of the outcrops here. And then also very detailed view of the outcrops in a, like, this is 1 meter scale. You can see everything. And then you can tell the software to measure whatever you want to measure in this scale, which we call inventory scale. So a lot of things are done by the software, but we have to tell the software what to do and how to do it as well. So now, after this quick introduction to capabilities of a LiDAR machine as we use it, there are other capabilities of that machine. Then I'm going to be introducing you to basically the Arkoma Basin, where I have been studying since early 90s when I was a faculty at Oklahoma State University. Basically, we studied natural fractures and their relationship to silica content and bed thickness. Silica content is important because silica areas of the Woodford silica is better reservoirs. So, and then this is in the southeastern Oklahoma, here Arkoma Basin, and this is the Arbuckles, the Anadarko Basin, just to locate you geographically, those of you who are not familiar with North American provinces. And then here, Arkansas, Oklahoma, this Mississippi embayment here, Tennessee, Mississippi, and the Arkoma Basin is north of the Ouachita Fault Thrust Belt. It's basically a foreland basin of Ouachita Fault and Thrust Belt. Just briefly, tectonic history of the Arkoma Basin. It starts with the fragmentation of Rhodania in latest Precambrian, early Cambrian, formation of Proto-Atlantic or Iapetus Ocean. And then from late Cambrian to late Devonian, it's a nice big passive margin. This is all North American craton or Laurentia in general. And these are all called North American myogeoclinal rocks. And those shallow marine carbonates and some shale units are here. Then this is a very nice passive margin environment, just like today's East Coast and West Coast, East Coast of North America and West Coast of Europe, the passive margin. So then in late Devonian to early Mississippian, there's a subduction zone forming, which is the south dipping subduction zone to the north, Gondwana and Yucatan Block here. And there's the volcanic arc. And then South America, which is part of the Gondwana, starts to move to the north And then here is the flysch deposits here, and these are the earlier shallow marine carbonate and deep marine shale and chert units here. Then we have this northward movement of southern continent, and eventually South America collides with Laurentia or part of North America here. Then that happens in late Mississippian to middle Pennsylvanian. We have a clastic wedge, which is the incipient Arkoma foreland basin. There's the accretionary wedge here, and then there's the forearc basin. Then basically here we have all this. There's a formation called Atoka Formation that we've been studying for many years, and this is part of this Arkoma foreland basin. And then in late Pennsylvanian, we go to this coal-bearing morass phase of foreland basin formation in Arkoma basin. And what is so interesting and in a way nice in Arkoma basin, this is the last episode of tectonism. When we look at basins in Anatolia, they have basically extension, compression, and other latest Extracellular motion with the westward escape of Anatolia. Everything is so complicated. In Arkoma basin, we have one major event, extension, and then passive margin deposition and compression. That's a lot. To some extent, it is a lot easier to study the North American basins, especially the Wachitas and Appalachian basins, which we've been working in Appalachian basins recently as well, and that's very interesting. Now, let's talk about Woodford Shale and its environment. It is basically late Devonian, early Mississippian, organic rich marine shale, that's what makes it a great source rock for conventional reservoirs in the Arkoma basin, including spiral reservoirs that we've been studying. Then it is deposited on stable shelf, a passive margin, influenced by marine upwelling. We're going to talk about that soon. And basically, it is a long-term regressive deposits. And some of you may be familiar with these terms, Fresnian and Feminian boundary. The sequence stratigraphers discuss about this boundary a lot, and that's a very important and a lot of implications for basically North American stratigraphic and structural development. Right here, we have this passive margin, shallow marine units. Basically, Woodford is deposited in this area. So this is from Blackie's 2016 diagrams. Now, here, when we look at the positional environment of Woodford Shale, it's basically influenced by marine upwelling. And it's a simple diagram showing some anoxic patches along a passive margin, which we have today in east coast of North America and west coast of Europe and west coast of Africa and east coast of South America. There are patches of organic rich zones. And those are very important for formation of source rock. And this was the area of Woodford in basically Devonian. So that's, there are overwhelming evidence to suggest that Woodford was deposited in this upwelling zone and organic rich zones area that I'm not going to go into detail, but that's basically quite well accepted by stratigraphers, structural geologists, and geochemists working in the Arkoma basin. Now, here is the story that we started this project. And we had this meeting with one of the major oil companies in Oklahoma. They invited us there in their office in Tulsa, and we started talk. And they say, Dr. Chairman, we have this problem that we've been producing from Woodford in basically Western Arkoma Basin and the Anadarko Basin and the Arbuckles in these areas. In some areas, we have great production. In some areas, we don't have good production. And engineers are using those default reservoir models, but we don't really know why we are producing a lot of gas in some areas and why we're not in other areas. Basically, they were crap shooting throwing the dice. And then they said, we know, because they've been, especially back then, they've been doing a lot of hydraulic fracturing. They were basically flooding the reservoir very badly to some extent, and then producing gas. But they really didn't know what was the original natural fractures and what new fractures they were producing, and why they were producing new fractures in some areas and why not producing new fractures in other words, in terms of they had good production, but they didn't know scientific part of it, why they were producing more gas in some areas and none or very little in others. And then my good friend, Darwin Boardman and Jim Beckett, we said, we can help you. First, we do the stratigraphy on the outcrops, and also then we will study the fractures in the outcrops. And we started this project back then, and then we gave them a report a few years later. I think it helped them. Now, all this, we have three major research questions. I'm going to come to the answer to this. I think we have provided pretty good answers recently for these three research questions that we've been working almost like 15 years by now. One, is there a relationship between bedding thickness and natural fracture spacing and fracture density? And two, does the mineralogy vary vertically in the outcrops and between the outcrops? And if so, does this influence the formation and distribution of natural fracture? Three, what effects, if any, does the localized folding and at surface outcrop have on natural fracture method? In other words, we're talking about here the influence of local structure control, like folding and little faulting in the outcrop scale on the formation of the fractures, rather than regional fractures that those three natural fractures. So then we have worked, we did in the, from 2005 to 2009 and 10, when I was at Oklahoma State, we worked basically with hand measures. We measured the fractures, density, and the opening in the field with regular rulers. But then when I came to Alabama, as part of my startup package, they bought me a new LiDAR machine, which which is really a cool machine, as I've been talking about. Then here we have recently, we work on these two outcrops, which we call Waponoka and Ataka outcrops. In the Waponoka outcrops, the Woodford is nice, gently dipping unit. This is the upper Woodford. Here, this is also upper Woodford, and we're going to, down here, there's very steeply dipping. It's basically a steeply dipping limb of a drape anticline. Here, there's the seismic shows nice, well-developed truss below. So then recently we studied these two outcrops, and that again, Robert Menschel did a really great job here, and we're publishing this. When we look at this stratigraphy of Woodford, here, the Hunton group underlies the Woodford. Hunton is a limestone unit with a lot of karstic structures. And then Woodford is middle to late Devonian shale. And in Ouachita Mountains in Arkansas, it's a more charred unit, and it's called Arkansas Navoclite, which is upper Woodford, but it has more charred. The upper Woodford in Oklahoma also has charred and silica, but not as much as Arkansas never flight. And when we look at this here, then again, lower Woodford here, basically, oops, what's happened? Lower Woodford is moderate silica, moderate clay, low TOC, but the middle Woodford is low silica, a high high TOC. Middle Woodford is very high in TOC. That's actually the source rock. The upper Woodford is high silica, low clay, low TOC. So what my good friend Roger Slatt and I, we always thought that actually this upper Woodford is the reservoir. The middle Woodford is the source in classical petroleum system analysis. And the lower Woodford is very much influenced in early depositional pattern by the caustic structures in Hunton. And as a very, there are very varying thickness of Woodford in the lower Woodford, but then middle Woodford is a nice source and upper Woodford is a nice reservoir. So upper Woodford is basically reservoir part, in quote, is the unconventional reservoir. And middle Woodford is the source of the unconventional reservoir. That is really, I like those terms. Roger Slatt and I, this is from Roger's 2015 paper. Roger was in Oklahoma, University of Oklahoma, and I was at Oklahoma State. We became really good friends, and we did a lot of work together. And again, the upper Woodford is a nice reservoir. Now, we studied these outcrops and the fraction analysis. Basically, here we have Waponoka outcrop and Atoka outcrop. Again, Waponoka is nice, it's a gentle dipping upper Woodford, and this is steeply dipping upper Woodford. There are three methods that have been proposed for outcrop scale natural fracture study: scan line sampling, circular scan line sampling, and window sampling. We use window sampling method. We think it fits best for our purpose. And basically in this window sampling method, parameters are measured in what's called inventory scale. We determine this 1 meter, 1 meter, 1 meter. So it is 1 meter square area. And then within this inventory scales, we measure bed thickness, fracture spacing, and then fracture density has been calculated based on these measurements in terms of number of fractures per unit, basically fractures per centimeter, or you can do it for per decimeter, basically. But fracture for centimeters work because these are highly fractured units. And then when you look at this, for instance, there's a lot of fractures in that inventory scale. Also, obviously, we also did a lot of sample collection from these outcrops to determine the mineralogy and petrography of the shale. Samples collected from varying bed thicknesses. Here we have this thinly laminated to up to 2-inch thick, which is 2 inches, about 5 centimeters. For those of you who are not familiar with this US measurements. Here we have this laminated beds, and then 0.5 inch, which is about like a little over centimeters, and then 2-inch beds, which is 5 centimeters. This shows the location of our samples. After this, we did XRF data analysis for this to determine the composition of the samples, especially for silica content. And those of you familiar with this XRF data, preparing those glass beads and all this is a good, important work. Thanks goodness there are graduate students doing those things, and that's very, very important. Samples of varying bed thicknesses are taken from each outcrop for XRF analysis. We prefer XRF. XRD doesn't give us good results. XRF is important for determining silica content, the organic content. Of course, we always had to do classic petrographic analysis. Always reminds me again, Enver Altun, he always wanted to have some thin section work in every thesis, which was really good. We still do it. After all those years, importance of petrographic work cannot be underscored. Basically, it's very important work. And there's always new things in petrographic analysis that tell us more about what we're doing. Here is my little lab here with this nice microscope and a screen. And basically, we prepared thin sections and analyzed for mineral composition. Now, first, I'm going to be talking about Vaponica first inventory fraction analysis. This is our inventory scale, 1 meter scale here. When we measured in the field, we scanned this in a very high resolution and then run those software analysis with using RiseScan Pro. And there is also Riggle provides a software of their own. We use that, but there's also software. Some people use MATLAB and for analysis of this inventory scales. When we put all this together, bedding thickness, increasing bedding thickness basically correlates with increase in average fracture spacing. There's a nice correlation here. As the bedding thickness increases, the average fracture spacing also increases. And there's a nice correlation, R-square of 0.9. And for bedding thickness and fracture density, which is fracture per centimeter, this correlation is pretty good as well. Of course, as the bedding thickness increases, density decreases. Then in Vaponica 2 inventory scale here, we also did this analysis with using this Riggle software. Then bedding thickness increases and average fracture spacing also increases. And then here bedding thickness increases, fracture density decreases. So there is that reverse relationship here. And here the correlation is 0.88. It's still pretty good correlation. Here is R-square 0.86. It's still pretty good. And in Atoka, this steeply dipping areas here, the correlation is not as good because there are basically other fractures here that because of the folding. This folding provides
Professor Temen, last 5 minutes, your talk, please.
Okay, all right. So I have 5 minutes to go? Or am I 5 minutes over?
Yeah, yes, please, 5 minutes or
okay,
6 minutes.
I can finish in 5 minutes. Okay, bedding thickness is increasing and average fracture spacing increasing, and bedding thickness increasing here, fracture spacing decreasing. Again, the correlation is not very good because of this new fractures forming due to folding. Here, the same thing, bedding thickness increases, average fracture spacing increases. Again, these are a little better correlations in Atoka inventory scale 2. We also did petrographic analysis. Silica content in upper Woodford is biogenic. This is very important in forms of radiolarians. There's a lot of radiolarians in the thin sections, and there's pyrite and bitumen present in the thin sections. Beds that have higher silica content will generally have a greater thickness that we have determined based on our field measurements. And we got this XRF results, basically bedding thickness versus silica content. It's not a very steep correlation, but basically as silica content increases, bedding thickness increases as well. Then we have been warned that there are some possible areas of possible errors in our statistical analysis. Some people propose that using Excel is not a good way of doing statistical analysis. They recommended some other programs, but me and graduate students use Excel. It is easier to use. But then there are other people, they say, if you're using with newer versions of Excel, which we are, then using Excel is okay. The error is negligible, especially for our work. And some non-systematic fracture networks may be present within inventor scales. Yes, that's always there, but it's hard to distinguish them. And then measurement errors. This is when you use LiDAR, it's basically measurement error with only dark spots within the LiDAR images. And we did some other comparisons. Here is our Atoka set, north 45 east, and second set is north 60 degrees west, and then first set, north 15 west, and north 80 degrees. Owner's study he did with this all with his hand measurements back in 2008. Then he determined two sets, and then Josh Hensel, he used LiDAR. He also determined three sets in basically McAllister shale pit here. So their study and our study with Rob Pinchell's and Ben Ginter's studies and Jeff Clark's studies basically correspond. Now, here is the, remember I told you we have three major questions. Then in terms of conclusions, here are the answers for the research questions. One of our most important question was, is there a relationship between bedding thickness and natural fracture spacing density? Yes, as the bedding thickness increases, fracture spacing will increase and fracture density will decrease. So that's actually is very important conclusion. And does the mineralogy vary vertically in the outcrop, within the outcrops, and so does this influence the formation and distribution of the natural fractures? Yes, silica content is elevated around Atoka 1 inventor scale, and elevated silica content will generally be associated with an increased bed thickness that we have determined. And three, what effect, if any, does the localized folding at the Atoka outcrops have on the natural fracture networks? Areas with elevated silica content will react more brittle to localized deformation, causing additional complex natural fracture networks. So basically, organic rich shales are not good for fracturing. We want less organic, more silica to have fractures. And then implications of LiDAR fracture analysis data. Terrestrial LiDAR images provides a very detailed study of natural fracture patterns that can be used for reservoir modeling. And this is me in the field, and this is the LiDAR. And then in the field, we call it, in reference to Star Trek, Star Wars, we call this RT-D2 because it rotates. And then areas of intense deformation, such as Atoka outcrop, basically needs to be studied individually to fully understand local fracture network. Then it can be applied to subsurface for reservoir analysis. Anyway, thanks for listening. Any question? So from major Eastern Mediterranean oil and gas reservoir analysis to small fracture analysis in Arkoma Basin.
Thank you very much, Professor Çemen, for your excellent talk about fracture analysis of US important shales. I have just looked to the Q&A section. There is no questions, but I want to ask you about, clay, squares and carbon-rich shales have more fracture, natural fracture. But clay-rich shales, organic-rich shales are not rich fracture.
Yeah.
You know, carbon storage is very important facts of today. And carbon dioxide storage shales is not recurring clay-rich shales, because
that's right.
more fracture is escape of the carbon dioxide to the surface. When I ask you about which shales clay-rich in US?
Well, the Woodford has parts of it clay-rich, parts is not, which is why it's a very thick unit. And also there are the Chattanooga, that in some places it is clay-rich, which is also equivalent to a Woodford in terms of its age. But then there are also Cretaceous shales, which I haven't studied. I've been studying only the Devonian shales on mid-continent. So I don't know much about the Cretaceous shale units in like in Bakken Shale, in this other basins.
Thank you very much.
But the clay, organic rich shales are very bad in fractures, but they may provide a good, great source. That's why when they do the horizontal drilling, they drill into silica-rich units where they can fracture the reservoir well and then get the gas out, which is migrated from the source below, from organic.
Thank you very much again,
You're welcome.
Professor Çemen.
Thank you. Thanks for your invitation
to the TÜBA Energy Conference.
Thank you.
Next speaker is Professor Birol Dindoruk from University of Houston. His talk is about is related with data mining, machine learning in the oil and gas industry. First of all, I would like to give brief information about Professor Dindoruk. Professor Dindoruk is currently a professor at the University of Houston Petroleum Engineering Department. Previously, he was the chief scientist of reservoir physics and principal technical expert of the reservoir engineering in Shell. Most importantly, Professor Dindoruk is currently editor-chief in the SPA journal, which is a very important journal of the Society of Petroleum Engineers. Please, Professor Dindoruk.
Okay, thank you very much. Thank you very much, Dr. Shan. And also thank you for the kind invitation of the committee here as well. And it's interesting, my previous colleague over here, Dr. Çemen, is teaching at University of Alabama, where I got my master's degree a long time ago.
Oh, right.
Yes, in 1980s, last century. I'm going to talk about today on data mining, machine learning in the oil and gas sector, and I will give specific applications in the area of petroleum engineering. One of the things about the applications is that they're going to go pretty fast, because every single application that I'm going to talk about, specific example, is the paper itself, but I'll share which resources that I have for those, and I'm going to show the cross-section of the things that I have directly involved. And there are reasons for it that I'll highlight later on. And here's the quick outline of my talk. I'm going to talk about modeling the physical processes first. I mean, what we do and what are the changes recently, at least the perception. And I'll talk about disruptive and fast changes in our industry and industry as a whole, in fact, and where we are in our specific industry and with respect to others. Then I'll highlight a couple of things about data and process integration and focus on the cultural elements of it. Then proxies, theories, and data. I'm going to bring a couple of classical problems over here along with these specific implementation examples for focus areas. These are the focus areas that I focused actually. It's not necessarily a cross section of the focus in the industry, but again, I'll bring a couple of issues regarding that. Then I'll conclude the talk. So what we do normally is that, especially in academia, we try to publish, of course, at the end of the day, and even in the companies. So the real problems that we involve, normally we pose the problem somehow and we formulate it. Then we have the mathematical model, but many of us know that if you write the mathematical model generally in general forms, it tends to be very difficult to solve, especially with analytical techniques. So we simplify somehow. Of course, there's a justification here. Then we have the solution, then we interpret the results. We interpret the outcome, I would say, towards the results. Then we make decisions based on that. Then if we have issues with the results, depending on is it good enough for the purpose, it depends on our purpose as well as our risk appetite or error appetite. Then we go back to the real problem and we may visit it. And we may go cycle this thing. And also, we, of course, try to predict what might happen. Generally, prediction is key for many of the problems that we solve, so that if we can predict, we can go directly to mathematical problem as well. But of course, we have the scrutiny of management on these things all the time. Or funders, they say, so what? Why are you doing it? I mean, can you justify this thing? So now, of course, with the data, etc., we try to shortcut it in many ways. I mean, we have the problem itself, and we use the data. We go into directly to the prediction mode towards the results. Of course, content becomes very important. However, especially in a couple of days, a couple of years ago or earlier days of in a way, overheated data science domain, we had a lot of people in open public presentations. They said, I don't need the content. Just give me the data. I'll tell you what it is. But of course, we all know that, and people who are focusing on the physics of it, it's not always true, actually. In fact, if you have the content information, you have competitive advantage over others. I'll give you a couple of examples of it in the coming slides here. So when we look at the technological changes in engineering in general, this was prepared for petroleum engineering, waves of petroleum engineering methods. I crossed the petroleum here on purpose, and it's true for pretty much all technical areas over here. I mean, we have step changes or big changes. These are relative changes. One may not think that, you know, slide ruler was important, but before, if you look at the previous time, these were important things. Calculators came in, then the mainframe was there. Of course, it was for elites and nerds and sci-fi kind of people. I mean, you see in the movies, etc. I mean, I remember still the Star Trek, etc. That's the first place that I've seen mainframe in a fake way, I guess. But now, of course, the biggest step over here is the desktop computing, and large-scale numerical calculations became enabled. So desktop computing means that things are distributed as well. I mean, this is kind of the precursor of the entire data domain. I mean, you have large digital output, but of course, when desktop first came, nobody looked at the large digital exhaust, what it generates and how we can collate it. Of course, internet and a couple of other things, enabling environment, led to high performance computing in a collective way, not necessarily specialized visualization. And of course, now the step that we see over here with the dashed here is that, in fact, it's a solid line, data mining and machine learning. But of course, the problems that we are trying to solve is also getting more and more complex in the meantime, actually. I mean, we always stretch ourselves to the resources. So the After the fifth step here, high performance computing, databases, accumulation of knowledge, data models, and analysis became very important. In fact, these things started like late 80s, early 90s with various companies. But now what we are dealing and what we will be dealing is going to be even more complex. It's going to add other ingredients. You need to add energy and environment, union of many factors when you bring them all together. Let me just highlight a couple of things about the current landscape for oil and gas. We are lagging in digitization, but competition is moving. Competition over here is other industries as well. In fact, if you look at the top companies, market cap, etc., there are a lot of companies that they weren't there 20 years ago or so, actually. I mean, Google's, Facebook, etc. They are basically banking on data, and it's a competition for everybody. Competitive landscape is different than before. Barrier to entry to new businesses is not as big as before. You can operate like a bank and you can buy the services. You can form an oil company overnight if you want to. You can just buy the components if you have the cash. So of course, the competition is different now, and the problem that oil industry or oil and gas is lagging with respect to others. This is a relative scale. I mean, we may all think that we are digital on everything, but generally it comes with the territory. Risk and investment intensive businesses tend to hold on more on transformation in general. I mean, it includes oil and gas, healthcare, insurance, government. I mean, you can still see a lot of doctors walking around with paper, actually, even today. And but the gains are enormous over here. So the current and future challenges, when we look at it, the current over here is depending on which day or which decade you look at it. It's always current, it seems like. But what we know is the environment is changing fast and coupled with complex problems. What is impossible, the motto over here, or the understanding should be, what is impossible today will be easy tomorrow or easier tomorrow. If you think this one, I got a lot of heat. In fact, I published that statement in 2005, I underline here. If you think your job can be done by a machine, soon it will be. If you really think about it, it's gonna happen, it's a matter of time. And more competitive landscape not declared anymore. I mean, this is again, analysis of the word competition in the financial reports, annual reports of companies. After 2010-ish or so, there's less mention of competition. Competition goes, at least the wording goes in an implicit way. And you will see why in this one. One of them is the companies are mentioning more on digitization in earnings and analyst calls. If you look at here, 2017, 18, 2019 was incomplete over here. So probably it exceeded 2018. With the current environment of COVID, etc., and current epidemic or pandemic, probably things got accelerated in various fronts, especially when you cannot go to the office, you have only digital options. Based on International Data Corporation survey of 100 upstream energy executives, it's interesting that this is all lined up. We see when we look at 5 investment priorities in 2020, 2021, data centralization has probably the highest priority in their investment priorities, basically how we can put everything together. Because if you want to do any kind of machine learning or data analysis, the precursor is basically getting the data. Data consistency, integration, quality improvements, data governance, they all are kind of like equally distributed, give or take over here. But the first one is, in fact, many times we see data centralization and bringing data in a usable form is even more than 60%. So if you want to apply artificial intelligence or data analytics or machine learning, whatever the acronym that we are using, by the way, these things are probably in the dashboard, but they're not new either from a fundamental point of view. But we have the right enabling environment and things are getting cheaper. But the first step is, again, take the stock. What data is available? Where is that data? Is it in the right format? This is the boring part of it. But if you want to get into this business, you got to spend a lot of time over here, which we did in pretty much all the publications that I had. We spent a lot of time. This is the boring part of it, but it has excitement here as well, because what is right, what is wrong, bring the domain expertise here. So hypothesis-based analysis. First, you look at the outliers and etc. trends. So this brings the data expertise again. Focus, use representative data set for what you want to do. Then prototype and prove. The final goal over here is to make money, of course, or positive NPV projects, hopefully, or reduce uncertainty, or become safer. What is on the way for many companies? Actually, one of the things that was highlighted in our digital energy program in SPE and various places. I used to be the technical director, board member for Society of Petroleum Engineers in this business, data science and digital engineering. And we see that culture and work processes are the top two things that are impediment in implementation on it. And I'll highlight especially, they are coupled as well. I'll just highlight the stuff about the things about work process real quick. This is data analytics types. Upstream data can be characterized by 6 V's, basically volume, variety, velocity, variability, value of information, for example. If you think that it's less valuable, you have less drive to get data. But these are some of the classical discipline-based workflows in a way for upstream, like exploration is one. They look at things, they have different tools, techniques. Reservoir engineering and development function, and that's where I operate myself. Drilling and completion and production. You can add finance, etc., other things. But one of the key things that when we look at the diagram or a table like that is that these are workflows and they are deadline driven, and certain disciplines own these processes. One of the issues here is that they don't go laterally talk to each other. But of course, now in the current environment, we are seeing more and more need for making these boundaries more porous or permeable. I'm not talking about integrated workflows, integrated reservoir management, integrated GNG and reservoir engineering or petroleum function gas together. These are all a lot of words. In reality, how we can fuse them in data level. Like if somebody had a difficulty in drilling, and if it is written in the report at the bottom of a page, how can I use that information in my modeling, for example? And it may not be so easy to extract that information. Other challenges that we have, data is unstructured, silo nature of traditional workflows. I mean, I kind of highlighted here, and data is related and needs expertise. Some data is dependent on each other. When you put things on a time series, for example, things might look independently parameterized in time, but when you cross-plot things, you may get different things out of it. This highlights actually how complex the business, the entire system analysis is actually. This is presented by one of my colleagues some time ago. And this is the reservoir, and these are various segments or components actually. You look at the well logs, you create certain type of data, you have completion information, you have markers, you have GNG data, you have fluid data, you have facilities, you have integrated facilities. And when we look at all these things as a whole, there's a system or systems engineering type of approach is needed. Every little thing over here or arrow might be connected to a software and it may not be connected to each other. So this is basically, it becomes a corporate information factory in a way. So we keep generating things. There are other complications here also. In some places in this domain, we are data rich. In some places we are not. Like if you look at direct data for a reservoir, well is the direct penetration, as direct as it gets. But when you look at production data, it's time series. You can get it every second if you want, or millisecond. And also we have scale dependency of these things as well. And when we look at today's worker, it's also supposed to be multi-skilled worker actually. I mean, if you look at it, it's donated with lots of devices here, GPS, cameras, voice on the helmet, gas monitor, all these things go to a corporate data storage or surveillance centers and being interpreted for various reasons. One of them is, of course, safety is part of it. Another one is to make everything and everybody more efficient as possible. So it requires, of course, multi-skilling foundations, actually. You get more output per person, and you have also centralized approaches. So I'm going to go, for the sake of time, I'm going to go directly jump into a couple of examples over here. In our industry, when we look at this entire complex systems that we have to manage from safety to production to the bottom line, is that we have, of course, when we go to various symposiums or read various papers, manuscripts, there are two different approaches to this thing. In fact, more than two, probably 3 or 4. One of them is that we will manage everything. I don't need anything. I can guess the entire thing, but if you give me enough data. Well, in that statement, we have two issues. I have been into projects that we wanted the information yesterday. I did modeling without a single well drilled, with no information whatsoever. So how can you data analytics on it? That's one extreme. Another one is that we have a lot of data, but they don't match. There's conflict in data. There's scale issue. There's measurement processes. And what I did is that as a result, I tried to look at various physical processes and things that I thought that it would be with my team. It could be, we could chew it, so to speak. We could get results for sure. And of course, some of the motivation behind attacking small and more self-contained problems is that not necessarily they are easier, but the thing is that in pretty much anything that we do, there's some kind of an underlying physical equation or differential equation, and the coefficients of these equations might be the proxies for digital models and how I can extract them actually. So even if I try to solve some kind of a self-contained relevant problem, I'm helping big problem tremendously because those coefficients or numbers will be used in the bigger picture or in the larger problem actually. I just like, you know, if you want to do a Google search, you need the right keyword actually. If you have the right keyword, you're going to get better results automatically. In a way, what could be the good high quality proxies? So the example that I have over here, and I'll give a couple of sub-examples, is the PVT or fluid property data. Fluid property data is that, like, for those of you who may not be familiar, is that how fast a fluid flows, for example, is related to viscosity. The more viscous, the thicker the fluid is, the lower the rate you will get, or you will get higher pressure drop if you try to force the system. Other things could be compressibility, or it could be H2S or H2S, hydrogen sulfate concentration for safety. It could be anything. So we get this kind of data from various sources, but the direct data comes from the laboratory. So we looked at the first workflow on this thing in 2015 to be exact. In fact, 2013 on, and we finally disclosed it under a consortium. So what we see is that, first of all, the data wasn't standard and everybody had a different need. And how we can store the information, how we can generate an audit trail. We looked at every single piece of it, and we basically developed 5 chunks or 5 segments. I mean, you acquire the sample, it comes from a well or a tank. So you analyze it if it makes the case, then you characterize the sample in a numerical way. Then you look at a broader picture, then eventually you store. So you store because you will be using it, either using piece by piece, or you will be using in an aggregate form. So of course, we did this thing and we had the data. I'll give you a couple of examples of it here. Some of them are gonna highlight the pitfalls. This is for bubble point prediction using machine learning. So bubble point is the minimum pressure at which the first incipient gas forms. Infinite small amount of gas comes out of solution. It's extremely important for depletion performance of a reservoir, or you can even apply it for other contexts, other disciplines as well. It's a pretty commonly needed information. So we did machine learning algorithms we applied with our proxies with simple input variables, basically. We got this great looking cross plot. This is extremely extended. This is very, very expanded rate. 10,000 or 12,000 PSI is kind of the limit, or as high as you can go. And, however, I had an old correlation that I worked on myself and with a co-author. And I put the same input to the correlation that I had long ago, like 25 years ago. Actually. The difference between these two plots is 25 years plus apart. So when I look at the classical correlation, I see one point is outlier here and in the other one is not. So somehow, of course, I got challenged from my colleagues in data science area. They were not necessarily fluent in the content. They said, well, 5 different data models are absorbing data somehow, and the correlation that you have is wrong. And I said, you know, I'm not crazy about what I've done long ago. I know it has physics embedded in it, but it's telling us something. So I wanted this point to be isolated. So it turned out to be, the bottom line is that this point was 5.6146 times incorrect in the input variables. It is a conversion factor from barrel to cubic feet, basically. So somehow another data model absorbed this one. So it was a learning, actually. So when you see things are all aligned, you may have overfitting problems as well as you may have issues like I highlighted. Another problem that we looked at is we tried to predict viscosities. We have a broader range of viscosity correlations on this thing with the data model. But also we looked at another problem here. What if we have only one viscosity measurement for an oil at a temperature that we are not interested in today? The most classical one is that I have an oil well that I'm producing, or I have a viscosity measurement for anything. It doesn't matter actually. At a certain temperature, and somebody's asking me, I'm going to steam clean it or steam flood it, and I'm interested in extremely high temperature behavior for this viscosity. How could you get that? Single data point. So we generate a trainable model basically with a reference viscosity that you can kind of nail the outcome. I mean, this viscosity range here from a fraction to million, actually, I like to highlight that one. So we have extreme cases as well. We have very little data in an undesirable form, or we have a lot of data that we need to do something about it. It's another problem that we deal. This is a relative permeability. Basically, relative permeability is, in a way, analog of when two phases flow in a pipe, how would they compete with each other in a porous media? And the permeability per phase is basically the analog of pressure drop per phase, actually, whether there's slip or not. Of course, pipe flow is going to be complicated depending on the flow regime. So is permeability. But the bottom line for the relative permeability problem was that we were able to get about 700 plus data points, good data points. And we proved that there is another piece of information hidden in functionality. And if we don't include it, we are going to get this scattering with the classical models. Classical models generate this scattering actually. Like if you take permeability as a function of saturation, which is the common approach. What we did is that we find another parameter and proved it, Euler parameter. But the problem is that if I have this parameter, I can't go back in time and measure it. I need to measure it with CAT scan. So we use a digital proxy to extract that number in a correlated fashion, and we apply it to as a proxy, as an input into machine learning model, basically. That identified the missing number for us, and we were able to collapse the information that you see here for relative permeability. So we use basically a hybrid model per se. Another thing that we looked at was that we used the public domain data for Eagle Ford, and we tried to predict API based on the coordinates in the system aerially and vertically as well. So I mean, we got good results out of it, but what we noticed is that in public domain data, there are a lot of issues in reporting, and there's no way that we can get to the bottom of it because it's confidential, or even the companies may not be in business actually. So for example, in some of the well reportings were in aggregate rather than a single well. Another problem that we worked later on is the minimum miscibility pressure identification for CO2. This is an important parameter if you want to sequester CO2 or if you want to improve your recovery of oil with injection of CO2, or it could be for cleaning, environmental cleaning actually. It could be CO2, it could be another gas as well. So in this case, we use semi-empirical methods to be able to represent the minimum miscibility pressure for oil systems. It's only measured for oils. And if you really want to measure this thing, it can cost you months and as well as $100,000 to $250,000 actually, generally excluding the sample acquisition cost on this one. So it's every point over here can be quite expensive actually. And so we were able to feed the system with some proxy equations that use the scaled input variables, which is only composition, and gives you the results. And we also shared this particular correlation engine actually through LinkedIn at rShiny. So people are using what we exposed in the open literature. Basically, many times when we read data-related things, papers, it's very hard to access that information or click on it and try to see how good it is. Generally, these are black boxes. So we try to make it as transparent as we could. We checked two other things over here. I'm going to go real brief on it, go to conclusions after this one. In flow in porous media, whether it's oil flow or unsaturated, any kind of flow, or it could be a porous material, we have various forces. One of them is convective forces. It's known in petroleum literature, if it is convective force only, it's known as Buckle-Leverett problem. The other one is convection dispersion equation. It's all diffusive basically. And of course, in reality, those forces, and if there's reaction, they all compete. What we also try to do is that if you have a physical process, especially numerically difficult, would we be able to duplicate it with machine learning? So in this case, the information that we use is totally artificially generated, numerically generated. But can we generate that data without knowing physics with machine learning? But of course, we use the physical information in scaling up and feeding the models actually. The quick answer was that yes, we were able to train and predict, validate, then test. This is the prediction. And this is the entire aggregate of it actually. And when we put random error in our measurements, in our calculations, we got similar type of scattering. We did a similar thing for convection dispersion equation as well, whether we could predict or not. Basically, these are operators for the aggregate differential equation or transport equation that governs the flow in porous media base. So this is not presented yet. Its manuscript is ready and it will be presented in September for the annual technical exhibition of Society of Petroleum Engineers. So in short, I'd like to highlight a couple of things over here to conclude this talk. Continuous progress is being made in all fronts, especially quite significant in the areas of miniaturization. We are making things smaller and sensors, and more data is coming. Basically, we have a larger digital output or exhaust, and standardization and integration is taking place. There are a lot of joint ventures or consortium type of settings that they are standardizing the data. So data storage and quality issues are hopefully being resolved. And augmented machine learning methodologies are being developed, and we can extract the value. So in short, what might be expensive or impossible today will be cheaper and easier tomorrow, hopefully. And we have the enabling technologies, and we are going towards deployable technologies. So thank you very much. And these are some of the references that we have worked on or I have presented. Thank you again. Thank you. I'll be happy to answer any questions that you may have.
Thank you very much, Professor Indorok, for your data-rich presentation from Center of Oil and Gas Houston. If there are any questions, please use Q&A section. During this time, I want to, one question.
Sure.
You know, Schlumberger, I hear that accepted to the Silicon Valley. And what is your comment on oil companies and technology companies' relation? Are there any others to the move to the Silicon Valley?
Yeah, I mean, it's a great question. As a matter of fact, the problem that we are having is the following. Everybody has data, operators. Everybody is holding on their data, and they don't know their next door neighbor's information, and they all are losing. But also data is an asset as well. So they need help from the service providers like Schlumberger. But the thing is that solution is going to come when companies agree with each other and share the data. In fact, we are in such a bad situation in the industries that, in my opinion, is that we have, let's say, a reservoir that we operated. Some company operated from, let's say, 1930 to, let's say, 2000 or 1999, whatever. And that company, let's say, bankrupt or sold. That reservoir is not being produced. All the information is gone. So that's a very important information that we should have, because we are in a situation that every reservoir has a different DNA. That's what we say. Every single one of them is important, actually. Every single one of them has some kind of a variation with respect to others. So we are just wasting our time.
What is your comment on will oil companies buy technology companies, or technology companies buy oil companies?
I think I kind of highlighted at the beginning, I don't see any difference in between anymore. There is no barrier to entry. I can form oil company today if I get capital. No big deal. What does oil companies do? Even the biggest. If they want to drill, they call the drilling company. It's not like I did summer job in the past for Shell and Turkish Petroleum, Türkiye Petrolleri Anonim Ortaklığı. I mean, we had our own rigs, we had our own people, we had our even own logging trucks, actually. Then they start coming from Schlumberger later on. So what happened towards the end, and starting in the 80s, it became, service providers became bigger, companies became a little open, and if they use something once a year, they say, why do I want to keep it? I use it only once. So as a result, technology company can be an oil company literally overnight, except, you know, permits may take a longer time, whatever the government says. But I can call Schlumberger to do the service. I can call Neighbors Drilling or whatever drilling company for it. And for engineers, I'll hire a bunch of very experienced consultants, actually. So I can make it like that.
Thank you very much. There is no question. And thank you very much again to participate and give more important data-rich presentation. Thank you very much.
Thank you very much. Thank you for the kind invitation and chairing our session.
Thank you.
Thank you, everybody.
Thank you. Thanks for the invitation.
Fire is undergoing, and plane and helicopters numbers are growing time to time. There is fire very, very near. Close to the voice because there is many roar. Bye. Thank you.
Good luck.
Have a nice day. Bye-bye.
Bye-bye.
See you again.
Okay, I see you. Bye-bye.
See you.
See you. Bye-bye.